see if the function is continuous at the given x values. We've got -3, we've got 0, and a function is continuous as long as the denominator is not 0. That's called undefined if it is. So what I need to do is I need to plug in -3, see what I get, and I need to plug in 0 and see what I get. So let's start out with -3. I got -3 squared plus 3 times -3 again. -3 squared is 9. 3 times -3 is -9. That becomes 0. So at -3, it is not continuous. That's a big fat no. Let's try it again with 0. I have a good feeling about this one. I'm going to plug 0 into the denominator. 0 squared plus 3 times 0 is going to be 0 squared is 0 plus 3 times 0 is 0, 0 again. So is it continuous when x is 0? No. Now you might be thinking, well, what about the x up in the numerator? We don't care about the x in the numerator. So even though I plug in 0 into the top and the bottom and I get 0 over 0, it's still discontinuous. No good. So that's my answers. Find where the function is discontinuous. A function is discontinuous at the x values that make the function undefined. What does undefined mean? Whenever the denominator is equal to 0. So let's do that. Let's set the denominator equal to 0 and see what happens. Now I have 2 x's. Sounds like my dating history. And I'm going to factor out one of them. When I factor out an x, I have regular x minus 4 left behind. Now what I do is I use the zero product property. I set each factor equal to 0. So x equals 0 and x minus 4 equals 0. Now when I set this regular x equal to 0, I'm done that part. There's nothing to do here. X equals 0. Over here I can add 4. So x equals 4. And those are my 2 points where my function is discontinuous, also known as the point of discontinuity. Now, I know if I plug in 0, I get 0 on the top and 0 on the bottom. And you might be thinking, don't those guys go away? No. When you have 0 over 0, when x equals that value, you get what's called a whole. It's still discontinuous, even though maybe if you were to factor things out, the x's would disappear. It still makes the original function discontinuous. Don't be fooled. Estimate where the function is increasing and decreasing. All right, well, increasing means my function's going up. Decreasing means my function is going down. Now, I'm going to try my best to make this as pretty as possible. It seems here that that's where things change. It looks like it's decreasing all the way up until -4, and now it's going uphill up until about regular 4, and then going downhill again. So increase here, decrease here, decrease here. Now, it all depends on what kind of format your book uses. I'm going to use what's called, I don't know, just like regular format. It all depends on your teacher. I'm going to say that this is decreasing. Why not start with the decrease? I'm going to say it's decreasing when the x value is less than -4. And it's also decreasing when the x value is greater than 4. I'm going to say it's increasing between -4 and +4. So x is in between -4 and +4. And you might be thinking, well, what about at -4? What about at 4? Well, it's doing neither because it flattens out perfectly. And it flattens out like this. When it does that, that is technically a slope of 0, which is neither increasing nor decreasing. Lots of calculus stuff that you'll see when you deal with calculus, but that's my guy. Estimate the relative extrema. Relative extrema is a fancy word for saying, where do I have the top of the hill? Where do I have the bottom of the hill? Knowing very well that this is going to forever be going up and forever going to be going down. Well, here's the top of the hill. Here's the bottom of a valley. I guess you wouldn't say bottom of a hill. And so I would say that there is a relative maximum at the point, looks like 0, -3. There's going to be a relative minimum when there's a bottom of a valley, and that appears to be right here to, what is that, -7? And again, the purpose of relative is I know this isn't the absolute minimum because this guy keeps going down forever. And I know this isn't the absolute maximum because that guy keeps going up forever. But if we were to ignore the up and down forever part, where do I have my maximum? Where do I have my minimum? Top of the hill, bottom of the valley. Those are my 2 points. Find the average rate of change over the interval 3 and 13/4. Well, that's going to be fun, especially because my function has a square in it. Average rate of change, what is that? Well, it's basically slope. And the way you find average rate of change is you do f of b minus f of a over b minus a. Now, what's b and what's a? Your b and your a, or your a and your b. So let's find out what f of b and what f of a are. Let's go in order from easiest to not so easy. F of a is going to be the same as f of 3. F of 3 means I take 3 and I plug it into every x up here. So 3 squared minus regular 3 minus 1. 3 squared is 9 minus 3 is 3 minus 1 is going to equal 9 minus 3 is 6. 6 minus 1 is 5. Bada bing. So f of a is 5. A was 3. Now on to the rough stuff. F of b, which is the same as f of 13/4. All right, so what I'm going to do is I'm going to take 13/4, I'm going to plug it into this function, and I'm going to square it, subtract it, minus 1. So I got 13/4 squared minus 13/4 minus 1. 13/4 squared means you multiply 13/4 times itself. So 13 times 13 is the numerator, that's 169. 4 times 4 is the denominator, that's 16. What I'm going to do is I'm going to rewrite 13/4 so that it has a denominator of 16 so I can deal with fractions. So let's multiply the top and the bottom of this guy by 4. So if we multiply 13 by 4, that gives me 52, and 4 times 4 is 16, and now I can deal with those fractions. Minus, let's turn 1 into 16/16 by multiplying it by 16/16. 169 minus 52 is 117. 117 is 101, my favorite amount of Dalmatians. Look at that. 101/16, that's f of b. Let's plug stuff in. So f of b ended up being 101/16 minus f of a, which ended up being 5. Let's do this. Let's turn 5 into something over 16 by multiplying 5 to 16/16, which is going to be 80/16. So that's just the numerator. All of that is going to be over b minus a, which is 13/4 minus a, which is 3. So why don't I turn a into something over 4 by multiplying u by 4/4? So you're going to be 12/4. Oh, that's actually going to turn out quite nice. 101/16 minus 80/16 sixteenths is 9 plus 10 sixteenths. It's a joke, look it up. 13 minus 12 is 1 over 4. A fraction divided by a fraction means multiply the top part by its reciprocal. So something divided by 1/4 is the same thing as times 4 over 1. So these guys simplify to 21 over 4. And that's my average rate of change. Not pretty at all, but a lot of fun. G of n equals negative n plus 5. F of n equals n squared minus 1. Find g of f of n. This is called a composite function. So even though it looks like this, I'm going to rewrite it so that it looks like this. G of f of 6. What I'm going to do first is I'm just going to find out what f of 6 is. F of 6 means I take f of n and throw in 6 for every n there. So 6 squared minus 1 is going to be 36 minus 1, which is 35. So f of 6 is 35. So g of f of 6 is the same thing as saying g of 35. Got to get my colors right. So I could take 35 and substitute 35 into g. So it's going to be negative 35 in a parentheses, I guess. Just got to look proper. Plus 5. Negative 35 plus 5 is negative 30. So g of f of 6 is negative 30 composite functions. Write g of x, which is this dashed line here, in terms of f of x, which is this solid line here. All right, so g of x is f of x with stuff happening to it. So let's write out the stuff that happens. F of x gets flipped upside down and gets moved to the left, looks like 1, 2, 3 times, so left 3. Whenever you flip something upside down, what you do is you multiply the function by a negative. So by flipping it, I'm throwing a negative here. If I move to the left 3, I take the x value, and I know this is going to sound crazy, but when you move left, you're actually going to add a number to x. So I'm going to take this and I'm going to add 3 to it on the inside of the parentheses. So g of x is now negative f of x plus 3. So no moving up or down. If I were to move up, I'd add something. If I were to move down, I'd subtract something outside the parentheses. If I had moved right, I'd subtract something in here, and this was negative because I flipped it upside down. So that is g of x. Fun, fun. Sketch the piecewise function. More like piece of garbage, not wise function. You like that? I did. No one likes these. I don't like them either, but here we are. I have essentially 3 graphs being drawn on the same picture, but I only care about what happens in specific areas. So this is what I'm going to do. I'm going to graph the entire function where it needs to be, and then I'm going to cut it off where I have to cut it off. If I were to graph f of x equals negative 4, it's just going to be a straight line along negative 4 right here. But you know what? I only care about this line when x is less than or equal to negative 2. So I'm going to put a little circle right there. I'm going to put my little arrow there, and I'm going to erase all the stuff that is greater than negative 2 because I don't care about this guy once it hits negative 2. I'm trying to just clean that up right there. How about that? So you are in red. Happy day. Now what I'm going to do is I'm going to, oh, by the way, fill in the circle because you're including -2. Don't know if I said that. Here I'm not including any or either -2 or regular 2. I'm going to graph the equation x minus 2 from -2 to +2. So let's graph x minus 2 regularly. Start at -2. I go up 1 over 1, up 1 over 1. And you know what I'm going to do? Since I'm supposed to stop at 2, I'm going to make this a circle, not filled in. If I were to keep going down here, I'd go down, make that a circle, not filled in, but it doesn't matter because it's continuous. How about that? And this just is a regular old diagonal, perfectly straight line. Now, the last guy is probably the most challenging to graph because I'm going to start graphing it up here and erasing a lot of stuff, right? When you graph something in slope-intercept form, it's usually easy to start, at the y-intercept. So I'm going to do that knowing that some of this is going to be erased. My slope is -2, so up 2 over 1, up 2 over 1, knowing that this is pointless. Literally, there's no points there. But if I keep graphing the slope of -2 here, here, I do include regular 2, so I'm going to fill that in, making this continuous, and I'm just going to keep going down to right 1, down to right 1, down to right 1, down to right 1. These guys connect, making a perfect straight line, as you can see from my drawing. There you go. I'm going to get rid of these guys. And there's my piecewise function. Everything connects. Will that always happen that they connect? No, it's just this one was designed to connect. There you have it. Piecewise function. This one was not so bad, but they do get bad. Find the inverse of f of x equals 2 over 7x minus 10 over 7. All right, so the best way to find the inverse is I'm going to pretend that f of x is y for now, just because it'll make things look a whole lot nicer. I suggest that when you do problems like these, you do the same. The first step that you do is you swap the x and the y. That's step number 1. So y is now x, and x is now y. Now my job is to solve for this new y. So I have myself a literal equation where I have to get y all by itself. Step number 1, add 10 over 7 to both sides, add 10 over 7 to both sides. X plus 10 over 7 don't combine, so I just have x plus 10 over 7. That's going to equal 2 over 7y. Now I still have to get y all by itself, so what I'm going to do is I'm going to multiply both sides by this reciprocal here, which is 7 over 2. I'm going to multiply both sides by 7 over 2, so I've got distributive property going on, but that allows y to be all by itself. Okay, so y is now all by itself on the right. 7 over 2 times x is just 7 over 2 times x. 7 over 2 times 10 over 7 allows the 7s to cancel out. 10 over 2 becomes 5 over 1, which is just 5. So I get plus 5. Now what I'm going to do to make this look a whole lot better is I'm going to move the y to the left and move this guy over here to the right, 7 over 2x plus 5. Remember, I turned f of x into y, so I'm going to turn y back into f of x. But since this is my inverse, I'm going to make that f inverse of x equals 7 over 2x plus 5. That is my inverse function. Can't spell inverse function without fun. Find the real zeros of f of x equals x to the fourth plus x to the third. All right, and then when we're done, we need to find the multiplicity of some of those. Okay, so we got a graph here, but the graph doesn't do it a whole lot of justice. The zeros is when my graph crosses the x-axis, and it looks like that happens at 0 and -1, but who knows? So what you do algebraically is you just set this equal to 0. And what I'm going to first do is factor out x to the third, which leaves me with an x plus 1. Now, whenever you have two or more things multiplied together equal to 0, you use what's called the zero product property, and you set each part equal to 0. So x to the third equals 0 and x plus 1 equals 0. Those are my two different things. In order to get x all by itself, I cube root everything. And believe it or not, 0 times 0 times 0 is 0. So the cube root of 0 is 0. So that's one of my potential answers. This guy's a bit friendlier, maybe. Subtract 1 from both sides, and you have x equals negative 1. So those are my real zeros. X equals 0 and negative 1. What does multiplicity mean? Well, if this is x to the fourth, technically I should have 4 answers. And technically I do. It's just since that I pulled out an x cubed, 0 repeats itself. So x equals 0 has a multiplicity of 3. It's a triple root. The other one has a multiplicity of 1. So if I wanted to say x equals negative 1 multiplicity 1, there you go. But I have essentially 4 answers, 0, 0, 0, and negative 1. And this is 3 zeros because it's x to the cubed equals 0. So that's what multiplicity means. Not to be confused with felicity, a show from the 90s. Divide using long division. I love polynomial long division. So when you do polynomial long division, your factor go there. And what go here is this guy. Oh, but be very careful. X to the fifth, x to the third. I'm missing something. So as I write this in, anything that's in between that's missing is filled in with a 0. So in this case, 0x to the fourth. Minus 15x to the third, minus 9x squared, plus 11x, plus 12. This is going to be a good one. All right. Treat this like regular long division. You start out with the first part and the first part, and you find out how many times or what times x gives me 2x to the fifth. Well, 2x to the fourth times x gives me 2x to the fifth. What I do is I take this guy right here, my quotient, and I multiply it to my factor. 2x to the fourth times x is 2x to the fifth. That will always happen that these guys are exactly the same, otherwise you did it wrong. However, this is going to be different. 2x to the fourth times 2 is 4x to the fourth. Just like long division, you subtract this guy underneath, but when you subtract this whole thing. So you become a minus and you become a minus. This crosses out. 0x to the fourth minus 4x to the fourth is negative 4x to the fourth. All right. Now we drop down the next guy, negative 15x to the third, and we repeat. Okay. X times what gives me negative 4x to the fourth? X times negative 4x cubed gives me negative 4x to the fourth. Now take this, multiply it to the entire factor, and write it underneath. Negative 4x cubed times x is negative 4x to the fourth. Negative 4x cubed times positive 2 is negative 8x to the third. Subtract this entire factor, which means flip the signs for both. This will always cross out. Negative 15x to the third plus 8x to the third is negative 7x to the third. Drop down this guy. Repeat. Okay, and we're still moving. We're like halfway done. X times what is negative 7x to the third? Negative 7x squared times x is negative 7x to the third. So take negative 7x squared times this whole factor, write it underneath. Negative 7x squared, times x is negative 7x to the third. Negative 7x squared times positive 2 is negative 14x squared. Subtract this entire product, so that makes these signs switch. Negative 9x squared plus 14x squared is 5x squared. Drop down the 11x. X times what is 5x squared? X times 5x is 5x squared. Take that 5x, multiply it to the entire factor, and write it underneath. 5x times x is 5x squared. 5x times 2 is 10x. Subtract this entire product, which makes you a minus sign. This crosses out. 11x minus 10x is x. Drop down the plus 12. I'm running out of space. X times what is x? Positive 1. Multiply 1 to the entire factor and write it underneath. X times 1 is x. 1 times 2 is 2. Subtract what you got here. So minus sign, minus sign. 12 minus 2 is 10, which becomes my remainder. So what you do, since this is positive, is I'm going to put a plus sign in here. If it was negative, I'd make it minus, but plus 10 over the original factor, which is x plus 2. So my final answer is this mess right here. 2x to the fourth minus 4x to the third minus 7x squared plus 5x plus 1. And since my remainder was 10, plus 10 over my factor, x plus 2. Long division. Divide using synthetic division. I love synthetic division. Look at it. Oh my gosh. This is what you do. This is what synthetic division looks like. Don't know why it looks like that, but we have that weird little box on the top left and this weird little box on the right. So that's how you set it up. What goes inside this little box is the root of this factor. The root is whatever makes this factor equal to 0. So quick math would be x plus 4 equals 0, subtract 4, x equals negative 4. So let's throw negative 4 in here. What goes here are the coefficients to whatever it is that we're dividing our factor from. I said fractor. I did it on purpose. If you're missing something in between, you throw in a 0, but it looks like we're not. So you just have 6 for x to the fifth, then 21 for x to the fourth, then negative 14 for x to the third, negative 8, 1 for x, and then negative 6. Drew that out perfectly. Synthetic division. Step number 1 is always drop down the first coefficient below the line. Then you take that number and multiply it to the root. So 6 times negative 4 is negative 24. Write it underneath the next coefficient. Take these two numbers, add them up. 21 plus negative 24 is negative 3. And now it's just repeat, repeat, repeat. Negative 3 times negative 4 is positive 12. Add them up. Negative 14 plus 12 is negative 2. Multiply. Negative 2 times negative 4 is positive 8. Add them up. Negative 8 plus 8 is 0. Multiply. 0 times negative 4 is 0. Add these up. You get 1. 1 times negative 4 is negative 4. Add these up and you get a remainder of negative 10. Now, what does this mean? Well, my final answer are the coefficients of whatever's left over. This is a remainder. My remainder is negative 10. Now, just like long division, you take your remainder and you put it over the factor that you use to divide this polynomial. So since this is negative 10, I'm going to have minus 10 over x plus 4. Now you go to the right and you attach variables starting at the degree of 0, which means 1 x to the 0, which is just 1, plus 0x, which means, 0x. I'll get rid of that, I guess, in a minute. Minus 2x squared minus 3x cubed positive 6x to the 4th. Now, writing this all out one last time and getting rid of this guy, I have a final answer of 6x to the 4th minus 3x cubed minus 2x squared plus 1 minus 10 over x plus 4. So this is synthetic division. I have a video on long division. Watch that. I prefer this because it's a little bit faster. It's a little bit cleaner. But I love both of them like they're my own children. If math was my own children, it would be the divisions. By the way, I do love my kids. Solve 2n squared minus n minus 4 equals 2. This is a quadratic. And in order to solve a quadratic, you really need to get 0 alone on one side. So the way we're going to do that is we're going to start out by subtracting 2 from both sides. There you have it. That gives us 2n squared minus n minus 6 equals 0. Now, this is probably factorable, but what I'm going to do is I'm going to use the old quadratic formula. Let me sing it for you. X equals negative b plus or minus the square root b squared minus 4ac all over 2a. Copyright goes to Nick Parrish. Now, I know this is x equals and I was given n, so I'm just going to pretend that that x is an n. But what I need to do is I need to label these guys up here. A, negative 1 is going to be b. Okay, negative 1, negative 6 is going to be c. We just throw stuff in. Watch out for double negatives. There's going to be probably quite a few of those. Negative b is going to be negative, negative 1. So right away we have a double negative. Plus or minus, positive or negative, big square root of b squared is going to be negative 1 in parentheses squared minus 4 times a, which is 2, times c, which is negative 6. Let me scooch that over. Let me give myself a little bit more space. And then we have over 2a, which is going to be 2 times 2. All right, let's do some simplifying. Negative, negative 1 is regular 1. Positive or negative? All right, we've got negative 1 squared, which is 1, minus 4 times 2, which is negative 8, times negative 6 is going to be plus 48. How convenient is that? All over 2 times a, which is 4. So this gives us 1 plus or minus the square root of 49 over 4. This gives us 1 plus or minus 7 over 4. Now at this part, we are going to split this up into 2. One is going to be 1 plus 7 over 4 because it's positive or negative. And the other one is going to be 1 minus 7 over 4. 1 plus 7 over 4 is 8 over 4, which becomes 2. So one of my answers is going to be not x, but n equals 2. And the other one is going to be 1 minus 7, which is negative 6 over 4, which simplifies to negative 3 over 2. So when I have somewhat friendly answers like this, yeah, the original problem was factorable, but you know, what fun is that when we could just use the quadratic formula and sing? Solve 8a squared plus 6a equals negative 5. This is a quadratic, so the first thing I want to do is get the right side, or any side, equal to 0. So let's do that by adding 5 to everything. That gets me 8a squared plus 6a plus 5 equals 0. Is this factorable? I don't know. But let's do the quadratic formula because I love the quadratic formula. X equals negative b plus or minus square root b squared minus 4ac all over 2a. One of my previous videos, I sing that. If you love a good song, look it up. Look it up. All right. Let's label U A, let's label U B, and let's label U C, and let's just plug stuff in. Negative B is going to be negative 6, plus or minus square root. B squared is going to be 6 squared minus 4. A is going to be 8. C is going to be 5. Scooch that over a little bit. Let's put it all over 2 times a, which is 2 times 8. All right, negative 6. Can handle that one. Plus or minus the square root. 6 squared is 36. Minus, let's do this kind of a little out of order. 4 times 5 is 20 times 8 is 160, I mean. So minus 160 all over 16. Okay. That's going to equal negative 6 plus or minus 36 minus 164 is going to, oh, why did I write that out? (36 minus 164). And let's switch colors. Negative 6 plus or minus 36 minus 164 is negative 128. All over 16. Now, negative 128, okay, let's just move this over here, is the same exact thing as 64 times 2, which is the same thing as saying 8 times 8 times 2. So what we can do is we can simplify this square root. And if you notice, I have a negative under there. So we have imaginary numbers. So the first thing I'm going to do after I write out my negative 6, I'm going to leave myself a little bit of space. Is since negative 128 is the same thing as negative 8 times 8 times 2, I can bring out an 8. And since it's negative, I can bring out an I. What's left over is 2, and that's going to be all over 16. Now, that's an even number, that's an even number, that's an even number. So to go a little bit further, I can pull out a 2, which gives me negative 3 plus or minus 4i root 2 over 2 times 8. Cross out the 2's, and I can finally say, let's not use x, it's a. I can finally say a equals negative 3 plus or minus 4i root 2 all over 8. Now that's pretty much it. I can be done if I want to be. I know a lot of teachers might have you split this up and go a little bit further where you would simplify that, but I'm not going to go any further. I'm out of space, and that's an answer that's good enough for me. So quadratic formula with a little bit of imaginary numbers. Fun, fun. Find the zeros of f of x equals x cubed plus 8. Now, find the zeros means, let's just set this up like this. 0 equals x cubed plus 8. Now, x cubed plus 8 should look familiar to you. X cubed is a cube. 8 is also a cubed. It's 2 cubed. So what we have is a sum of cubes. Similar to difference of squares, there's sum of cubes, difference of cubes. There's no such thing as sum of squares, but there is a sum of cubes. And it looks a little something like this. Let's just say you have a cubed plus b cubed. That's going to be the same thing as a plus b times the quantity a squared minus ab plus b squared. Now, in this case, what's a, what's b? Well, if we're comparing a cubed to x cubed, then a is x. And if we're carrying b cubed to 8, which is 2 cubed, then b is 2. So let's fill this in using the letters. A is now x, okay? B is now 2. So a squared is x squared minus, now let's be a little clever here. X times 2 is going to be 2x. And b squared is going to be 4. Now, let's not forget the original problem. This guy, x cubed plus 8, is now what's here in green, and originally it's equal to 0. So I'm not sure if I can factor this out, and I'm not even going to try to, but if my job is to find the zeros, I have one of them. And one of my zeros is going to be x equals negative 2, because I'm using the zero product property. Now, what I also know is this chunk right here is equal to 0. And we could probably use the quadratic formula to do it. So, x equals negative b plus or minus square root b squared minus 4ac all over 2a. More singing. So let's plug stuff in. A is an invisible 1. B is negative 2, C is 4. So x equals negative 2, positive 2, plus or minus the square root of b squared, which is going to be negative 2 squared, so 4, minus 4 times a, 1, times c, 16, all over 2a, which is 2 times 1, which is 2. This ends up being 2 plus or minus the square root of negative 12 over 2. Now, negative 12, or regular 12, is 4 times 3, which means 2 times 2 times 3. So if I wanted to, I can take that and turn that into the square root of negative 2 times 2 times 3, which means we can bring out a 2. Not only that, we can bring out an I, and we're left over with this square root of 3, all of this being over 2. Now I have a 2 and a 2 and a 2, so let's deal with that. 2, let's pull it out, leaves me with 1 plus or minus I root 3, close it, all over 2. The 2's cancel, and my other possible answers are going to be x equals 1 plus or minus I root 3, which goes along with negative 2. Those are my 3 answers. So one was simple, one was quadratic formula. All of this means I have 3 answers, which makes sense. According to the fundamental theorem of algebra, I'm going to have 3 answers here. 2 of them are complex, 1 of them is real. Fun, 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 fun. All right, we need to factor 28 n to the 4th plus 16 n to the 3rd minus 80 n squared. You know from Algebra 2 that factor could be so many things. It could be pulling a greatest common factor out. It could be like dealing with a quadratic. In this case, I'm going to start out by knowing that these are all even, and I can definitely bring out a 4. I can bring out an n squared, so let's start out with that. 4 n squared. When I bring that out, I am left with 7 n squared plus 4n minus 20, and that's it. I don't know why that took me so long, but it took me so long. Now, when I'm done pulling a greatest common factor out, I'm left with what looks like is a quadratic, because it is, and I should be able to look at this and ask myself, does this factor any more? Okay, can I write this guy right here as this? Well, let's try a few. In order for me to do this, I have to have a 7n and an n. One of these has to be positive, one of these has to be negative. So let me think of two numbers that multiplies out to 20. So how about 10 and 2? If I were to make you a positive 10, and if I were to make you a negative 2, and do a little bit of math, I'm not going to get that plus 4. That didn't work. Okay, so let's try this. Let's try, you know what? I think I figured it out by guessing and testing. If I made you a positive 2 and made you a negative 10, then when I FOIL these out, I have 7n times n, which is 7n squared, 7n times 2, which is 14n, minus 10n, I get my 4n, and then I have my minus 20. So if you struggle with a problem like we just did there, this is called solving quadratic equations with a leading coefficient. I have videos on those, and I'm not going to spend a ton of time doing that here, but I have a pretty significant video on how to solve quadratic equations when you have a leading exponent. Make sure you look that up, because that's the problem here. Okay? But we're done. We factored. We don't have to solve. We don't have to do any more. That's it. Evaluate f of x at k. All right. This is kind of a bizarre problem. This is supposed to lead us into the fundamental theorem of algebra. And right now, all it's asking is for me to find f of 1. Okay? I don't know why it's written out this way. Sometimes it'll say x equals 1, but this is not something to overthink. You just plug in 1 for every x. So 1 to the 5th minus 4 times 1 to the 4th minus 5 times 1 squared minus 5. Okay. 1 times itself a bunch of times is just going to be 1. Minus 4 times itself a bunch of times. 1 times itself a bunch of times is 1. 5 times another 1. And then 5 is all on its own. You become 5. You become 4. You become 5, that's negative. You become 5, that's negative. 5 minus 4 is 1. 1 minus 5 is negative 4 minus 5 again is negative 9. So f of 1 is negative 9. And that's it. Find the remainder when f of x is divided by x minus k. All right, so this is all about the remainder theorem, which says if I have a factor x minus k, I could take that k, which in this case is negative 2, and do a little bit of division and get a remainder for a polynomial. So what I'm going to do, since it's a whole lot faster, is I'm going to do synthetic division. All right, I have a video purely on synthetic division on this channel. Give it a watch. But this is more remainder theorem-y, so I'm going to treat it more remainder theorem-y, which I'm pretty sure theorem-y is a character in Lord of the Rings. Just kidding. That's not the case. I've got, let me see, 5 and then 5 again, and then negative 7 and then 7 and then 5 and then negative 4 and then negative 1. And I'm expecting my remainder to live right down here, whatever that might be. If you're missing like an x something, like if I was missing an x to the third, I would make sure I use 0, but I wasn't missing anything. Everything's already in order. God is good. Step number 1, drop down the 5. Okay, now multiply these two together and write it underneath the next coefficient. So 5 times negative 2 is negative 10. Write it under the 5 and then repeat. 5 plus negative 10 is negative 5. Negative 5 times negative 2 is positive 10. Add these. Negative 7 plus 10 is 3. 3 times negative 2 is negative 6. 7 plus negative 6 is 1. 1 times negative 2 is negative 2. 5 plus negative 2 is 3. 3 times negative 2 is negative 6. Negative 4 plus negative 6 is negative 10. Negative 10 times negative 2 is 20. Negative 1 plus 20 is 19. My remainder is 19. Now, when I did synthetic division, I was asked to actually divide, and so I was able to use this and turn this into a whole other polynomial, with that being part of my remainder and part of my answer. But that's not what we're doing here. This is just remainder theorem, and all I have to do is just that, find the remainder, and it's 19. Great. Write a polynomial with integer coefficients using these given zeros. All right, I'm going to approach this kind of like in a weird step-by-step basis. Thing number one, I'm given 2 roots. That doesn't mean anything. I actually have 3, and you might be thinking, no, there's 2 there. There's a little thing called the conjugate rule that says if you have something in this form as a root, you must also have something in this form as a root. And you might be thinking, well, we don't have anything that looks like a plus bi. Yes, we do. That's a plus bi because it's a complex number that can be written out as 0 plus 2i, which means 0 minus 2i also has to be an answer. So I have to throw negative 2i in there. Okay, so that's thing number one that you have to be careful of. The problem is kind of incomplete, and you have to fill in the blanks yourself. Those are my 3 roots. Now, another thing that I want to look at is reminding ourselves what zero product property says. If I have something that looks like this, and I'm just picking random numbers, if I have something that looks like that, I know that my answers are going to be x. Why did I pick 0? Let's make it a 10. X equals 5, and x also equals negative 10. So if I get the parentheses, then I know the roots. Well, now I have the roots, so I should be able to do this. Throw opposite symbols in front of these and throw them in the parentheses to get a similar idea. So what I'm going to do is I'm going to write out x minus 4/5, x minus 2i, and x plus 2i. Now what I have to do is I have to simplify this out. So I'm going to use my eyes over here, knowing very well that things are probably going to go away, things will disappear, but I'm going to multiply this out. So I haven't touched x minus 4/5 yet. Not yet. I will. But if I FOIL this out, wonderful things are going to happen. X times x is x squared. X times 2i is 2ix. Negative 2 times x is negative 2ix. How about that? Negative 2i plus 2i, or times positive 2i rather, is going to be negative 4i squared. Now, before you're like, oh, this is a nightmare. No, it's not. These guys go away. And what's also nicer is I squared. Remember, I squared is the same as negative 1. So negative 4i squared is the same as positive 4 because it's negative 4 times negative 1. So let me write this out as x equals 4, not x equals, x minus 4/5 and x squared plus 4. Now let's factor, that's supposed to be a parentheses. Let's factor this out. X times x squared is x cubed. X times 4 is 4x. Negative 4/5 x is negative 4/5 x squared is negative 4/5 x squared. And negative 4/5 times 4 is negative 16/5. Now, before I call it a day, remember, this is all equal to 0. So this is all equal to 0. Before I call it a day, I'm supposed to have integer coefficients. So what I'm allowed to do is I'm allowed to multiply both sides by 5. Why am I doing that? To make these fractions no longer fractions. So by doing that, I now have a polynomial where I can have 5x cubed. Let's put it in order. 5 times negative 4/5 is going to be negative 4x squared. Okay, I'm doing this one. Plus 20x minus 16. That is a polynomial that, when set equal to 0, gives me zeros of 4/5 and 2i. And, oh yeah, by the way, negative 2i. State the number of complex zeros, the possible number of real and imaginary zeros, and the possible rational zeros for each function or for this function right here. What a mess, what a mess, what a mess, what a mess. Well, let's start out with complex zeros first. What is a complex zero? Well, a complex number is a number in this form right here. Now, if I were to pretend that that b is gone, then my complex number is real. If I were to pretend that that a is gone, then my complex number is imaginary. So complex numbers could be real or it could be imaginary. According to the fundamental theorem of algebra, whatever your leading term's degree is the amount of complex zeros you're going to have. So in this case, we are going to have 5 complex zeros because this is a 5th degree polynomial. So that's part 1. Part 2 says if I'm going to find, let's actually jump to imaginary zeros before we do real. Part 2 says if I were to have an imaginary number, like a plus bi, I have to have its conjugate also floating around as my answer as well. So imaginary zeros, if you're going to have one, you must have the other. So I could have no imaginary zeros. I could have 2 imaginary zeros. I could have 4 imaginary zeros. So it's basically even numbers all the way up until you hit complex, but you're not allowed to go beyond it. So since my highest degree is 5, I start out with 4 and work my way down. Now what that means is since I could have 5 real numbers, I could also have 3 real numbers, and I could also have 1 real number. Okay, so whenever you're being asked to find your your real numbers, you start with the odds and work your way down from there. Now on to the nightmare scenario, the rational root theorem. Okay, the rational root theorem has me listing out every single possible root that is rational that I could have, and is an absolute god-awful nightmare. Okay, but this is what we do. We already have this written in order. I'm going to call you Q. It'll be nicer if I had a pen. I'm going to call you Q, and I'm going to call you P. Now, my rational roots are all the numbers in the form plus or minus P over Q, where P are all the possible factors of P, and Q are all the possible factors of Q. So what are my factors of P? 9, 3, and 1. What are all my factors of Q? 15, 5, 3, and 1. Now, what I'm going to do is I'm going to list out all 12 possible numbers in the form P over Q. Technically, it's 24 if I throw the plus or minus in there. So let's go in order. Plus or minus 9 over 15, 9 over 5, 9 over 3. We'll simplify these in a little bit. I'm going to forget my pluses or minuses. Don't want to do that. And 9 over 1. Now, I'm expecting repeats to take place. Okay, so if you're looking at this and saying, will we have 12 separate ones? Nope. When things simplify, we will have repeats and we'll get rid of the repeats. Okay, now let's do 3 over 15 plus or minus 3 over 15 plus or minus 3 over 5 plus or minus 3 over 3 plus or minus 3 over 1. Now let's do plus or minus 1 over 15 plus or minus 1 over 5 plus or minus 1 over 3 plus or minus 1 over 1, running out of space. All right, so let's write these all out and get rid of the repeats. Let's simplify while we're at it. Plus or minus 9 over 15 can be written out as 3/5. So we're done with you. Plus or minus 9 over 5 is simplified as much as it can be. Plus or minus 9 over 3 is 3. Plus or minus 9 over 1 is 9. Plus or minus 3/15 is 1/5. Plus or minus 3 over 5, I did already. Plus or minus 3 over 3 is 1. Plus or minus 3 over 1, I did already. Plus or minus 1 over 15. Plus or minus 1/5, I did already. Plus or minus 1/3. And plus or minus 1, I did already. So these are my options, all of them in all of their glory. Do I have to put them in order? Nah, I'm not going to, but I did it. That's the rational root theorem. I sprinkled in some fundamental theorem of algebra in here. A lot going on in this one little problem, but we did it, and I'm proud of you. Identify the points of discontinuity, the holes, the intercepts, and the horizontal asymptote, and the domain. Goodness gracious me. All right, well, lots to answer, so I have myself a quadratic over a quadratic, and the first thing I want to do is factor the quadratics. So I'm going to do just that. Two numbers that add up to -1, multiply out to -6 are going to be -3 and 2. So the numerator factors out to that. The denominator, two numbers that add up to -2 and multiply out to -8 are -4 and 2. Oh, look, two 2's. Just like at a ballet recital. What am I doing first? Point of discontinuity. A point of discontinuity are the x values that if you were to plug into this equation, the whole thing, all right, would make it undefined. So in other words, what numbers, if I were to plug into the bottom here, would give me a undefined equation? Well, if I were to plug in 4, and if I were to plug in -2, 4 would make this 4 minus 4, which makes that 0, which makes the whole thing 0, discontinuous. And if I were to plug in -2, same exact thing would happen. That is the zero product property in action. There's my points of discontinuity. A hole exists when you have a point of discontinuity existing in a parentheses. That's the exact same thing as you have there. So in this case, since I have an x plus 2 on the bottom and an x plus 2 on the top, my hole exists at -2. Okay, which means like if I were to graph this, there's not an asymptote happening. You just have a break in the graph. That's what a hole means. An intercept. Let's start out with the easy one, the y-intercept. And remember, you find the y-intercept by substituting 0 into your equation. So simply put, if I were to take f of 0 and plug in 0 for x, I would get 0 squared, which is 0, minus 0 minus 6, over 0 squared, which is 0 minus 2 times 0, which is 0 minus 8. And my y-intercept simplifies to negative 6 over negative 8, which is positive 3/4. That's my y-intercept. Now, the x-intercept is a little more involved. Okay, the x-intercept is what if I set my y, or my f of x, equal to 0. Okay, so let me not use red. I just used red. What color haven't I used? Black. X-intercept, I'm going to set my f of x equal to 0. So 0 equals x squared minus x minus 6 over x squared minus 2x minus 8. Now, what I'm going to do is I'm going to multiply both sides by this guy right here, which eliminates that entire thing. So now I'm left with x squared minus x minus 6. Let's not forget that if I wanted to use zero product property and factor this guy out, x squared minus x minus 6 is x minus 3 and x plus 2, which means my x-intercept is going to be positive 3 and negative 2. Oh, but wait. X can't be negative 2 because it's discontinuous there. So my only x-intercept is going to happen at 3. So again, my x-intercept looks like it should appear at 2 places, but it's not allowed to be negative 2 because negative 2 is where my line is discontinuous. Last but not least, let's get a nice little orange color going on here. Last but not least, my domain, let's get rid of the color palette. My domain, when graphing these things, is going to be everything but where this is discontinuous. So what I will say is my domain is going to be all real numbers, but x cannot equal 4 and x cannot equal negative 2. Where did I get 4 and negative 2 from? Well, that's where my graph was discontinuous. So my domain says I'm allowed to plug in all real numbers except for 4 and negative 2. So lots going on there. But there you have it. I think I covered everything. Solve a big fraction with a polynomial minus another fraction with a polynomial equals another fraction. Look at that, with the polynomial. There's a little rule that says, and this is how we're going to start off. If you have a over, I don't know, smiley face. This is me drawing a smiley face. And you have b equals a smiley face, that at the end of the day, the smiley faces cancel each other out and you have a equals b. Now, why am I bringing that up for a problem like this? Well, these guys are the same. If I can find a way to make this guy look like this guy and combine these fractions, then I will have a fraction equaling a fraction where the denominators are the same and therefore the numerators will be the same. So this is what I'm going to do. In order to make these fractions have all the same denominator, I'm going to factor that guy, which also factors that guy, and hope that n plus 1 is one of the factors. I have a feeling it will be. So I have 4 over n plus 1. Okay? I'll leave that right there. Minus 1 over n squared plus 7n plus 6. I need to come up with two numbers that add up to 7 and multiply out to 6. Well, 1 and 6 should do it. So there's my n plus 1, and there's my n plus 6. That's going to be equal to 3 over the same exact thing, n plus 1 plus n plus 6. My goal here is to have the same exact denominator. In order for me to turn this fraction into a denominator with n plus 1 and n plus 6, let me throw parentheses around them even though it's not necessary. And I'm going to multiply the numerator and the denominator by n plus 6. What that'll allow me is to have the same exact denominator all the way throughout. Okay, so now I can do this. If I were to distribute 4 to n plus 6 in parentheses, that gives me 4n. 4 times 6 is 24. And now that these are the same denominator, I can combine the denominators, giving me this guy, and minus 1 comes along for the ride. That's going to equal 3 over n plus 1, in parentheses, n plus 6. While I'm here, what I'm going to quick do is I'm going to quick erase 24 minus 1 and make that 23, just so that I don't have to rewrite so much. And since these two denominators are the same, okay, I don't need them anymore. So that leaves me with 4n plus 23 equals 3. My next step is to subtract 23 from both sides. Minus 23, cross you out. Let me write it up here where I have a little bit more space. 4n equals negative 20. Divide both sides by 5. 4. This is me just accidentally thinking ahead, because when I do that, I get negative 5. And n equals negative 5. That's my guy, that's my solution, and I'm done. Solve x squared minus 4x minus 32's got to be greater than 0. Okay, this is an inequality. Now, I don't know exactly what this picture is going to look like, but let's just take some arbitrary thing. I know this opens upward. And let's just say that my picture looks like this. Okay, let's just make believe. Who knows what this looks like? What I care about are the x values that are going to make my value positive, which means I only care about everything from here on over, and I only care about everything from here on over, because whatever of these x values that I plug in is going to give me a positive y value. I know I said y, I probably shouldn't have said y. It's just going to give me a positive value in general. I don't want any of these. So what I'm going to do is I'm going to find out what these are. And I can do that by factoring things out and using the zero product property, because I care about a zero. So step number 1, let me get rid of you, let me get rid of you, let me get rid of you, let me get rid of you. Step number 1 is I'm going to factor this out. That should be pretty simple. Two numbers that add up to negative 4 multiply out to negative 32. One's going to be positive, one's going to be negative. Looks like 8 and 4 will do it. The 8's got to be negative, because negative 8 plus 4 adds up to negative 4, not the other way around. So now that I have this, I have a slightly better picture where I know my zeros are going to be negative 4. And I'm going to say that. My zeros are going to be negative 4 using the zero product property. It's going to be the opposite of that, and it's going to be positive 8. So now that I have a little bit more clarity, I can draw myself a slightly better picture, a picture that looks like this, where this guy right here is negative 4, this guy right here is 8, and I only care about these parts right here. Now, I knew that my picture would look like this. So technically I have my answer, but let's just say I didn't know. Let's just say I didn't know what the picture looks like. This is a backup plan. I'm going to create what's called a sign graph. Now, this is very calculus-y. You're going to do this a lot in calculus. So I'm doing this too to prepare you, because this is a pre-calc class and its job is to prepare you for calculus. Let's just say I didn't know what the picture looked like. Okay, what I want to do is I want to pick numbers that are not negative 4 and are not 8 and live in these 3 areas that I care about. I care about everything less than negative 4. I care about everything between negative 4 and 8. And I care about everything greater than 8. And what I'm going to do is I'm going to plug it into the original problem and see if by plugging it in gives me a positive or negative value. If it's positive, that means I want it. If it's negative, that means I don't. So I'm going to pick 3 numbers that live in these 3 areas. So let me pick negative 10, let me pick 0, and let me pick positive 10. Why did I pick those numbers? Because they're easy to deal with. What I'm going to do is I'm going to pick negative 10 I'm going to pick 0, and I'm going to pick positive 10 and see if it gives me a positive or a negative value when I plug it in. So I'll say f of, even though there's no f in the original problem. I already said why. Why not commit to it? If I plug in negative 10, I'm going to get 100 plus 40 minus 32. Doing a little mental math, but without doing too much, 100 plus 40 minus 32 is definitely going to be positive. So as we can see from the picture that I drew, this gives me exactly what I want. This is positive. I'm happy. If I plug in 0, I get 0 minus 32. That's definitely going to be negative. Okay, so I don't want this interval. And if I plug in 10, I get 100 minus 40 minus 32, which is 38 or something like that, or 28 or something like that. It doesn't really matter. It's positive. So this area checks out. So again, I made believe just for a few seconds that I didn't know what the picture looks like. Even though I know this opens upward, I'm still make-believing because I love make-believing. It's fun. All right. And I found out that by plugging in specific numbers and by finding out my zeros, I was able to determine if those numbers would definitely be positive, definitely be negative, and definitely positive. And since these were greater than, the original problem is greater than, I only want the positive ones. So the positive x values that I care about, the x's that I definitely want, are everything less than negative 4 and everything greater than 8. Okay, because everything in between negative 4 and 8 is negative. Don't want that. Why doesn't it equal negative 4? Why doesn't it equal 8? Well, if I plug in negative 4, I get 0, which is neither positive nor negative. So this is my answer. Those are all the possible x values that when plugged into the original problem give me something greater than 0. Again, this is very calculus-y, so understand this process. This will not go away anytime soon. Ooh, we've got ourselves solving rational inequalities. The first thing you're going to want to do is remove everything from the right side, move it to the left. So let's do that. I have negative 3 over x plus 7, and I'm going to wave my hands a little bit. I would add 4 over x plus 8 to both sides, so that will look like that, and now I have that. What I'm actually going to do is I'm going to scooch that over a little bit because you'll see what happens next. And I'm going to turn that negative 3 into its own negative 3. So let's clean that up. Let's scooch that over because my next step is to combine these fractions. Now, when you combine fractions of any kind through addition, you need a greatest common denominator, or maybe a least common denominator. In this case, the least common denominator is going to be x plus 7, x plus 8. So I'm going to multiply u by x plus 7 over x plus 7, and I'm going to multiply u by x plus 8 over x plus 8, like so. All right. Now I'm going to use distributive property. That gets me negative 3x minus 24. I'm going to use distributive property again. That gets me 4x, how convenient, plus 28. And now all of this is going to be over x plus 8 times x plus 7. And it's still less than or equal to x, or 0. When I combine all of these, negative 3x and 4x combine to make x, negative 24 and 28 combine to make 4, and I have x plus 4 over x plus 8 times x plus 7. Now I have 3 factory-looking things here, and in fact, I'm going to put that in parentheses to really emphasize that point. What I need to do is very similar to when I was having polynomial inequalities. I'm going to create what's called a sign graph, S-I-G-N. And in this case, I care about when things happen at what would create zeros. So I care about things happening at negative 4, I care about things happening at -7, so I'm all out of order. So technically -4 would happen here. I care about things happening at -7, and I care about things happening at -8. Okay, so I need to pick numbers that are not equal to these numbers but live in specific intervals. So for example, I need to pick numbers like -10. This is going to be a pain in the butt. -7.5. How about negative regular 5 and 0? And I need to see which of these numbers are going to be less than or equal to 0. So I can actually use this equation right here. If I plug in -10, if I plug in -7.5, if I plug in -5, and if I plug in 0. Okay, let's see what happens. I'm going to try to do most of these mentally so as not to really kill my brain here. But this will be -10 plus 4, which is going to be -6. -10 plus 8 is going to be -2. -10 plus 7 is going to be -3. Okay, negative over a negative times a negative is going to be negative over a positive, which makes this negative. So this makes me happy. I want this. 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 Now let's plug in -7.5. If I plug in -7.5 on the top, that gets me a negative. Let's do it this way because I really don't care about what numbers I get. I care about what kind of numbers I get. So I get a negative if I plug in -7.5. If I plug in -7.5 here, I get a positive. And if I plug in -7.5 here, I get a negative. So this negative over negative is going to be positive, which means I don't want the numbers between -8 and -7. If I plug in -5, running out of space, if I plug in -5, -5 plus 4 is going to be a negative number. -5 plus 8 is going to be a positive number. And -5 plus 7 is going to be a positive number. So negative over positive times positive is negative. So you're good. And if I were to plug in a number like 0, I would get positive over positive times positive. Positives all around. So that's positive. So that's no good. Now, before I create my intervals, before I say what's what, okay, one of the things that I also have to keep in mind is numbers like 8 and numbers like not 8, but -8 and numbers like -7 are not allowed. Why? Because that would make this undefined. So the numbers that I want are everything less than -8, but I'm not allowed to include -8. So x is less than -8. I also care about the numbers between -7 and -4. So I can say that -7, I'm not allowed to include it, is less than x, which is less than or equal to -4. That's my guy. If you have a teacher that wants you to write it out in this type of notation, like the union notation, you could write it out as -infinity goes to -8 with the parentheses, and, union means and, -7 to -4 with a bracket because we are allowed to include -4. There's nothing here that says we can't plug in -4. If I were to plug in -4, I get 0, and I'm allowed to get 0, and this won't be undefined. So that's my guy right there. Ooh, it's a doozy. But that does it for this section. All right, we are going to graph this exponential function right here, y equals half times 5 to the x power. Now, there's little tricks that you could use to graph exponential functions, but what I'm going to do is I'm going to make myself what's supposed to be a t-chart. Looks terrible, but what I'm going to do is I'm going to substitute in 0 for x, 1 for x, figure out a pattern before I even bother with these guys right here. Now I'm going to plug in 0 for x. I'm going to do that a little bit mentally, but also write a little bit off to the right. So if I plug in 0 for x, that's going to be 1/2 times 5 to the 0th. Anything to the 0th power is 1. So that gets me half of 1, which is a half. So plugging in 0 gets me a half. Now, a trick that we can learn here is whenever you plug in 0, whatever number is being multiplied to our power, that's going to be your y-intercept. Fun fact. All right. As long as you're not adding anything over here. Don't want to screw that up. Now, let's plug in 1 and see what happens. Okay? If I were to plug in 1 for x, 1/2 is still lingering. 5 to the first power is just 5. Okay? That ends up with 5 over 2, which is 2.5. Now, the pattern that we're figuring out, right, is as x goes up by 1, my fraction, or whatever number this is going to be multiplied by 5. So the next guy is going to be 25 over 2, because as x increases, y gets larger by multiplying it by 5. 5 over 2 times 5 is 25 over 2. In reverse, as I lose an x value of 1, this guy divides by 5. So if I were to take 1/2 and divide it by 5, that's the same thing as multiplying it by a 1/5. That gives me a 1/10. So that allows me to draw a few points. So -1 is basically 0. I mean, 1/10 is close enough to 0. 0 1/2. 1 2/5 is 2.5. 25 over 2 is 12.5. And if I were to multiply by 5, I'd definitely run out of space. Okay? But what we see is as this guy goes to the right, it gets super big, super fast. As it goes to the left, it gets super small. And this is just going to keep getting smaller and smaller and smaller and get awfully close to 0, but never technically hitting 0. So this is an example of exponential growth. If I knew how to draw pictures correctly, this is going to look absolutely terrible. I'm going to start that over, pretend that didn't happen. Look at it. Look at it. Looks like a hair. Scooch it over there. Let's try one more time. Still staring at me. Let's make it nice, and yeah, maybe if I kind of do like a sketch way of doing this, nice and flat, gets bigger, gets bigger, gets bigger, gets much bigger, much bigger, much bigger, much bigger. And even though that still looks god-awful, that's what it is. Exponential growth. Don't judge me on my artistic talent, judge me on my brain, which is slightly above average. But there you have it. We need to solve this exponential equation right here. Now, eventually you're going to learn something called logarithmic functions that would do the job for you, but that's not what we're going to do here. There's a little rule that says if you have, let's use 6, just for fun, 6 to the a equals 6 to the b. Well, since these 6's are the same, then we can legally say that a equals b. These exponents are the same. Now let's just leave that over there. Let's just leave that over there. Why am I saying that? Well, if I can make 36 6 to the something power, like, I don't know, 6 squared, then I'm in great shape. 36 is 6 squared. This stays 6 to the negative 3v minus 2. And since these 6's are the same, then these two are the same, and I can set them equal to each other. So negative 3v minus 2 equals positive 2. And now it's just an Algebra 1 problem. Add 2, cross you out. Negative 3v equals 4. Divide both sides by negative 3, like that. And 4 over negative 3 is the same as negative 4 over 3. So if you can make the bases the same, you're in great shape. If you can't, you're going to learn something called logs that'll do the job for you. This is going to be terrible, but this is solving an equation where you have variables in your exponents. So what we can do is we could try to turn this into just one thing looking equal to one thing. So what I'll do is I will rewrite this guy as 16 over 16 to the negative 1 to the x. Now, what did I do? If you have 1 over 16, if 16 is in the denominator, move it to the top part and make it to the negative 1. That's going to equal 1/4, which, tell you what, while I'm at it, I might be doing a bit too much here, but while I'm at it, I'm going to turn 1/4 into 4 to the negative 1. For the same exact reasons that I did that over here. That's all the 2 to the 2 minus 2x. Too many 2's in this problem. Now, if I wanted to, if I have a power to a power, you multiply the exponents. So this becomes 16 over 16 negative 1 times x to the negative x. Okay? Equals, same rules apply here. Okay, if I multiply negative 1 to this whole thing, I use distributive property. So this becomes 4 to the negative 2 plus 2x. Now, I'm going to put an imaginary 1 here. Why? If I have 16 to the stuff over 16 to the stuff, when it's division, you subtract the exponents. So invisible 1 minus negative x can make this rewrite as 16 to the 1 plus x. That is still going to be equal to, nothing changes here, not yet, 4 to the negative 2 plus 2x. Now, in a previous problem, I had a very similar situation going on here where if I can take that 16 and make it 4 to this stuff, I'm in great shape. So I'm going to do that. 16 is 4 squared. I still have 1 plus x over there, and this is still 4 to the negative 2 plus 2x. Just like I did over here, I'm going to distribute that 2 through multiplication to 1 plus x, so I now have 4 to the 2 plus 2x equals 4 to the negative 2 plus 2x. Now that I have the same base, if these are the same, then I can say that these are the same. Now, at this point, you should be saying, uh-oh. I have a 2x on the left. I have a 2x on the right. They go away. That leaves me with 2 equals negative 2. Does 2 equal negative 2? No. So what's my answer? There is no answer. All of that to find out that there's no solution. Ah, what a rip. But I had a great time doing it. Rewrite in exponential form. We have a log. Generally speaking, if I give you something in this form, log base b, and let me get all colorful, log base b of a equals x. Oh, so many colors. If I give you something that looks like this, I'm allowed to rewrite this as b, so the base is still the base, x for exponent, b to the x equals a. So what I need to do here is I need to take a look at this guy and compare this to that guy and say, all right, well, b is my 7, 49 is my a, and 2 is my x, which I made purple. I'm going to stop with the colors because it's taking me way too long. I can write that as b to the x, so 7 squared equals a, which I called 49. So fun fact, this is a true statement, making that a true statement. But this is how I rewrite something that's in logarithmic form into exponential form. No solving, no completing anything, nothing to simplify. That's just me changing log into exponential. That's it. All right, my job is to evaluate log base 4 of 1 over 64. Now, if you look at a calculator, you're not going to find log base 4. However, what we know how to do is we know that I can rewrite a log into exponential form. So if I give you something in the form log base b of a equals x, I can rewrite that as b to the x equals a. Now, if you look at this, you might be thinking, well, that is not the same as that because it's not equal to x. So let's make it equal to x. Why not? I'll label you b. 1 over 64 is my a. So I can rewrite this as b, which is 4, 4 to the x equals 1 over 64. Now, right now, there's not much I can do, but I do know this. I do know that if I can make these guys the same exact base, life is a lot easier. So if I write this as 1 over 4 to the third, because 4 times 4 times 4 is 64, and if I take that 4 to the third that's in a denominator, move it up into the numerator, and make the exponent negative, I now have two things that have the same exact base. If 4 equals 4, if the bases are the same, then these exponents are the same, and I know that x equals negative 3. So, what is log base 4 of 1 over 64? Negative 3. I probably shouldn't have circled this guy because there was no x in the original problem, but the answer is negative 3. So there you go. Find the inverse function of y equals log base 5 of negative 2x. All right, whenever you're trying to find the inverse, the first thing that you do is take the x and the y and swap it. So I'm going to make this x equals log base 5 of negative 2y. What I need to do is I need to solve for my new y, but this is an absolute mess. I mean, y lives inside of a log inside of a parentheses. This is terrible. So let's turn this into exponential form. Okay, so exponential form, I had 2 videos where I do this. So this will become 5 to the x equals negative 2y. And my job is to now solve for my new y. So I divide both sides by negative 2, both sides by negative 2. Cleaning that up will make this look like, let me move this y over here. Y equals 5 to the x over, let's put that negative out there, over 2. And now that y is all by itself, I can throw the inverse symbol to it, and I have my inverse function. Y to the negative 1 equals negative 5 to the x over 2. You might be able to write this out. Some teachers might want you to write this out as this so it looks more like exponential growth or something like that. Some teachers might want you to say, all right, well, bring that 2 out, make it negative a half times 5 to the x. Either way is fine. They're exactly the same. They're exactly the same. It all depends on your teacher. Condense into a single logarithm. All right, well, I have 2 logs being connected by addition. The first thing that you always want to do is if you have a number living in front of a log, like this one right here, there is a rule that you can take that number and make it the exponent inside the log. So I can rewrite this as log of y to the 5th. I like to put parentheses around there. It just looks better. Okay, log of x, nothing happened there. Nothing at all. When you add 2 logs, you multiply the insides. So log of x plus log of y to the 5th is going to be log of x times y to the 5th. And there you have it. If I were to subtract these logs, you would divide, but in this case, I added these logs. So x times y to the 5th is x y to the fifth. X has its own person. Y has that 5 attached. It is now a single logarithm. Fun, 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 fun. Condense into a single logarithm. All right. First thing that you want to do is if you notice any numbers living in front of a log, which I have here, and I also have here, you're going to want to take those and make those exponents for the things living inside the log. So I'm going to make this first guy log of, and I like to put parentheses, it just looks better, log of u to the 6 minus log of v to the 6. If I were to add these, I'd multiply. However, since I'm subtracting logs, you divide, and you always go in the order that you're given. So since this is a negative, this becomes my denominator, and since this log is positive, it's my numerator. And so by putting these together, I have log base 10, invisible base 10, of u to the 6 over v to the 6, and I am done. Okay, nothing more to do. Now, some teachers might be like, well, I noticed that there's a 6 in common with each of these, so if I wanted to, I can write this out as log of u over v, and since both of them have a 6, I can throw a 6 right there. You're allowed to do that. To me, it's not necessary, but don't be surprised if you have a teacher that asks you to do that. It's perfectly possible, perfectly fine. But yeah, either one of these work just fine for me. My job here is to expand this log into multiple logarithms if that's what I'm going to get. And so the first thing that I'm going to do is I'm going to rewrite the cube root of x as an exponent of not cube root. So the cube root can be written like this. And I always like putting things in parentheses, especially logs in parentheses, x to the 1/3 power. If I have a log and I'm supposed to expand it, make it look larger, what I can do is if you have an exponent living inside your log, bring it out front. So this now becomes 1/3 log of x. And believe it or not, that's it. There's not much more I can do with this unless I want to rewrite it all over 3, but that's kind of pointless. I mean, expand means take everything on the inside and rip it out so there's nothing but x's and nothing else. So that's what I did. That's all I have to do. I'm done. All right, my job is to expand log parentheses u times v close parentheses to the 6. So I might have several logs going on. First thing that I notice is I have an exponent living right here. My exponent is attached to the whole thing, okay, and not just u and not just v. So the first thing that I want to do is if I'm supposed to expand a log and I see an exponent that applies to everything, bring it out front. So now I have 6 log u times v. Now I'm going to throw this in brackets just to demonstrate what happens next. If I'm multiplying stuff inside a log, what I do is I split it up through addition. So 6 is still living out here. Log u times v becomes log u plus log v. That 6 that's living out there gets applied to both of these. So this is now 6 log u plus 6 log v. And this is further stressing the point, stressing the fact that that 6 applied to both u and v and not just one, and that's why the 6 lives in front of the u and lives in front of the v. All right? So now that I have just a u and just a v, everything's ripped apart. That's me expanding this guy right here. Dunzo. All right, my job is to solve 10 to the b equals 74. Now, back in the day, if this number was something like 100 or 1,000, we could just make this 10 to the number donezo. But we can't do that here. If it's 10 to the b equals some number that you can't make this equal 10, we have to use logarithms. So what we're going to do is we are going to rewrite this as log. My base up here is my base down here. Whatever it equals goes inside the log, and my exponent up here is what it equals down here. Now, any log that you see in a calculator, if you go to a calculator and you see the log button, that automatically means log base 10. So what you do is you go to a calculator, you type out log of 75, and you'll find out that you get 1.869. Is there more? 2, 3, blah, 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 blah. Now, why such an ugly number? Well, first off, 10 to the first power is 10. 10 to the second power is 100. So my number is going to be something close to 2, but not quite 2. And it's going to be a terrible mess because I don't know what 10 to the what power is 74. So it's going to be something kind of close to 2. And in this case, it's that guy right there. All right, so that's how you use logs to solve an exponential function. All right, looks like we have to solve ourselves this terrible looking exponential equation. First thing we should do is just get rid of that 4 that's just lingering on the left. So subtract 4 from both sides. That gets us 17 to the k minus 10 equals 62. Now, normally when we see 17 to the stuff equals a number, we want to try to make this number 17 also to the stuff, but 62 ain't happening here with 17. So we're going to have to turn this into a logarithmic function and take it from there. So in order to turn this into a log, we make this log. Our base is also our base here. Whatever it equals is going to be inside the log, and that's going to equal k minus 10. Now here's the tough part. Whenever it just says log, that's log base 10. We throw it into our calculator, call it a day. But that's not going to happen here. This requires the change of base formula. Now the change of base formula says if you have something log base b of a, you can turn that into log base 10 or log base whatever you want of a over log base, same thing, of b, right? So log base 10 of a, you could also use ln of a over ln of b, but, you know, that's what I have here. So I'm going to write this out as log of 62 over log of 17 equals k minus 10. I have no, now I'm going to write this over here where I have a little bit more space, split that into 2 parts. Let's find out what log 62 is. I have no idea. All right, log 62 is 1.79239, so I'll make that 4. Log base 17, according to the internet, is 1.23044, and that's still going to equal k minus 10. Now what I have to do is I have to divide 1.7924. I'm going to divide that by, and I'm actually literally doing this on a computer right now, 1.2304. That ends up being 1.4567. So let me write that out, 1.45675. So I'll actually make that 68 equals k minus 10. Now that I have something a little bit more manageable, I can add 10 to both sides. I don't need a calculator for this one. That gets me 11.4568 equals k. And that's my answer. Not very pleasant, this one. Not very pleasant at all, but that's how it's done. Okay, log base 7 of x plus 4 minus log base 7 of x equals 3. I see two log base 7 stacked up right next to each other, so why don't I combine them? If you have log base something minus log base something, you divide the inside, so this guy becomes log base 7 of x plus 4 over x equals 3. Now, I can't throw this into a calculator. I can't use the change of base formula because I can't find what the log base 10 of x's are. So what I need to do is rewrite this into exponential form. So my base is going to be my base here. Whatever it equals is going to be my exponent, and that's going to equal x plus 4 over x. 7 to the third power, that's a good one. 7 times 7 is 49. Let's not pretend that I'm plugging this into a calculator. 343, I knew that, is going to equal x plus 4 over x. Let's multiply both sides by x. So I now get 343x. So that happens, we get, you cross out x plus 4. So I guess the best thing to do is subtract x from both sides. Subtract x from both sides. That crosses out. That gets us 342x equals 4. Divide both sides by 342. Divide both sides by 342. That's gotta simplify to something. 342, 86? 1 over 86? Maybe? Well, my phone just dinged, so I'll take that as a sign. Let's keep it. 1 over 86, that's my answer. That was a nightmare, but a lot of fun. All right, time to solve. Negative 3 e to the stuff minus 7 equals negative 91. Fun little fact, I'm sure you already knew this, but log base e of x is the same thing as ln of x. Will that pop up here? I don't know, but yeah, probably it will. Let's add 7 to both sides. Let's scooch this over here. Negative 3 e to the stuff is now going to equal negative 84. Yeah. Now, not much I can do here. Oh, you know what I can do? I can divide both sides by negative 3. Let's do that. Let's divide both sides by negative 3. So now I have e to the 5a plus 1 equals positive 30. Nope. 28. 28. All right. That's a close one. Now, I can't do anything when I have variables living inside the absolute, or living inside an exponent. So what I can do is rewrite this as a log. Now, keeping in mind this happens, so what I could do is I could write out log base e, but I know log base e is the same as ln. So I have ln of 28 is going to equal 5a plus 1. ln of 28, according to the internet, which I'm using right now, currently is 3.3322. So this becomes 3.3322 equals 5a plus 1. Let's subtract 1. Let's subtract 1. And I now have 3.3322 equals 5a. Divide both sides by 5. Divide both sides by 5. And we're looking at something around a half. 2.3322 divided by 5, according to the internet, is 0.5. 0.46644. That's what A is going to be. Delightful. Oh, stupendous. Wonderful. Grand. Gross. All right, my job is to solve ln of 5 minus ln of stuff equals ln of 33. Let's do this. Let's shove. Oh, no, I have a better idea. I have a wonderful idea. Let's connect these two ln's. Remember, ln is log base e, so ln follows all of the log rules. If I have a log minus a log, I subtract things in that order. So this guy becomes ln of 5 over 4 minus 4x. That's going to equal ln of 33. Now I have to be careful how I word this. What I can do is to make both of these ln's go away, I could take e to the of both sides. Why am I doing that? Well, e to the ln of stuff is just stuff. So e to the ln of 33 is just 33. I can multiply both sides by that 4 minus 4x, which is what I'm going to do. Multiply both sides by 4 minus 4x. This crosses out, leaving you with just a 5 on the left. Distribute here. 33 times 4 is going to be 132 minus 132x. Subtract 132, subtract 132, and 5 minus 132 is negative 127 equals negative 132x. Divide both sides by negative 132. Divide both sides by negative 132. Negative over a negative is a positive. And I'm pretty sure these guys don't simplify in any way, so I'm not even going to try. That's my guy. That's my answer. Fun, fun, fun. Jasmine invests $2,658 in a retirement account with a fixed annual interest rate of 9% compounded continuously. So this will require the continuously compounded interest formula, which is the total amount is going to equal your principal times e to the rate times time, also known as PERT, which is a type of shampoo. Now you know. So let's label things. You're my principal. You're what I start out with. 9% is my rate, but I'm going to write it out as a percent. So 9% is not a percent. As a decimal is 0.09. My t is going to be 15. And now it's just a matter of me putting it all together and throwing it into a calculator. So a is going to equal 2,658 times e to the 0.09 times 15th power. I'm going to move my mouse to the left and pretend that I'm not about to plug all this into a calculator and act as if I'm doing it in my head. And you get 10,253.037, so I'll do 04, which means $10,253.04. Now, if that seems like a lot of money, it's because it is. And it's because your rate is 9%. That is an unreasonably high number, but that's how you do it. And that's what we got. So we're done. Ah, yes, the unit circle. Not much is more important in pre-calculus than the good old unit circle. Look at it. It's a circle, and there's units on it, and there's points on it, and there's pies and square roots and degrees, and you're like, what the heck, sir, does all of this mean? Teach me, oh wise internet guy. Well, here I am. But in order for us to understand the unit circle and whatever the heck it means, we need to understand two specific triangles, and here they are. Triangle number uno is the 45, 45, 90 degree triangle. Of course, named after its angles, 45 degrees, and this right angle here. It's also called a right isosceles, but, who cares? What matters about this is if this is a right isosceles triangle, these two guys are the same. So we'll call them A. Now, we could use Pythagorean theorem to find out what the hypotenuse is, but if it's 45, 45, 90, there's a shortcut. Whatever these small legs are, you're just going to take the square root and multiply the square root of 2 to that leg. So if this was 5, that would be 5 root 2. If this was 8, then that would be 8 root 2. That's your 45, 45, 90 triangle. Now, the other guy is the 30, 60, 90 triangle. Of course, named after its 30, 60, and 90 degree angles. Okay, the smallest side over here, B, is going to live in between your 60 degrees and 90 degrees. This is fun. If this is B, then your hypotenuse is always going to be 2 times the smallest leg. The second leg, the in-between side, is going to be whatever the smallest side is times the square root of 3. So if this was 8, that would be 8 root 3, and that would be 16. So these special triangles help us figure out specific measurements in this guy back here, the unit circle. Now let's try to take 2 examples and try to understand where these measurements, these numbers are coming from. Let's take this line right here that I'm drawing in blue. Okay? Now, if I wanted to, I can make this look like a right triangle right there. So let me redraw that. Okay, what do I know? Well, I know that this guy right here is going to be 30 degrees. I know that this guy right here is going to be a right angle, which means this guy right here is going to be 60 degrees. Do I know any lengths? Sure I do. In every single example in the unit circle, my hypotenuse is going to be 1. Where did I get that number? 1, 1, 1, negative 1. And negative 1, which means if I were to take this length right here and spin it around, the radius of my unit circle is going to remain 1. So in this case, my hypotenuse is going to be 1. This is a 30, 60, 90 right triangle. Now, normally we view this as, all right, well, whatever the smallest side is, my hypotenuse is going to be 2 times that. Let's work backwards. If the hypotenuse is going to be 2 times my shortest side, then my shortest side is going to be 1/2 of my hypotenuse. All right, I can handle that. And if I now know that my hypotenuse is 1, my shortest side is 1/2, then this guy is going to be 1/2 times a third. Well, that looks kind of sloppy, doesn't it? It does. Thank you, whoever said that. So 1/2 times a third can be written out as 1/3 over 2. So this guy is 1/2. That guy is 1/3 over 2. Now, if I wanted to, I could write that as the point where if this is going right 1/3 over 2, and that's going up 1/2, that becomes the point root 3 over 2, not 1/3 over 2, I apologize, 1/2. Okay, let's look at another example. Let's look at an example, let's say, let me get a different color. Let's get my favorite color, green, and look at this guy here. Okay. Now, if I wanted to, I can turn this guy into a right triangle like so. So let me draw that out. What do I know? I know that my hypotenuse comes from the radius of the unit circle, which is 1. I know that if I'm using this guy, it's telling me right here that the angle is 225. Well, what does that mean? 225 starting from this guy spun around means that if I were to cut out 180 of it and only focus on the degrees from 180 degrees to 225, that gives me a right here 45 degree angle. Okay? Which means you're 45 degrees. If I created a perpendicular line, you're 90. And I have myself a 45 degree angle, 90, 45, 45, 90. This is 1. Now, this is where the math gets a little weird. If this is 1, we know that if the shortest side was like 15, we would multiply root 2 to get my hypotenuse. So in order to go backwards, I have to take 1 and divide 1 by root 2. Now, we know that it's completely against the law to divide by root 2. So we rationalize it by multiplying the top and the bottom by root 2. This gives us root 2 in the numerator. Root 2 times root 2 is root 2 squared, which is regular 2. So 1 divided by root 2 gives me root 2 over 2. And since these are exactly the same, root 2 over 2. So if I take it back over here, this length is root 2 over 2. This length is root 2 over 2, that length right there. Now, there's negatives all over the place. Why? Well, in order for me to create a point in the third quadrant, I go left root 2 over 2, down root 2 over 2, and that gives me the point root 2 over 2 negative, root 2 over 2 negative again. Bada bing. So the unit circle comes from the fact that we have special triangles. Okay, if we don't have to deal with triangles like these guys, like 0 and 1 and 1 and 0, then, we're good. And if we deal with specific angles, like if we were to deal with this 225, which we just did, we can view this as right triangles anyway. And then we just have to remember, 225 lives in the third quadrant. Or if I were to ask you to deal with 300, that lives in the fourth quadrant. So the point is positive, negative. Or if I were to ask you to deal with 120, then that lives in the second quadrant, negative, positive, so on and so forth. So that is the unit circle. At some point, you are going to learn and try to memorize a lot of these measurements, but this gives you just a nice little visual. Thank you so much for watching and enjoying with me. The end. Unit circle. Find the angle measure of this guy right here. Now, two things that we have to keep in mind. This is spinning at a clockwise fashion. If it's counterclockwise, it's a positive angle. But since this is a clockwise, it's one negative angle. Every solid rotation is 360. So if we start from here, we've got negative 360, negative 720, and then negative 180, which takes us to 900 right here. Now, this is 900, negative 900. Since this is 50, that makes this 40 degrees because of, right angles and stuff like that. So negative 900 minus another 40 gives me negative 940 degrees. So that's how you do it. Pretty simple. All right, if we want to convert radians into degrees, it's important to keep in mind that every 360 degrees is the same as 2 pi. So when converting radians into degrees, what we're going to do is we could multiply this whole thing by 360 over 2 pi, but instead we're going to multiply it by 180 over pi. What it allows us to do is it allows us to cancel out those pi's right there. We can simplify this part probably easier than just multiplying straight across. So 180 over 4 makes this a 1, and this becomes a 45. So 45 times 5 is 225 degrees. I hope that's right. I'm going to hit pause and double check. Yep, just check. Did it right. Of course I did it right. Of course I did it right. 225 degrees. It's a hot tamale. Like and subscribe. Convert into radians. Now, before we do this, it's important to remember that every 360 degrees is 2 pi radians. So what we're going to do here to convert this into radians is we are going to multiply by pi over 180. So let's do that, multiply by pi over 180. Why pi over 180? Well, because 2 pi over 360 does the same thing, so why not simplify? 510 divided by 180, I can get rid of the zeros. 51 over 18 simplifies to, I can do this, I can do this, I can do this, I can do this, I can do this. Let's write it out. 51 pi. I'm having a hard time figuring this out in my head. I know I could divide both of them by 3. So if I divide both of them by 3, that gives me 17 over 6. So that actually is it, 17 pi over 6. Yeah. So, and I'll put rad for radians. So, yeah, got a weird looking circle. We got a weird looking fraction. But that's our answer. I'm sticking to it. Find the reference angle for each. I'm going to draw a little picture over here. Okay, a reference angle is my angle. So whatever picture I'm given, it's the angle measured closest to the x-axis. So if I'm given an angle and it looks like that, that's my reference angle. If I'm given an angle and it looks like that, that's my reference angle, so on and so forth. So let's get rid of some of these things that I just drew, and let's figure out how we do this. Now, this is if I'm given angles measured less than 360 degrees or 2 pi, it's actually kind of easy, okay? If it's in quadrant 1 here, your angle is just your angle, okay? Now, if I'm measuring this in degrees, if you live in quadrant 2, it's going to be 180 minus the angle that you have, or it's going to be pi minus the angle that you have. That's how you find the reference angle. Okay, if you're in quadrant 3, it's flipped. It's going to be the angle that you have minus 180, or the angle that you have minus pi. And if you're living over here in quadrant 4, your reference angle is found by doing 360 degrees minus your angle, or it's found by doing 2 pi minus your angle. Now, before we get started, we need to find out what these guys are in terms of 360 or 2 pi. So what I need to do is I need to make sure that this guy here is written in between 0 and 2 pi. Similarly, I need to make sure that guy is written in between 0 and 360 degrees. If it's not, then I need to keep adding or subtracting these numbers right here until I live in that territory. Now, this is not in between 0 and 2 pi. Since this is negative, I'm going to add 2 pi until I live in that territory. So if I add 2 pi, that would be the same as me adding 24 over 12, which is 2 pi. When I do that, I get negative 23 pi over 12 pi, or just 12, or just 12. Even though I wrote pi, I said pi, it's just 12. Just 12. Just 12. Now I'm not in my range again, so I'm going to add 2 pi again. I'm going to add 24 pi over 12. Negative 23 plus 24 is 1. So negative 23 pi plus 24 is pi over 12. Now, if I want to turn that into a reference angle, I need to compare that to here. Anything in quadrant 1 is going to be less than half a pi or 90 degrees. This is less than half a pi, which means this is already my reference angle, praise God. So I'm done with that guy. Not so bad. Not so bad at all. 530 is not quite there. I'm going to subtract 360, that number, and end up with 170 degrees. Now I know that this is 180 degrees, which means 170 lives in quadrant 2. So to find the reference angle, I'm going to do 180 minus 170 and end up with 10 degrees. That's my reference angle right there. Now, other teachers might do this differently. If you're able to look at this and know exactly what quadrant that lives in your brain, great. And then what you do, if you knew that immediately right off the bat that was in quadrant 1, then you just add 2 pi, you add 2 pi again, and then you end up with that. Or if you knew right off the top of the head that after you spun this around a few times, you ended up in quadrant 2, then you could do 180 minus 530, realize you don't get what you want, and then repeat the process, and then you end up with 10. Awesome. That's not how I did it. I find this method a little bit simpler, so I'm sticking with it. Okay, might take a few steps longer, but I like it. Don't judge me. Reference angles. Find the value of the trig function. I have to find the tangent of theta, which is that angle right there. Whenever I'm dealing with right triangle trigonometry, I'm thinking SOHCAHTOA thoughts. Now, SOHCAHTOA is a cute little, acronym? I don't know, to help us remember what's what. Okay, sine stands for opposite over hypotenuse. Cosine stands for adjacent over hypotenuse. But I'm dealing with tangent. And the tangent of an angle is going to equal the opposite over its adjacent angle. Great. So if we're looking at theta right here, its opposite is 14. I can handle that. And its adjacent is, it's not there. So if it's not there, then we need to take a step aside and bring back our old friend, the Pythagorean theorem. So I will label you C, I will label you A, I will label you B, and the Pythagorean theorem says A squared plus B squared equals C squared. So A is 14, 14 squared, plus B squared equals 22 squared. 14 squared is 196. B squared is, I don't know. 22 squared is
It's 484.
484. Excuse me, 484. Now I have to get B squared all by itself. Let's subtract 196. Let's subtract 196. Ding says not my watch because I don't need a watch when I do math. Dinging, I think an angel just got its wings. 484 minus 196 is going to be 288. All right, so if I have B squared equals that, I have to square root everything. Don't need to worry about a plus or minus. And the square root of 288, we might have to go all the way over here and make ourselves a factor tree. It's been a while since we've done that, but we might have to rip this apart and make this look better. So I could do 2 and 144. Oh, this is manageable. 144 is 12 and 12. So if I wanted to take the square root of 288, I have 2 times 12 times 12. Circle a group of 12s, bring that out, 12 root 2, bingo, bango, bongo. So after all of that, we found out that our adjacent angle is 12 root 2. So going back here, I'm going to say adjacent is 12 root 2, which gives us 7 over 6 root 2. We know a rule that says, you're not allowed to have square roots on the bottom of a fraction. So we rationalize it by multiplying the top and the bottom by root 2 over root 2. That gives us 7 root 2 on the top over 6 times root 2 squared, which is 6 times 2, which is 7 root 2 over 12. Holy cow. So that was a pretty involved problem just to find a tangent. Okay, it involved Pythagorean theorem. It involved simplifying square roots. Lots to do there. Lots happened there, but we did it. We did it, as Dora said. We did it. Find the value of a trig function. We have ourselves a little bit of right triangle trigonometry. Right triangle trigonometry teaches us a little thing called SOHCAHTOA. SOHCAHTOA is clever wordplay, and it stands for the sine of an angle, in this case right there, equals its opposite over hypotenuse, the sine. The cosine equals the adjacent over the hypotenuse, and the tangent of an angle equals the opposite over adjacent. Well, we don't have anything for secant, but what do we know? We know that secant is the same as 1 over cosine. Sure is. So I don't care about you, and I don't care about you. I care about you. So if cosine theta is the adjacent over the hypotenuse, then secant theta is going to be the reciprocal of that, the hypotenuse over the adjacent side. Here's my theta, okay? The hypotenuse is given to us as 15, thank goodness. So secant theta is 15 over its adjacent side, which is 10 over pi. Now, in a previous problem that I have on the old YouTube, I had to do Pythagorean theorem. This problem is a lot friendlier. Didn't have to worry about that. But what I do have to worry about is the fact that we have a square root living in the denominator. You're not allowed to do that. Another thing, too, is this isn't really even simplified either. So maybe the first thing I should do is simplify this by dividing the top and the bottom by 5. Then what I'm going to do is multiply this by root 2 over root 2, and that rationalizes the function. So finally, we can say 3 times root 2 over root 2 times root 2, or root 2 squared, which is 2. Let me get out my calculator. 2 times 2 is 4. Secant theta is 3 root 2 over 4. That is the value of my secant theta. Done. Find cotangent of theta if cos theta equals 3 over 13. All right, so we've got ourselves some right triangle trigonometry going on here. And I know, according to SOHCAHTOA, I know that the cosine of an angle is going to be its adjacent side over its hypotenuse. Now, if you're looking at this and you're like, well, which one of these is going to be theta? It doesn't matter. It doesn't matter at all. We're just drawing pictures. So if my adjacent is going to be 3 and my hypotenuse is going to be 13, I can put this as my 3. I can put that as my 13. Bada bing. Now, according to this, tangent of theta is going to be my opposite over my adjacent side. And you might be thinking, well, why are you talking about tangent? We need cotangent. Well, because then cotangent of theta is going to equal the reciprocal, the adjacent side, over the opposite side. So according to my theta, the adjacent side is 3. My opposite side isn't there. So I have to bring back our old friend Pythagorean theorem. I'm going to call you C because you're the hypotenuse. I'll call you A and I'll call you B because it doesn't matter which is which. So A squared plus B squared is going to equal C squared. A is, I don't know. B is 3, so 3 squared is 9. Let's skip a step, save some time. C is 13, so 13 squared is 169. Nice. I'm going to subtract 9 from both sides, and that gives me A squared is equal to 160. Square root that. Now, I don't know what the square root of 160 is off the top of my head, but what I do know is I can make a factor tree. I was going to try to do some stuff in my head, but it's just not going to work right now. So I'm going to make a factor tree using 160. Okay. That's 40 and 4. Don't circle either of those. That's 4 and 10. Don't circle either of those. That's 2 and 2. That's 2 and 5. That's 2 and 2. All right. So A is going to equal the square root of 160, which is 2, 2, 2, 2, 2, 5 of them. 2, 2, 2, 2, 2 times 5. Okay. Okay. Circle a group of 2's, bring it out. Circle another group of 2's, bring it out. Okay. 2 times 2 is 4. My leftovers is going to be 2 times 5, which is 10, which means after all of that, my job was to find the opposite side according to theta, and I end up with 4 root 10. So my opposite side according to theta is 4 root 10. Now, before you get all cocky and arrogant, we're not done. And we're not done because I'm not allowed to have a square root in the bottom of a fraction. So we multiply our fraction by root 10 over root 10. That gives us 3 root 10. And 4 times root 10 times root 10 is the same thing as 4 times root 10 squared, which is the same as 4 times 10, which is the same as 40. And that's my guy right there. So kind of messy, kind of difficult, lots of fun. Find the measure of the angle, theta right there. All right, so there's my theta. This is some right triangle trigonometry, so I have to think SOHCAHTOA thoughts. So if I'm looking at theta and I'm comparing 2 and 3, I've got myself an adjacent side and I have myself an opposite. My hypotenuse right there is blank. Don't need it. Don't even bother doing it. Don't need it at all. So if I think SOHCAHTOA, which is that cute little acronym to help us remember what's what, I need the one that involves my opposite and my adjacent, my O and my A, and that's tangent. So tangent theta is going to equal my opposite over my adjacent. So rewriting that out, tangent of theta equals, look at all this space that I'm leaving, opposite is going to be 3 over the adjacent, which is going to be 2. Now, I'm solving for theta. I have to find the measure of theta. How do I get rid of a tangent? Divide both sides by tangent? No, no, no. You use the inverse function. So the inverse tangent of tangent theta is going to give me theta. Well, if I inverse tangent the entire left side, then I have to inverse tangent the entire right side too. I'm not going to pretend that I know what the inverse tangent of 3 over 2 is, so let's use good old technology. The inverse tangent of 3 divided by 2. And of course, it's not giving me at all what I want. So let me go off site to a calculator. The inverse tangent of 3 over 2 is 56.3. Now, I know we're not supposed to look at this and say, you know, well, that looks pretty good. If I were to get out a protractor, that looks like it could be 56.3. It actually kind of doesn't. But, you know, that's my guide. That's how I do it. That's my answer. So there you have it, 56.3. Solve the triangle. Solve the triangle means find all the missing sides and all the missing angles. Now, the first thing that we want to do is try to figure out which one of these do we have two of, because if we have two of them, we can find the third one. Well, I have two angles here, invisible 90 degrees and 33, which means 180 minus 90 is 90, and 90 minus 33 is going to be 57. So I have all my angles down. Now what I need to do is I need to find my hypotenuse and whatever side this is. Now, in order to do that, we're going to think SOHCAHTOA thoughts. So let me write that down. I'm going to pick an angle, any angle, it doesn't really matter. I'll pick 33. And if I'm looking at 33 as my primary angle, my theta, this makes it my adjacent side, and this is going to be my opposite side. So I need to find my adjacent side, and I need to find my hypotenuse. So let's start out by finding hypotenuse. Why not? Who cares? My hypotenuse, looking at 33, and the fact that I'm given my opposite, I'm going to need one of my trig functions that require the opposite and the hypotenuse, and that's sine. So sine theta, and in this case, my theta is 33 degrees, is going to equal my opposite, which is 14, over my hypotenuse, which is, I don't know. Let's call it C, because, you know, hypotenuses are C. Hypotenuse? Hypoteni? I don't know. Now, what I'm going to do is I'm going to use the wonderful world of technology to find out what sine of 33 degrees is. Anytime now. Any moment. Siri's working on it. While we're waiting, don't forget to click the little like and subscribe button. It's having connection errors, so let's go off site. Sine 33 is, no, I want degrees. Sine 33 degrees. 0.5446. So 0.5446. Now my job is to solve for C. So if I multiply both sides by C, that has C on level ground now. And if I want to get C all by itself, I'm going to divide both sides by 0.5446. 14 divided by 0.5446. Cross that out is going to be going off site again. 14 divided by 0.5446. 25.7069. Nice. What did I say? 25.7069. Nice. So that's my hypotenuse, 25.7069. Now you might be thinking, all right, well, do I have to do that again in order to find my adjacent side? No. In fact, if I wanted to, and what I'm going to do to find the remaining side is I'm going to do Pythagorean theorem just because it's been a minute since I've done Pythagorean theorem. So you're my C. I'll call you A because it doesn't really matter which one's A or B as long as the longest side is C. And I have A squared plus B squared equals C squared. So A squared is going to be 14 squared plus, I don't know, b squared equals 25.7069 squared. I know that's 196. You're still b squared. And 25 times 7 is 25.7069 times itself is 660.8447. All right, so what did I say? 660.8447. Let's subtract both sides by 196. So let's do minus 196 here. Hit enter. That's 464.8447, 464.8447, 464.8447. Let's square root everything. And that gives us, let me see if I can just, 21.5602. So let's do 21.56. Where are you? 21.56. So cleaning all of this up, cleaning all of this up, cleaning all of this up, and cleaning all of this up, I solve the triangle. I have 14, 21.56, and 25.7069. And I have a 90-degree angle, 57 degrees, and 33 degrees. Oh, wasn't that fun? Took a while, but very well worth it. Find the exact value of cosine 9 pi over 4. What I'm going to need if I find the exact value is definitely not a calculator. See, when we deal with sine and cosine, 99.99% of the time when we use a calculator, we end up with a crazy irrational number. So I'm going to refer to this chart right here. That's my reference angles chart that I stole from the internet. Thank you, math, blah, blah, blah. Now what I need to do is I need to find cosine of a reference angle. Well, you might be looking at that and saying, well, that's not a reference angle. Reference angles are supposed to be between 0 and 90 degrees, or 0 and half a pi. This is 9 over 4 pi, which means it's over 2 pi. So what I'm going to do in order to find my reference angle is I'm going to subtract 2 pi from that guy right there. This, of course, means that if I want to subtract 2 pi, it's going to be the same as 8/4 pi because, you know, fractions and stuff. And that leaves me with pi over 4. Now, where does that fall as far as being between 0 and half a pi? Well, that is between 0 and half a pi. So if we're looking at this as to where is this on a coordinate plane, it's in quadrant 1, which means I don't have to change anything. So cosine 9 pi over 4 is the same exact thing as cosine of pi over 4. Now, what is cosine of pi over 4 as far as my reference table goes? Well, there's pi over 4, which is 45 degrees. The cosine of it is going to be root 2 over 2. So whenever it says find the exact value, you're looking at this reference angle chart. That's what you're looking at. Find the exact value never means throw it into a calculator and round, because technically that's not the exact value. This is the exact value, and as you can see, square root of 2 is going to be irrational. It would be ugly if you use a calculator anyway, and if there's anything I'm not, it's ugly. Like and subscribe. Find the exact value of sine of 510 degrees. Okay, well, in order for me to find the exact value, I have to go to my reference angle chart right here. Now, as you can see, I don't see 510 degrees up here. Don't see it at all. So what I have to do is I have to find myself a reference angle. Now, I have 510, and it looks to me that 510 is going to end up in quadrant 2 here. So what I can do is I can subtract 510. I could subtract 360 from that, and that will get me to 150. So if this is 90 degrees, right, and this whole thing is 150, that'll make u 60. Now, I don't care about this. I care about the reference angle, and the reference angle is always the angle closest to the x-axis. So my reference angle for here is going to be 30 degrees. So at the end of the day, I need to find the sine of 30 degrees. And the sine of 30 degrees, according to this guy right here, is going to be 1/2. Now, sine is always going to be positive in the first two quadrants, so my answer stays positive. Once you turn into the other signs or the other trigonometric functions, you have to figure out which trig function is positive and which one's negative depending on where it lands. In this case, it lands in quadrant 2. Sine is positive in quadrant 2, which means my answer is positive 1/2. There you go. Find the value of this trig function right here. Okay, well, I don't have an angle, and it's telling me to find the secant of an angle. I don't have one. I don't even have a picture, but this is what I do have. I can just make a picture, just like that. So what I have is a point floating around out here. What this point tells us is this length goes from 0 to negative root 15, which means that length is root 15. We know that this guy goes up to 7, so I have a height of 7, and I don't know what this is. It's asking me to find secant theta. So if I spell out SOHCAHTOA, I care about the ka, my cousin, because secant is 1 over cosine. So secant theta is going to be the reciprocal of adjacent over hypotenuse, so hypotenuse over adjacent. Well, terrific news. I have my adjacent. I don't have my hypotenuse, so let's break out the old Pythagorean theorem. C is already called C. I called it C for a reason. We'll call you A. We'll call you B. And I have A squared plus B squared equals C squared. So I called A 7, so 7 squared is 49. I called B the square root of 15, so the square root of 15 squared is 15. And C squared is, I don't know yet. Oh, God is good, because 49 plus 15 is a perfect 64. Perfect because it's a perfect square. In order to get C all by itself, you square root. C is 64. Square rooted, that becomes 8. So secant theta, and I'll write it over here because I know I'm going to have to take one more step. I'm going to write it down here, is the hypotenuse 8 over the adjacent, which is the square root of 15. You never can have the square root on the bottom of a fraction, can you? So we have to multiply the top and the bottom by root 15 over root 15. You got to rationalize this guy. So when we do that, we have root 15 times root 15, which is 15, because root 15 squared. U become 8 root 15. Now, before we circle this and be happy and call this a day, we care about secants. Okay? Sine is positive here and positive here. Cosine is negative here and negative here. Secant is a cos function. And since everything happens in quadrant 2, this guy ends up being negative. Can't forget that little detail. Very easy to forget after doing all that work. But we did it. We had a great time doing it, didn't we? Didn't we, boys and girls? All right, this one's going to be a doozy. Find the other trig values if cotangent of theta equals negative root 7 and sine theta is greater than 0. In other words, sine is positive. So let's do this. Let's make ourselves a little fake coordinate plane and remind ourselves where sine is positive. Sine is positive up here and up here. Now, if my job is to find the other trig values, it's going to matter about everything else too. So while I'm at it, I care about sine being negative and sinus negative down there. Sinus negative sounds like I'm getting over a cold. So cotangent is negative root 7. Again, I care about positives and negatives everywhere because if my job is to find the other 7 trig values, if that's negative, I'm going to have to deal with negative values all over the place. So let's find out where cosine is negative. Cosine's negative here on the left and positive here on the right. Now, how is this going to help me with the others, like tangent and cotangent? Well, sine divided by cosine's tangent. Its reciprocal is cotangent. I don't know if I said that right. Sine over cosine's tangent. Its reciprocal is cotangent. I'm just giving it a second shot in case I misspoke earlier. But, that's going to help out here. Now, what I also need to deal with is I have to find missing pieces. I have to find sine, cosine, tangent. That's going to require knowledge of SOHCAHTOA. Why I wrote it out incorrectly, I don't know. It's been a long week. SOHCAHTOA. Okay. Now, the first thing I have to do is I have to break down the fact that cotangent of theta is negative root 7. So if I'm supposed to find sine and cosine and tangent and its reciprocals, I care about information about its opposite, hypotenuse. I care about everything, every single part about a right triangle. So I'm making this fake arbitrary right triangle here so I can gather as much information as I have. Okay. Cotangent theta comes from the fact that tangent is opposite over adjacent, which means cotangent, its reciprocal, is going to be adjacent over opposite. Okay, I know that cotangent is negative root 7. I'm not going to worry about the negatives right now when I want to put pieces on a triangle because you can't have a negative length. So I'm going to write that it's root 7 over 1. So according to this, if this is theta, and it doesn't matter which one theta is. If you're wondering, well, which one should I call it? Doesn't matter at all. If I have theta, according to what I just said, the adjacent side is going to be root 7, and the opposite side is going to be 1. That leaves me with the hypotenuse, which I'm going to call C. Why? Well, in order for me to find C, I got to use the old Pythagorean theorem. So what color haven't I used yet? Let's do purple. It's going to be a rainbow when we're done. A squared plus B squared equals C squared, right? You can be my A, you can be my B, and C has to be just C. 1 squared is 1. Root 7 squared is 7. That's going to equal C squared. Let's bring it up here so I leave myself plenty of space for my answers. 1 plus 8. 1 plus 7 is 8. That equals C squared. The square root of 8 is going to be C. All right. Now, if C is the square root of 8, that means I should be able to look at that and be like, wait a minute, can I go a little bit further? Yeah, I can. 8 is 2 times 2 times 2, which means if you rip out a pair of 2s, C is actually this. So my hypotenuse is root 2. My hypotenuse is 2 root 2, pardon me. My adjacent is root 7, and my opposite is 1. Now I have enough information to put all this together. So I want to find what sine theta is. An angel just got its wings. What cos theta is, and what tangent theta is. I also need to find out what its reciprocal cosecant theta is, what secant theta is, the reciprocal of cosine, and I already have u, so I am 1/6 of my way done. Hooray! Now listen carefully to how I'm going to proceed from here on out. Let's deal with the numbers, and then when I'm done, we'll deal with what's negative and what's positive. Let me repeat myself. Let's deal with the numbers, and then when we're done that, let's deal with what's positive or negative. Okay? Sine is opposite over hypotenuse, which means 1 over 2 root 2. Immediately, we realize this ain't good. You can't have root 2 on the bottom. So if we multiply the top and the bottom by root 2 over root 2, that leaves us with 1 times root 2 over 2 times root 2 squared, which is 4. Okay. Cosecant is going to be the reciprocal of this, which is, if I'm not going to look at the answer, I'm going to look at the original, which is going to be 2 root 2 over 1. Okay, so I'm half done. Well, not really, because I have negatives and positives to deal with. Cosine is adjacent over hypotenuse. Cosine is adjacent root 7 over hypotenuse, which is 2 root 2. Let's multiply the top and the bottom by 2 in square roots over root 2. And that gives me root 14 on the top. 2 times root 2 times root 2 again, I already know, is going to be 4. Secant theta is the reciprocal of this, but I'm not going to set it up that way. I'm just going to write out the fact that if cosine is adjacent over hypotenuse, then this is going to be hypotenuse over adjacent. So I have 2 root 2 over, root 7. Multiply the top and the bottom by root 7 over root 7. That gives me 2 root 14 over root 7 times root 7 is 7. Last but not least, if my cotangent is negative root 7, okay, I'm not worrying about negatives right now. I already said that. Let's not worry about negatives. This becomes 1 over root 7 times the top and the bottom by root 7 over root 7, and that gives me root 7 over 7. Now, last but not least, I need to apply my negatives. Okay. All of this stuff, first off, cotangent is negative. Okay. Sine is positive, which tells me that this stuff, which tells me that the original problem, if cotangent is negative and sine is positive, cotangent is negative in 2 spots, here and here. So if sine is positive and cotangent is negative, then everybody lives in the second quadrant, which is why I drew this picture. So in the second quadrant, sine is positive, leave this positive, which means cosecant is going to remain positive. In the second quadrant, cosine is negative, so make this negative, which means secant is going to be negative. Doesn't look pretty, but I'm making it red. I already know that cotangent is negative, So tangent's going to be negative. But if you need further proof, in the second quadrant, sine over cosine is going to be positive over negative, which is negative. There you have it. So to put this all together, even though it looks a little bit sloppy, I have all 6 of my trig functions where sine and cosecant are positive, cosine and secant are negative, tangent and cotangent are negative. Also, when I figured things out, I had to make sure that I didn't have any square roots on the bottom. And there we have it. Okay. Very involved problem, took a lot of time, but that's to be expected with guys like these. And also keep in mind, didn't use a calculator. So if you had a calculator, life would be a lot easier, but then you wouldn't have exact values. I didn't ask for that, but I assumed because I created the problem. Okay? Thanks for watching. Graph y equals 3 cos theta. Let's understand what cosine looks like. Okay? I'm going to try my best to draw a cos theta on this little thing here that I have that never works right. If it's regular cos theta, we care about its height being 1 and -1, or an altitude of regular 1. We care about all of our action happening at every half a pi. So you'll be pi, you'll be 2 pi. For a regular cos function, it repeats the process. In other words, it has a period of 2 pi. So it starts here at 1, goes through at half a pi, bottoms out at pi, goes through again at 3/4 of a pi, or 1.5 pi rather, and then peaks out. As you can see, drawing this is not my strength. So if it's 3 cos pi, and that's the only difference that we have, we take this picture right here and make the altitude 3 times bigger. If the number is multiplied to your trig function, that changes the altitude, the height, by that much. So instead of starting at 1, we start at 3. We go through the x-axis at half a pi. We bottom out at -3 at pi. Go through the x-axis half a pi later, and we repeat the process every 2 pi. So bottom out here, and we're done. Now, the fun part about all of this is me trying to draw this out. Oh my gosh, I actually started out decent for once. Oh, please, Lord. Nope, screwed it up already. Screwed it up even worse. What's worse is I have another problem like this later on. That actually turned out nice. Maybe if I talk, that'll help. Yeah. All right. That's what it's supposed to look like if this was a little bit cleaner. Ugh. You know what? Whatever. You get the idea. That is my 3 cos theta picture. I'm not an artist. I'm a math guy. Still, I tried, and that's all God cares about, isn't it, boys and girls? Like and subscribe. Oh, graph y equals cosine of this whole mess. This is called a sinusoidal graph. Okay, sinusoidal because it is a mixture of sine and soda pop. Also sounds like a Phil Collins song. Studio. Enough dad jokes for today. So let's try to compare this to what the actual sinusoidal picture looks like. Y equals A times whatever trig function it is that you're dealing with, times, and this is where it looks kind of weird, B times theta or x minus h, close it, plus k. This is the typical graph for the sinusoidal thing. Now, what's what? A, or better yet, the absolute value A is the altitude. That's how tall my picture is. Okay? I had a previous problem where the only thing I had to worry about was the altitude. Here, the only thing I don't have to worry about is the altitude. What's B stand for? B is the period, but the way you find the period is you take 2 pi and divide it by the absolute value of B. That's my period. That's where everything repeats, okay? Now, what's H and what's K? H is the left or right phase shift. If h is positive, you move right. If h is negative, you move left, which means k is the up or down vertical phase shift. Okay, so that kind of tells me what things look like there. Here's issue number one. This does not look like this. Why? I don't see any parentheses living inside this cosine parentheses. So in order for me to make this look like this, I have to remove that 4 from the denominator of this guy. And if I do that, I have to do the same thing from here. So although it's kind of unorthodox, what I have to do is rewrite this equation and factor out a 1 over 4 from both of these. One more time, I have to factor out a 1 over 4 from both of these. So I'm going to have cosine with the altitude invisible 1. If I factor out a 1/4, okay, that makes that just pi. If I factor out a 1/4 from pi over 4, that leaves me with just pi. Now I have -2. All right, so first things first, cosine look like this. We also know, based off of what I just wrote out, that my altitude is invisible 1. The height doesn't change. God is good. The period is going to be 2 pi over 1/4. Now, if I take 2 pi over 1/4, over 1/4 means I have to multiply the top and the bottom by 4, giving me a period of 8 pi, which is why this graph that I stole from CUDA software is so long. My phase shifts. My phase shift is, since this is a positive pi, I go left pi spaces. Now, if you're like, whoa. You just said this is positive pi. Shouldn't you go right? Nope, because it's the opposite of this guy. Everything in here seems to always live in opposite land. So we're going to phase shift left 2 pi. I'm sorry, 1 pi. 1 pi. That means phase shift down 2. Okay? So I'm going to pretend that this is pi. Okay, just floating around out here. If I move left pi 2 and down 2, that makes my brand new origin right here. Now, cosine starts at 1 usually, which means my new picture is going to start here. So I'm going to draw dots as to where things should be. Now, this is going to peak out at -1 and bottom out at -3. So if a question were to ask you, well, what's my maximum, what's my minimum? My maximum is going to be -1 and my minimum is going to be -3. Now, it's going to completely repeat itself every 8 pi, which means I'm going to go all the way over to 7 pi and draw that dot again. Which means if it peaks out at -pi and 7 pi, then it's going to bottom out here at 3 pi. It's going to go back to its normal position at 5 pi and regular pi. So basically, go 2 spaces, down 1, go 2 spaces, down 1, go 2 spaces, up 1, go 2 spaces, up 1, go 2 spaces, down 1, go 2 spaces, down 1, go 2 spaces, can't. The fun part about this problem, and the part that makes me the most nervous, is my ability to draw. So don't judge me, please, for the love of God. All right. Boom, 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 boom. Did I draw a dot here? I did. It's barely, you can't see it. Boom, and if I wanted to, meh. So that's my picture. I'll give myself a small pat on the back. That didn't look half bad. But that's how you do it. That's how you graph a sinusoidal equation without a calculator. Sinusoidal. All right, I'm done. Bye. Like and subscribe. Solve using degrees. All right, I'm going to write this out. I'm going to write this out, and I'm going to give myself a little bit of space because you will see what happens. What I really like about this problem is it doesn't say find the exact value, which means here I'm not going to worry too much about going to a reference angle table. I could, but I won't. I could, but I won't. What I'm going to do is I'm going to take the inverse sine of both sides. That's why I wrote so much space over here. I'm going to take the inverse sine of both sides. Now, the point of this is to get theta and whatever's attached to it all by itself. The inverse sine of a sine leaves whatever's inside left over. So now all I have to do is divide whatever this becomes by 4, and I have my answer. But spaghettios. Because this guy, the inverse sine of 2 root 3 over 3, it's undefined. Which means if I divide something that's undefined by 4, it doesn't really matter. And if my job is to solve, I don't have an answer. So in a case like this, I have no solution. Oh, isn't that nice? It is nice. Solve using radians. Okay. I did a previous problem like this where I used a calculator, but a lot of calculators don't have an inverse cotangent. See, my job is to get theta all by itself, but theta is trapped by this cotangent wrapped around it. And so what I would have to do is I would have to take the inverse cotangent of both sides. But I'm not going to do that here. I'm going to be a little creative. What if I don't have an inverse cotangent button? Like, let's say I'm on Desmos, which doesn't have an inverse cotangent button. What do I do? What do I do? What do I do? Well, if root 3 over 3 equals cotangent of stuff, then I can just turn this into root 3 over 3 equals 1 over the tangent of stuff. Oh, I didn't know I could do that. Oh, thank you. Now what I have here is I have myself a proportion, crisscross applesauce, 3 times 1 is 3. So I'll put that 3 over here. Root 3 times tangent of stuff is going to be root 3 tangent of stuff. What is that? 6? 6. Divide both sides by root 3, and now I have tangent of theta plus pi over 6 equals, leave myself some space, you'll see why in a second, 3 over root 3. Now I can run into most calculators and take the inverse tan of both sides. Now, when I take the inverse tan of a tan, that leaves me with whatever I have. All right, so I'm going to write up here, theta plus pi over 6 equals the inverse tangent of 3 over root 3. By the way, don't yell at me about root 3 being on the bottom. I'm just going to throw it all into a calculator anyway. When I throw it all into a calculator, I get pi thirds. Trust me on this one. Okay? This is in radians. Make sure that your calculator is set to radians. Now I have to subtract pi over 6 from both sides. Pi thirds minus pi over 6 is going to be pi over 6, because this could be like 2 pi over 6. So 2 pi minus a pi, it's just a pi. Sounds like Thanksgiving. But what I have to do in a case like this is I'm solving for all possible thetas. Remember, cotangents along with all the other trig functions repeat itself. So when I'm dealing with a tangent or a cotangent, I have to add pi n to my final answer because of the way that tangents and cotangents repeat themselves. So my final answer is going to be pi over 6 plus pi n. That's every single theta. Now, if it gave me like restrictions where it said, well, here's an interval of 0 and 2 pi, then that changes things and maybe I only have two answers, but I'm solving for every possible radian and this allows for every possible answer. So that's my guy. I'm done. I had fun. Thank you for watching. Find the exact value of the inverse tangent of -3. All right. Whenever it sees exact value, that's basically your teacher or a book saying, let's avoid a calculator and let's go run to a reference table like the one that I just threw up on the screen here. I'm going to avoid using the phrase throw up ever again. All right. So usually when you find the inverse tangent of something, that means the tangent of which one of these guys is going to give you -√3. Right now, let's not worry about the negatives, and let's just worry about the √3. The tangent of which one of these guys is going to be √3? Is that one right there, 60 degrees. It doesn't say here which one I have to use, whether it's degrees or radians. So let's use degrees. Let's use degrees. So right now, the inverse tangent of √3 is going to be 60 degrees. Now let's be very, 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 very careful here. Okay, inverse tangent, or tangent in general, is negative here and here. Since inverse tangent is negative, it must fall in the fourth quadrant right here. Which means instead of it being 60, it's going to have a reference angle of -60. So we could say -60 degrees is my answer. If we also wanted to throw it as radians, we could say -pi/3. I know it's so hard to see it even with my bad eyes. Either one of those is a possible answer. But since this was negative, it makes my answer -2 because of where tangent is negative. So there you have it. Find the exact value of cosecant of the inverse secant, so let me throw that in parentheses just to make it look better. Maybe my parentheses could have been better, of √6/2. Now, before you start thinking reference angle chart thoughts, before you start thinking unit circle thoughts, you're not going to find √6/2. It ain't happening. So this is what I want to do. I'm going to try to turn this into a right triangle, and I want to think Pythagorean theorem thoughts. First things first, what is inverse secant? What does that mean? Well, that means the secant of what angle is going to equal √6/2 in positive land. What is secant? Well, let's think SOHCAHTOA. Secant is the inverse of cosine. So if cosine is adjacent over hypotenuse, then secant is going to be hypotenuse over adjacent. Okay, so √6 is hypotenuse, so let's draw that out. Adjacent means right next to it, that's 2. And what's going to happen is I'm going to eventually find out that I'm going to have to deal with the cosecant, which is sine flipped. I'm going to need to know information about the opposite side. So let's use the old Pythagorean theorem. A squared plus b squared equals c squared. You're c, I'll call you a, and I'll call you b. So I have 2 squared plus, I don't know, the opposite side squared is going to equal √6 squared. 2 squared is 4 plus b squared. √6 squared is 6. Subtract 4 from both sides. I've got b squared equals 2. Square root it. B is √2. Which means you are √2 and you are my opposite side according to the picture that I drew. Now, based on this triangle, okay, I now know what this guy is. So cosecant based off of this information of theta, cosecant of theta is going to equal the hypotenuse over the opposite side, which is root 6 over root 2, which if I wanted to, before you start thinking, well, why don't I just multiply the top of the bottom? No, don't do that. Let's do this instead. Root 6 over regular 2 just gives me root 3. So cosecant of the inverse secant of this stuff gives me enough information where I can throw it all into a right triangle, do some Pythagorean theorem, get some info, and then find the cosecant of that. Gets me root 3. Kind of a weird problem. You could probably throw that into a calculator and be all right with it. But since it says exact value, I don't know what root 3 is off the top of my head. Some of you geniuses might, but that's what I get. Use a trig identity to answer this question right here. Okay, I have sine, and I'm being asked to find cosine of theta minus pi over 2. Well, there is a trig identity that says cosine of theta, or x minus pi over 2, which is the same as 90 degrees, happens to be the exact same thing as sine theta. So this guy is the same as that guy. This guy is the same as that guy. And if I'm being asked to find this guy equals the same thing. Too easy, you say? Maybe. But, that's the problem that you're being asked to do. And if you use the trig identity just the way it's given to you, you're going to get your answer right away. So that's it. Show that the identity is true. Boys and girls, this is called a proof. Now, you probably thought that, I'm done geometry. I'll never have to do a proof again. Lies. It's all a lie. This is actually pretty easy. I need to show that sine x, secant x is the same as tangent x. So what should be going through your head is you should be thinking, all right, well, tangent x is sine over cos. So can I turn that into sine over cos? I sure can. Sine x, can't do anything there. Secant x is 1 over cosine x. And when I multiply sine x to 1 over cosine x, I get sine x over cosine x, which is the same as tan x. Ladies and gentlemen, I'm done. That's my proof. I showed what I needed to show. It wasn't a lot. Too easy, you say. Too easy, sir. Well, sometimes these problems are a lot friendlier than you think. And this is one of them. Show that the identity is true. Ooh, we have ourselves a proof. What we want to do is we want to take this weird looking fraction and make it look like that. So basically, the best thing to do is whenever you see sines and cotangents floating around is to break it down to its simplest parts. Sine x is sine x, can't really change that. But cotangent x is cosine x over sine x. Sine x is in an invisible numerator and an invisible denominator. Well, not invisible, actual denominator. And they cross each other out. Now, when I do that, I'm left with 1 over cos x. And you might be thinking, no, that's too easy. There's no way that's all I have to do. Yeah, it is. It's a pretty friendly problem. Some of them are friendly, just like me. Show that the identity is true. We have cosecant squared x multiplied to cos squared x is equal to cos squared x minus 1. All right, Let's try to break this down into the simplest way possible. Whenever I see cosecants, I want to try to turn that into its actual thing. So let's do this. Let's put cosecant squared x in the bottom and make it sine squared x. Okay. Cos squared x, cos is pretty basic, so let's leave it like that. And let's try to change it into something that looks like that. Cos over sine is cotangent. So cos squared x over sine squared x is cotangent squared x. There is a little rule that says that cotangent squared x is cosecant squared x minus 1. And because of that, that allows us to arrive to our answer. So some of you might look at this and be like, all right, should we do something with maybe tangent and make that 1 over tangent squared? And then, tangent squared is the same thing as blah, blah, blah. Listen. This is good enough. Leave it like that. My proof is done. Our problem is done. Like and subscribe. Solve for every theta in between 0 and 2 pi. Let's take a look at what I have. Okay, I have a tan squared theta floating around on both the left and the right. When you see problems like this and you have, whether it's tan, secant, sine, squared, you're automatically thinking quadratic thoughts. You're thinking zero product property thoughts. And that's how I'm going to handle this guy right here. So let me move it to the left. Okay, I'm just going to start writing it from the left because I'm going to need all the space that I can with this one. All right, so I have 1 minus tan squared theta on the left is going to equal negative tan squared theta again on the right. Let's keep my tan squared theta positive. So the first thing I'm going to do is add 2 tan squared theta, add 2 tan squared theta. You cross out. 1 is alone. If I take away 1 tan from 2 tans, then I get 1 tan squared theta. I'm also going to subtract 1, and that leaves me with 0 equals tan squared theta minus 1. Now, you might be thinking, all right, well, what do I do now? This is difference of squares, boys and girls. And you might be thinking, the devil, you say. I don't see any difference of squares. Difference of squares looks like this. Sure does. So if I were to just make believe that x is tan, then I could just write this out as x squared minus 1, which factors out to x plus 1, x minus 1. So I can turn this into 0 equals tan theta plus 1 times tan theta minus 1. See what I did? That's difference of squares. Zero product property. Take each guy and set it equal to 0. So I'm going to do this twice. I'm going to have a lot to deal with. So let's split this guy right down the middle. And let's deal with this one first. Tan theta plus 1 equals 0. Now let's subtract 1 from both sides, and that gives me tan theta equals, give myself some space, negative 1. Why did I give myself some space? Well, if I want to get theta all by itself, I have to inverse tan both sides. Yeah. That crosses out. Theta is going to equal pi over 4. Now, this is a negative 1. Tangent is negative in 2 quadrants, quadrant 2 and quadrant 4. So if this is going to be quadrant 2, then that implies pi over 4 is going to be negative. And if it's pi over 4, negative pi over 4, that's no good. That's no good because it doesn't live in my area. So what I need to do is I need to add 360 degrees, or in this case, 2 pi, which if I add 2 pi to pi over 4, that gets me 7 pi over 4. So that's quadrant 4. And if I want the quadrant 2 version of it, I'm going to have 3 pi over 4. See, 7 pi over 4 is like the same as 45 degrees. So that's going to be the 45 degree version over here. So there's 2 of my answers. Oh, but I'm not done. I'm not done at all. You see, because I now have to do tan theta minus 1 equals 0. Add 1. Tan theta equals, give myself some space, 1 inverse tan both sides, inverse tan both sides, and theta is going to equal pi over 4. Tangent is positive in quadrant 1 and quadrant 3. This is quadrant 1. This is basically 45 degrees. So if I spin it out to quadrant 3, let's add pi, and that will give me 5 pi over 4. So over here, my 2 guys are 5 pi over 4 and pi over 4. So to put this all together, to sum this up, to finalize my answer, theta is 4 of them if it lives in between 0 and 2 pi. And those 4 are going to be, in order from least to greatest, pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. Whew! That's it. Solve for all thetas in between 0 and 2 pi. All right, well, we've got a sine squared, and we got some number floating around. So I'm thinking quadratic thoughts. So if I'm thinking quadratic thoughts, let's get this -1 over to the left so I can have it equal 0, and then I can deal with maybe possibly zero product property thoughts. Let's put things in order too. 2 sine squared theta plus 3 sine theta, and if I were to add 1 to both sides, plus 1 equals 0. Now I did all this, zero product property, quadratic talk, and you're like, what do you mean? Well, if I were to look at this guy right here and factor that, that would factor to 2x plus, would it be 1? Yeah. And then x plus 1, right? Well, this is no different. It's just instead of x squared, I have sine squared. So this factors out to 2 sine theta plus 1 parentheses sine theta plus 1 equals 0. Okay? Now, zero product property says that this times that equals 0 means this equals 0 and that equals 0. So let me do 2 different problems. 2 sine theta plus 1 equals 0. Let me wave my hands a little bit, do a little bit of quick math. Subtract 1, divide by 2 would give me sine theta equals, leave myself some space, minus 1 over 2. Now I need to get theta all by itself. The way I get theta all by itself is I inverse sine both sides like so. That leaves me with just theta. And the inverse sine of -1/2 is negative pi over 6. Now that's no good. That's no good because I care about stuff in between 0 and 2 pi. Something that's negative doesn't fall into that category. So if I were to add 2 pi to this, or 12 pi over 6, that gives me 11 pi over 6. Now, 11 pi over 6 lives in quadrant 4. Okay? Sine is negative in quadrants 4 and quadrant 3. Now, if this is going to live in quadrant 3, I have to do some reference angle stuff. So since this is 1/6 pi away from the x-axis, then 7 pi over 6 is also 1/6 pi away from the x-axis in the third quadrant. There you have it. Now, that was this red underlined stuff. Now, keep in mind, I'm not done, so let me box this off to see if I get a few more answers. All right. Let's figure out what this is. I have sine theta plus 1 equals 0. Zero product property. Subtract 1, and sine theta equals -1. Inverse sine, both sides, like so. And the inverse sine of -1 is negative pi over 2. So theta is negative pi over 2. Once again, this is no good because it's negative. So we add 2 pi, which in this case is the same as 4 pi over 2. And that ends up giving me 3 pi over 2. Now 3 pi over 2 is the y-axis underneath the x-axis. So this is in between quadrant 3 and quadrant 4. So if you're like, so what quadrant's in it? What is it in? Neither. Which means this is going to give me just one angle because I'm not going to try to figure out what quadrant it is in when it's not even in a quadrant. So this guy only has 3 answers, and those are my 3 answers right there. All right? Find the exact value of 5 pi over 12. So for this one, I'm going to open up my reference angle chart. Usually when it says find the exact value, I'm going to be dealing with some type of reference angle. All right, so I look at some of these and I try to find out, all right, well, which of these angles is 5 pi over 12? And I realize none of them are. So this is going to require me to do a little bit of identity work. And in this case, what I want to do is I want to come up with 2 of these guys here in green that you can barely see. Which 2 of these could add or subtract out to 5 pi over 12 so that I can write it out as tan something plus something. Okay, well, if I were to add pi over 6 to pi over 4, that gets me 2 pi over 12. This gets me 3 pi over 12. Adding that up gets me 5 pi over 12. That makes me happy. Now, why does all of this even matter? What am I doing here? Tan alpha plus beta is one of those addition identity properties where tan alpha plus beta is the same as tan alpha plus tan beta. Let me write that up here. Tan alpha plus tan beta over 1 minus tan alpha tan beta. So what I could do is I could use this identity and rewrite this as that. So you would be my alpha, you would be my beta, story of my life. I don't know what I meant by that. And this gives me tan pi over 6, something that I can do because of all this stuff over here, plus tan beta, which is, that's supposed to be a plus sign, ended up weird, tan pi over 4, all over 1 minus tan theta, or alpha rather, which is pi over 6, times tan beta, which is pi over 4. Tan pi over 6, according to my chart, is going to be root 3 over 3 plus tan pi over 4 is going to be 1. according to my chart, over 1 minus tan pi over 6, which is root 3 over 3, times 1. Let's do a little combining up here. So if I were to make this 3 over 3, and if I were to make this 3 over 3, right, I get root 3 plus 3 over 3 minus root 3 over 3. Multiply the top and the bottom by the reciprocal of this guy. So I'd multiply the top and the bottom, and I'm running out of space here, so I'm going to try to do this a little bit in my head. If I were to multiply the top and the bottom by 3 over 3 minus root 3, the 3's would cancel out, and that gives me root 3 plus 3 over 3 minus root 3. Now, my issue here is that I have a root in the denominator, and that's no good. So I'm going to use the conjugate, which is the difference of squares idea, and multiply the top and the bottom by 3 plus root 3. What that does is it, again, treats it like difference of squares and eliminates the middleman. So this foils out, eliminating stuff in between, and the top gives me root 3 times 3 is 3 root 3. Root 3 times root 3 is 3. 3 times 3 is 9. And 3 times root 3 is 3 root 3. The bottom is going to be 3 times 3, which is 9. Okay. 3 root 3 minus 3 root 3 disappears, and then minus root 3 times root 3, which is 3. I'm going to have to scooch this up. Sorry, reference angle table, but you're getting scooched up there. Thought I'd be able to make it, but I didn't. Let me move it up here so I have myself a little more space. 3 plus 9 is 12. 3 root 3 plus 3 root 3 is 6 root 3. And then 9 minus 3 is 6. I can factor out a 6 on top, so that makes this 6 times 2 plus root 3 over 6. 6's cancel out. And at the end of the day, I have 2 plus root 3. So you might be thinking, man, I really wish this word wasn't there so I could just throw that into a calculator. Well, if I had 3 wishes, I'd be Aladdin. If I had, like and subscribe. All right, my job is to simplify sine theta cos 3 theta plus cos theta sine 3 theta. Now, if you know your identities, and I'm sure you already do, you know that sine alpha cos beta plus cos alpha sine beta, it's an ugly looking N, is going to be the same exact thing as sine alpha plus beta. Now, how did I come up with that? Well, first things first, I noticed that there's a theta, there's a theta, there's a 3 theta, there's a 3 theta, so there's similarities. I noticed sine, cos, cosine, and the first parts are both thetas and the second parts are both 3 thetas, and I'm thinking, all right, well, my options are to try to make these tangents, try to make these something different, but that's not going to really help me anywhere because I can't even make them tangents. I can't factor anything out. There's nothing I can do, so I try to look for an identity that seems to match this and that match that. Now, what this means is alpha is theta, beta is 3 theta, which means this whole guy becomes sine alpha, which is theta, plus beta, which is 3 theta. And if you have a theta plus 3 thetas, let me get out my calculator, type, that's 4 thetas. And that's it. Nothing to solve, nothing to do. It just says simplify. So we used some trig identity stuff to simplify it. There you go. Use the half-angle identity to find the value of cosine of 105 degrees. All right, well, it wants me to turn cosine of 105 degrees, and let me throw this in over here. It wants me to turn it into cosine of 210 over 2. Now, using my formula for half-angle identities, cosine of stuff is going to equal the positive or negative, and I'll deal with that in a second. Okay, the positive or negative 1 plus cosine of whatever this numerator is, so in this case 210, all over 2. Now 210 lives in quadrant 3. Cosine is negative in quadrant 3, so this plus or minus is just going to be negative. While I'm at it, if I want to take the cosine of 210, 210 is negative, and that would make me have a reference angle of 210 minus 180, 30 degrees. So the cosine of 30 degrees is going to be root 3 over 2. And all of this is still going to be over 2. Now, this is supposed to be trapped in the square root. I didn't make my square root big enough. My bad. My bad. Now, I'm going to rewrite this just because I know, even though it doesn't really look like it, I know that this square root covers everything, including that 2 on the bottom. So what I'm going to do is I'm going to rewrite this as the square root of, and let's do this. Let's kill 2 birds with one. No, actually, I'm not going to do it. I have plenty of space. 1 minus root 3 over 2 over root 2. Okay, if I multiply the top and the bottom by root 2, that helps me rationalize this guy. So let me move that up over here. Let me change some colors. And that's going to give me negative. And a square root times a square root means I can just multiply these guys together. So I can distribute within the square root. So 2 times 1 is 2, minus 2 times negative root 2 over 2 is just root 2. I'm sorry, that's root 3. Yeah, I was wondering, that something looks weird there. That's supposed to be a 3. That's a terrible looking 3. Root 3. And that's going to be all over 2. And I'm not sure if there's any more that I can do with this. I mean, I know the square root inside the square root looks kind of funky, but I think that's it. I think I'm just going to call it quits there. I mean, I've rationalized everything. There's no more square roots on a bottom. So yeah, that's my answer. It's not pretty, but that's my answer. Tangent theta equals root 2 over 4. Quadrant 1 only. That's going to make life a little easier. Cosine theta over 2 is what I need to find. So first things first, it's giving me tangent theta equals stuff. Let's do SOHCAHTOA stuff. SOHCAHTOA stuff. Tangent means opposite over adjacent. So if I were to draw some arbitrary right triangle like so and put some regular theta like so, my opposite's going to be root 2, my adjacent's going to be 4. I need to find cosine. Cosine is adjacent over hypotenuse. I don't have my hypotenuse. Let's find it using good old Pythagorean theorem. A squared plus b squared equals c squared. So I guess I'll call you A, I'll call you B, not that it really matters. 4 squared plus root 2 squared equals c squared. 4 squared, 16. Root 2 squared is 2. Add those up. Square root it. 18 is 2 times 3 times 3, so I can rip a 3 out, and I'm left with 3 root 2, and that's my c, and that's my hypotenuse. Now, that's great. And what all of this means is cos theta is going to be my adjacent over my hypotenuse, my 4 over 3 root 2. Multiply the top and the bottom by root 2 because you know it's illegal. I'm going to wave my hands a little bit to save a little bit of time because time is money. And I need the space too. And that's going to end up giving me 2 root 2 over 3. Okay, so cos theta is 2 root 2 over 3. Great. I have to find cos theta over 2, so that requires a half angle formula. So the way I set this up is I'm going to use the half angle formula, and instead of cos theta, I'm going to replace it with 2 root 2 over 3. So the half angle formula says, let's do plus or minus, which I know one of those is kind of useless, but I'm still writing it out. 1 plus cos theta, which is 2 root 2 over 3, all over 2. Now, one of the things that I don't need here is the negative. Why? Well, because this is quadrant 1. Cosine's positive in quadrant 1. So I don't need that negative there. Now, what I have to do is I have to get rid of the fact that we have a square root on the bottom. It doesn't look like I have a square root on the bottom because the whole thing's trapped inside a square root, but I have a square root on the bottom. I guess what I'll do is I'll multiply the top and the bottom by 1 over 2. That'll eliminate u. So this becomes distribute 1/2 plus root 2 over 3 after I simplify the 2's. Multiply that by 3, multiply that by 2, and I have 6 on the bottom. So I have 6 on the bottom. I have 3 plus 2 root 2. If I wanted to, see, 6 is still on the bottom inside a square root. So if I wanted to, I can write this out as 3 plus 2 root 2 up top, root 6 on the bottom. I can rationalize by multiplying the top and the bottom by root 6 over root 6. That gives me regular 6 on the bottom. And if I multiply a square root to a square root, I multiply that 6 to everything. So this is basically distributive property. 6 times 3 is 18. 6 times 2 is 12. Root 2. And all this is still living inside of a square root. So even though that's sloppy, that's my answer. Okay, a root within a root, that's fine. Don't be like, oh no, 18 and 12 and 6, they got to combine. No, because this is not a square root and those guys are. So complicated problem, very busy problem. But that's my guy. That's my answer. There you go. Find the exact values. Oh, well, this is easy. Cosine of 45 is just root 2 over 2, according to that reference table that I have memorized now. Cosine 15 isn't there. So I'm going to have to rewrite cosine 15 as cosine 30 over 2 and use the half angle formula. The half angle formula for 15 in quadrant 1 is usually positive or negative, but since this is quadrant 1, I don't need the positive or negative. This is going to be 1 plus cos 30 over 2. Again, usually that's positive or negative, but I don't need positive or negative because this is quadrant 1. It stays positive. Cos 30 is root 3 over 2. So I can write this as the square root of 1 plus root 3 over 2 all over 2. I can multiply the top and the bottom by 1/2. That gets me the square root of, these are now gone, 1/2 plus 3, root 3 over 4. If I write that out as 2 over 2, I can now combine fractions. So I'm going to pretend that that's a 2. 2 plus root 3 over 4. This means the square root of 2 plus root 3 over the square root of 4, which gives me the square root of 2 plus root 3 over 2. Now that was cos 15. So you're cos 15, you're cos 45. Let's multiply them together. Root 2 over 2 times root 2 plus root 3 all over 2. It's going to give me 4 in the denominator. A square root times a square root that has a bunch of stuff going on inside of it acts like distributive property. So big square root up here. 2 times 2 is 4. And 2 times root 3 is 2 root 3. So that's my exact value. That's my guy. Not bad. Not good, but not bad. All right. This one's going to be a doozy. We have to solve for every theta in between 0 and 2 pi. All right, I've got cos 2 theta, 3 sine theta, sine squared theta, 0 equaling that. So I'm thinking quadratic thoughts, but here's the issue. Cos 2 theta doesn't combine with any of these guys. Oh, if only I can make a cos 2 theta into a sine. What's that? Cos 2 theta is the same as 1 minus 2 sine squared theta? Oh, that just makes life so much easier. So let me write it out. 0 equals 1 minus 2 sine squared theta plus 3 sine theta plus 4 sine squared theta. Now, this is definitely 100% a zero product property in factoring thoughts. Let's combine these guys. We'll put them in order the way they're supposed to be. 0 is going to equal 2 sine squared theta plus 3 sine theta plus 1. Now, this is a quadratic that is factorable. If we were to pretend that sine squared is like the same as x squared and sine is the same as x, then we would be able to factor this out to 2 sine theta plus 1 times sine theta plus 1. So we have to do zero product property on this, so let's focus one part at a time. If I were to say 2 sine theta plus 1 equals 0, and just because I'm worried that I'm going to run out of space, subtract 1, divide by 2, that gives me sine theta equals negative 1 over 2. I didn't leave myself a lot of space. Shame on me. I'm usually good for that, but I forgot this time. Inverse sine both sides. Inverse sine both sides. And theta is going to be negative pi over 6. Now, negative pi over 6, that's no good. Why? Because I only want it to be in between 0 and 2 pi. So if I were to add 2 pi to this, that gets me 11 pi over 6, which lives in quadrant 4. Okay, 1/6 of a pi away from it. I can see that from here. Now, what am I dealing with? Sine? Sine is negative in quadrant 4 and quadrant 3. So if this is 1/6 pi away from the x-axis in quadrant 4, then 1/6 pi away from the x-axis in quadrant 3 is going to be 7 pi over 6. So that's one side I still have to do the other. So I have sine pi plus 1, sine theta plus 1 equals 0, subtract 1, inverse sine both sides, and that gets me theta equals negative pi over 2. Negative pi over 2, again, not where we want it to be. Let's add 2 pi, and when I add 2 pi, that gets me 3 pi over 2. Well, God is good, because 3 pi over 2 is the y-axis, which means it doesn't live in any quadrant, which means I don't have to worry about reference angles and stuff like that. I just get 3 pi over 2. So my final answer are going to be these 3 guys right here. Not in any particular order, but that's the order that I wrote it in, and I'm running out of space. So I spent all that time writing that little curvy thing, Kirby's Dreamland, Kirby's Dream. Like and subscribe. Find all the solutions in degrees if 0 equals cos 2x plus cos 6x. Now, before we tarry any further, you can't just add these guys. It's not like you can be like, well, let's combine them, cos 8x. No, you can't combine cosines that have different insides. So I have to find a way to add these. Well, I wonder if there's a trig identity that will do just that. Good news, there is. Cosine alpha, or in this case, alpha would be 2x, plus cosine beta, 6x, has an identity, and it's 2 cosine alpha plus beta over 2. So we'll put that in parentheses, times cosine alpha minus beta over 2. Now, if you're wondering, well, which one should be alpha, which one should be beta? At the end of the day, since you're using cosines, it's not going to make a difference. It's not going to make any difference at all. So if I make believe that 2x is alpha and that 6x is beta, I can say that 0 equals 2 times cosine alpha plus beta, 2x plus 6x, so 8x over 2. I'll simplify that in the middle, or in a minute, or in a middle. Don't know why I said middle. Cosine alpha minus beta is negative 4x over 2. And this ends up giving me 0 equals 2 cos 4x cos negative 2x. Now, why does all this matter? Those of you who have been watching these videos from beginning to end, have been really following along in chronological order, know that if 0 equals something times something times something, we do zero product property, and we set each something equal to 0. So the first thing that we would set equal to 0 is 2. 2 equals 0? Who cares? The second thing that we would set equal to 0 is cos 4x. So I'm not sure how much space I'm going to have. Kind of wrote a bit too big up here. That's all right. Let's split this into 2. If I have cos 4x equals, leave some space, 0, I can inverse cosine both sides, like so. That crosses out. And 4x is going to equal the inverse cosine of 0. It says degrees, so the inverse cosine of 0 is 90 degrees. Okay, divide u by 4. And 90 divided by 4 is 22.5 degrees. So half of my answers, I know I'm not done yet, half of my answers are going to be 22.5. Now, let's be a little careful, because up here it says find all the solutions in degrees, and it doesn't say like between 0 and 360. So what I have to do, because of the period that I'm given here, because my period is, where is it, 4x, I have to do 45n. So the period here repeats every 45 degrees, so I have to do 22.5 plus 45n. All right, let's do the other guy over here. If I were to take this guy, split it off to the side, and say cos negative 2x equals 0, because of zero product property, inverse cosine, negative 2x equals, once again, 90 degrees. That part didn't change. Divide by 2, negative 2. X is going to equal negative 45 degrees. Again, there's no bounds here. So I'm allowed to use negative 45 degrees. So X is going to equal also negative 45 degrees plus 90n. Why is this 90n? Because of the original problem. It repeats its period is going to be every 90 degrees. So I'm going to add 90n every single time. And so these are my answers. Yeah, there they are. Not pretty, but those are them and thems are those. The measure of angle A is 64 degrees. The measure of angle B is 98 degrees. A is 29, and I have to find B. Whenever I'm given a problem like that, when it gives you capital A and lowercase a, I'm thinking this could have to do with any triangle. Little a is going to be opposite of angle A. Little b is going to be opposite of angle B. And if I had a C here, then I would use C. Now, I don't have that. I'm supposed to find B. Now, obviously, I don't have a ton of information, but whenever you're given two angles and a side, or two sides and an angle, and you need to find the missing whatever thing that's missing. So I have A, B, B, so they come in pairs, almost like a proportion. I'm going to use what's called the law of sines. Now, the law of sines says that sine of an angle over its opposing side equals a sine of an angle over its opposing side equals sine of the third angle over its opposing side. Now here I don't need that much information. The letters kind of line up nicely. But once I have enough information where I have a pair of stuff and a pair of stuff where one of those things is missing, I could just set up whatever letters work for me and do sine of one angle over its opposite side equals sine of the other angle over its opposite side and go from there. So I have all my letters working out for me. Sine of 64 degrees over its opposite side, which is 29, is going to equal the sine of 98 degrees, boy band from the 90s, over, I don't know. So whenever I have a proportion, a fraction equals a fraction, you use the good old crisscross applesauce method. So I have 29 times sine of 98 degrees is going to equal B times sine of 64 degrees. Okay, I did this ahead of time to save a little bit of time. 29 sine 98 when multiplied out is 28.7178. B is still B, so I'll put B over here, just to keep it look nice. Sine of 64 degrees is 0.8988. In order to get B all by itself, I divide both sides by 0.8988, divide both sides by 0.8988, cross U out, and B ends up being 31.9513 miles. So whenever I give you a triangle, okay, and you have two pairs of things and you're missing one of them, that's when you use the law of sines. Okay? And that's what we did. Not pretty, but neither is your mom. Just kidding. Your mom's fabulous. Like and subscribe. If TRS is a triangle, so let's draw that out. TRS is a triangle. Of course, not drawn to scale at all. I didn't even look at the numbers. If the measure of angle S is 118 degrees, and if little s, which is going to be over here because it's opposite of s, is 16 feet, and if little r, which is going to be over here, is 5, find this angle right here. So I have big S, little r, I need to find big R. Whenever I have two of the same letter and two of the same letter, but I need to find a missing letter, I'm going to use the law of sines. So let's set that up. The law of sines says that the measure, or the sine rather, of an angle, so let's just choose an angle, big S, over its opposite side is going to equal the sine of the other thing that I care about, big R, over its opposite side. So let's plug stuff in. Sine of big S is going to be sine of 118 degrees. Over its opposite side is going to be 16. That's going to equal the sine of big R, which is, I don't know, over little r, which is 5. Whenever you have a proportion, a fraction equaling a fraction, you do a little bit of crisscross applesauce. So I'm going to do that. I'll write it over here. That gives me 16 sine r equals 5 times sine 118 degrees. 16, can't do anything with it. Sine r, can't do anything with it. But I can type all of this into a calculator. And when I do, I get 4.41473. 4.41473. A lot of decimals, but who's counting? Now, in order to get sine r all by itself, I have to divide both sides by 16. Like so. So sine r is going to equal, leave some space, 0.2759. Now my job is to find r. I don't have that yet. So I'm going to inverse sine both sides. Inverse sine both sides. When I run to a calculator and inverse sine this decimal right here, I end up with 16.0169 nice degrees. And that's my guy. That's all I have to do. Solve this triangle right here. All right, solve the triangle means find all the other missing parts. What do I have? Two angles, a side, nothing else. So whenever I have two angles, first thing that I can do is I can find that missing angle by doing 180 minus 113 minus 36, and that gives me an angle measurement of 31 degrees. So angle P is 31 degrees. I meant to say angle P is 31 degrees, not angle 31 degrees. Let me just write that out. So many mistakes. All right, now what do we have? Well, we have all three angles. This side opposes this side. And I don't know, if I were to choose, doesn't really matter, K, then what I can do is I can set up the law of cosines. Now, what the law of cosines says, and let me use P, what did I say, P and K? The law of cosines says that if I take this, the sine of, what do I know now, P over its opposite side, little p, that's going to equal the sine of big K over little k. Whenever you have two pairs rather, and you have three pieces of that information, the law of sines is definitely going to be your guy. All right, so let's plug it in, see what I get. Sine of P means sine of 31 degrees over little p, which is 14. Remember, little p is the opposing side. That's going to equal sine of k, which I know to be 36 degrees, over its opposite side, so we'll call that k, little k. Whenever you have a fraction equaling a fraction, crisscross applesauce, so 14 times sine 36 is going to be 14 sine 36 degrees, is going to equal k times sine 31. Okay, if you just want to do this all in one shot and right now divide both sides by sine 31, that crosses out and leaves k all by itself. And so I could just type 14 sine 36 over sine 31 straight into the calculator, and that gives me k equaling 15.9774. So you are 15.977. So I got two sides, all three angles. I still need this little h that's not called little h, but little h over here. So what I can do is I could use this same exact information over here, but replace the k's with the h's. If you're like, well, why not Pythagorean theorem? This isn't a right triangle. Can't use Pythagorean theorem. So I'm going to use sine big P over little p again and replace the k's with h's. Sine big H over little h. So sine 31 again over 14 is going to equal sine of, what do I have, 113 over little h. Crisscross applesauce. When I do that, that gives me 14 sine 113 degrees this time equals h times sine 31. If we want to throw all of this into a calculator, let's divide both sides by sine 31. Divide both sides by sine 31. That crosses out everything, leaving h on its own. And according to a calculator, which I used ahead of time, h is going to equal 25.0216. So 25.0216. There you have it. So 31 degrees, 36 degrees, 113, 14, something that's awfully close to 16, and something that's awfully close to 25. I did it. I did it. I solved the triangle. Find the area of this triangle right here. Normally it's a half a base times height. Simple, right? Well, not if we don't have the height. So can I easily find the height? No, not really. So what I'm going to do is I'm going to use this formula right here, which is kind of based off the law of sines. So the formula is area equals a half times some side times another side times the angle in between those two sides. Pew. All right, so I have a side. I have two angles. What I don't have is a side angle in between. So if I just find one of these sides, I'll have an angle in between and I'll be able to use my area formula. So let's find this guy, we'll call it little d. So if I have big D, if I have this side right here, which is opposite of E, and you're like, oh, I don't E, your plan is, I don't have E, it's falling apart. 180 minus 50 minus 66 gives me the measure of angle E. And the measure of angle E in this case is going to be 64. Nintendo's 64. But in this case, 64 degrees. So what I have is I have angle, its opposite side, but I haven't figured out the opposite side. I have an angle, its opposite side. I could use the law of sines. The law of sines that says the sine of some angle over its opposite side is going to equal the sine of some angle over its opposite side. So I use 64 and 8, boom. I use 50 and I don't know, boom. Whenever you have a fraction equaling a fraction, you crisscross applesauce called proportions. So 8 sine 50 is going to equal d sine 64. Let's throw this all into our calculator all at once. So I have sine 64 over here. I have sine 64 over here. Cross you out. That gets d all by itself. 8 times sine 50 over sine 64 is 6.8184. So now that I have this guy right here, 6.8184, I can use my area formula, which says half times 2 sides and the sine of the angle in between. So half times 8 times 6.8184 times sine of 66 degrees. When I throw all of that into a graphing calculator or any calculator, I get 24.9157 centimeters squared because it's area and centimeters. All right, there you have it. Find ST. Now, ST is this guy. We'll also call it little r. Now, usually we do the law of sines, but the law of sines says that if you have like 2 angles and a side and you compare things up, then you use the law of sines. However, I don't have that. If you're given 2 sides and you're missing 2 angles, it'll be an absolute nightmare to use the law of sines. So we are going to use what's called the law of cosines. The law of cosines is best used, again, if you have 2 sides and only 1 angle, or if you have all 3 sides and you need to find some missing information about your angles. In this case, I have 2 sides, 1 angle, law of cosines. What is it? C squared equals A squared plus B squared minus 2AB cos big C. So if you're thinking Pythagorean thoughts, you're thinking right. A, B, and C are all sides, and big C is the angle opposite. So this would be like my little c, you would be like my big C, and you can be A or B. It doesn't really matter which is which. My job is to find R, which I'm calling C. So R squared is going to equal, if I call you A and if I call you B, that'll be 12 squared plus 16 squared minus 2 times 12 times 16 times cos 54. The nice thing about all of this is it's all one big terrible calculator problem. And when I throw that into a calculator, I get 174.2905. Am I done? No. In order to get R all by itself, I have to square root everything. And the square root of that terrible number is another terrible number, 13.202. Any units? Nope. But there you have it. Law of cosines is useful when I'm finding a missing side when I only have 1 angle but 2 other sides. Okay? Dunzo. Find the measure of angle R. If I give you a triangle and I give you all three sides and it has nothing to do with a right triangle and you're trying to figure out what your missing angle is, you are going to use the law of cosines. The law of cosines, which says c squared, which is a side, equals another side plus another side, both of those squared, minus 2ab cos big C. Now, what's big C compared to little c? Big C is the angle opposite of this side right here. So in this case, R is my big C. R is my big C, which means I want to make you my little c. I don't care which one's A or B. So when I set this up, I'm going to be doing 28 squared. Again, whatever you have, whatever angle you're looking for, it's equaling that side squared. That's going to equal, it doesn't really matter which one's which, 18 squared plus 12 squared minus 2 times 18 times 12 times cosine of, I don't know. Let's do a little bit of math. 28 squared becomes 784. Let's do both of these. 18 squared plus 12 squared is 468, sorry. Minus 2 times 18 times 12, let's do all of that math right there, and that gets me 432, still attached to cos R. Right now, this is just a gross-looking two-step equation. Subtract 468, that's supposed to be a 6. Subtract 468, cross U out. That gives me 316, John 316. That equals negative 432 cos big R. Not done yet. Divide everything by negative 432. Divide everything by negative 432. That crosses U out. So let me get a different color. Let me move stuff off to the side. I have cos R is going to equal negative, and let me move that over there, negative 0.7361. In order to get R all by itself, I'm going to inverse cosine both sides. Definitely throw that into a calculator. But what you get is the measure of angle R. And the measure of angle R is 137.4 degrees. And now that we're supposed to look at these pictures and say, oh yeah, that looks like it could be right. But yeah, that looks like it could be right. That's a pretty big angle. Pretty big angle. Just like Kurt Angle. He was a wrestler. Look him up. Big dude. Like and subscribe. All right. When I have to solve a triangle, that means find all the missing parts, which means I have to find an angle, I have to find an angle in this case. We know that if I'm given all three sides of a triangle and I have no knowledge of whether it's a right triangle or not, I'm going to use the law of cosine. So let me write that out. Side squared is going to equal a squared plus b squared, which are both sides, minus 2 times those sides times the cosine of the angle opposite of this side right here. What I have to do is I have to do this twice. Okay, so let's go alphabetical order. Let's start out with x. Okay, so if I find x first, I'm going to make sure that I set it equal to 23. Remember, if we're trying to find this angle right here, I want it to equal the opposite side squared. So 23 squared is going to equal the other two sides in no particular order. 25 squared plus 26 squared minus 2 times 25 times 26 times cos, what am I doing? Big X. 23 squared is 529. Let's do both of these. 25 squared plus 26 squared is going to be 1301. Minus 2 times 25 times 26 is 1300 cos big X. Subtract 1301 from both sides. Subtract 1301 from both sides. That gets me negative 772. That's going to equal negative, close one, 1300 cos X. Divide both sides by negative 1300. Divide both sides by negative 1300. And that's going to leave me, let me have myself a little bit of space, 0.5938 is going to equal more space cos X. Why did I leave all of that space? Well, because I have to inverse cosine both sides, and I need the space to write that out. Don't I? That gets me X all alone. And the inverse cosine of that monstrosity right there is another monstrosity, 53.5729 degrees, 0.5729 degrees. So that's X. 53 point, we'll say 6. Okay? I'm allowed to be a little lazy. Fight me. Now I have another one to find. This is still not enough information to find the remaining thing, so what I have to do is I have to find another angle. So let's work with y here. Let's do that next. I'm going to set up my, what is this called? Law of cosines formula, where I'm going to make sure it's 25 equals. So let's see if I can sneak that there. 25 squared is going to equal in no particular order 23 squared plus 26 squared minus 2 times 23 times 26 times cos big Y. 25 squared is 625. If I were to do that whole math problem in one foul swoop, I'll get 1205. That's going to subtract, if I do all that math right there in one foul swoop, 1,196 cos Y. Subtract 1205. Subtract 1205. Cross U out. That gets me negative 580. Equals negative 1196 cos Y. Divide both sides by that number I just said, which I think is a fake made up number. But this number is not fake nor made up. 0.485 is going to equal cos Y. Why did I leave all that space? Because I have to inverse cos again. And when I inverse cos again, that gets me Y is equal to 61.9875. So I'll call you, which one was that? Y 60, I can round that to 62 degrees. Now, if I were to use some common sense, which is what I'm going to do, and a new marker, I could find Z, but just by doing 180 minus 62 minus 53.6. And when I do that, that gives me an angle Z measurement of 64.4 degrees. So after all of that, I've solved my triangle. Thank you for joining me in this journey for solving triangles. If only I could solve my life. Like and subscribe. Find the area of this triangle right here. Usually with the area of a triangle, I'm trying to find like a right triangle, try to find the height so I could do half a base times height. Not happening here. I don't know if that's a right triangle. Pretty sure it's not. And usually when we see three sides, we're thinking cosine thoughts. But this is asking for area. So we did a problem a couple videos ago where I was able to use like a law of sines hybrid thing to find the area. There's no like law of cosines version of that. So I'm going to have to use that exact same area formula, which said half times a side times a side times the sine of the angle in between. So I have a side and I have a side, but I have no angles. So let's do this. Let's use the letters that we have. A, B, I just have to find C. Now, what we can do is we can use the law of cosines to find that missing angle C, throw it into that formula right there, and I'm donezo funzo. So here's the law of cosines formula. And I'll use little c since I already labeled as much as I could here. C squared is going to equal a squared plus b squared minus 2ab cosine big C. So let's plug in what I have. 9 squared, that's going to equal 15 squared plus 13.8. It has to be a decimal. Minus 2 times 15 times 13.8 cos C. You become 81. Let's do some math here. Let's do some calculator math. That guy becomes 415.44 minus, let's multiply these three numbers together, 414 cos C. All right, let's subtract both sides by 415.44 minus 415.44, cross U out. 81 minus 415.44 is, of course, negative 304.44. I have all these numbers memorized, and I'm not looking at a piece of paper. That's going to equal negative 414 cos C. Let's get rid of negative 414 by dividing it out. And again, let me just do this off the cuff. That gives me negative positive 0. Let me give myself some space. 0.8078 is going to equal more space cos C. Why all the space, you ask? Well, because I have to inverse cosine both sides, and I need that space to write it out. Don't I? Don't I? But what that does is that gives me an angle measurement of, let me see off the top of my head, 36.1185. Duh. So now I have everything I need. And all I have to do is just throw it into that formula right there, and I get myself an area. The area is 1/2. That's already called A, so let's keep it consistent. That's already called B, so, consistent. Cosine C, which is 316.1185. I probably could have skipped this step right here and jumped right to that, but you know what? It's too late. I did it and I'm done. Area is going to end up equaling, let me do it all off the top of my head, 61.0088 yards squared. Ooh, boy. Trigonometry, baby. So much fun. All right, graph x equals t, where also y equals t squared over 4. This is called a parametric equation. And what you do with parametric equations is it tells you what x is, it tells you what y is. So let's pick a bunch of t's and plug them in and see what it looks like in the end. So I'm going to make a table like so. I'm going to pick a bunch of t's, get a bunch of x's and a bunch of y's, and that's going to give me points to graph. I'm going to use -4 and then work my way up. So -4, -3, -2, -1, 0, 1, 2, 3, 4. Why I chose those numbers, I don't know. But I guess we'll see if it works out. If x is t, then that makes this left side pretty easy. X is t means x is -4, x is -3, x is -2, x is -1. You get the idea. You get the idea. Okay. Here the math is a little bit more complicated, but it's nothing to lose sleep over. T is -4. -4 squared is 16. Positive 16. 16 over 4 is positive 4. Okay, not bad. -3 squared is positive 9. 9 divided by 4 is 9/4, but if I'm going to graph that, I kind of want to view that as 2.25. Okay, -2 squared is 4. 4 over 4 is 1. -1 squared is 1. 1 over 4 is 1/4, so I'm going to view that as 0.25, especially since I'm going to graph it. 0 squared is 0. 0 divided by 4 is 0. 1 squared is 1. 1 over 4 is 0.25 again. 1, I already did that. 2 squared is 4. 4 over 4 is 1 again. 3 squared is 9. 9 over 4 is 2.25 again. 4 squared is a fun game, is 16. 16 over 4 is 4 again. And we see some parabola-y looking stuff. So let's graph things and label what we did as we graph them. Let's use a different color. Use purple. All right, here's my points. Here are my XY values. So you're dead to me now. So one of my points is -4, +4, and that happened when t equaled -4. Another one of my points is -3, 2.25. So -3, 2.25. So we'll sneak that there, and that happened when t was -3. Another point was -2, 1 right here, and that happened when t was -2. Another point was -1 1/4 right there. That happened when t was -1. 0, 0, that happened when t was 0. 1/4 happened when t was 1. 2, 1 happened when t was 2. 3, 2.25 happened when t was 3. And last but not least, 4, 4 happened when t was 4. So here's my parabola. There it is. That looks awful. That looks better. So let's clean that up. All right. Let me see if it lets me do it. Now, the thing with parametric functions, getting ahead of myself, this is parabolic, so I didn't technically say anything wrong, is we also care about the direction from least to greatest. So we're going to put little arrows saying that this guy went that way as t got larger. Yeah. So there you go. Look at that. Look at that. Cute. Fun. Parametric equations. Let's graph this parametric equation where x is 5 sine t and y is 4 cos t. Not to be confused with Ashanti, rest in peace. Whenever you graph a parametric equation, you should make a chart of t, x, y values. Now, the t's that we're going to choose, I know I'm going to choose clever ones because I'm going to eventually plug them into here and hope to take the sine and the cosine of it. So let's use all the quarters of t from 0 to pi. Maybe not even including pi. Let's just go from there. So let's start out, we're going to choose 0. We're going to choose 1/4 of a pi. We're going to choose 2/4 of a pi. So that's going to be pi over 2. We're going to choose 3/4 of a pi. And I'm actually going to go all the way around to 2 pi because I think we should do 2 pi. I think we should do a complete circle. All right. So I'll plug in pi. I'll plug in 5/4 of a pi. I'll plug in, what's next? 3 pi over 2. I'll plug in 7 pi over 4. And that should get me where I need to be. All right. I'm just letting you know ahead of time, I'm using a calculator for all this. So when I use these numbers, when I plug in 5 sine t, I'm plugging in 5 sine 0, which gets me 0. When I plug 5 sine pi over 4, that gets me 3.5. It gets me a much worse number than that. But again, if I'm going to just graph on here, it really doesn't matter what the exact numbers are as long as I'm graphing for accuracy. When I plug in pi over 2, I get 5 because sine of pi over 2 is 1. 5 times that is 5. When I plug this in, I get 3.5 again. When I plug in pi, I get 0 because sine of pi is 0. When I plug this in, I get negative 3.5. When I plug in 3 pi over 2, I get negative 5. And when I plug in 7 pi over 4, I get negative 3.5. So those are my x values. Okay, here, here, here. It's just everywhere. I'm going to plug these into the y function. I'm again using my calculator. I'm going to get terrible numbers and then just simplify it to, or round it rather, to the nearest tenth. When I plug in 0, I end up with 4 because cos 0 is 1. 1 times 4 is 4. When I plug in pi over 4, I end up with 2.8, which is a much worse number. But again, I'm not going to lose sleep over that. Cosine of pi over 2 is 0, so 4 times it is also 0. When I plug in 3 pi over 4, multiply it by 4, I get negative 2.8. When I plug in pi, I get negative 1. 4 times that is negative 4. When I plug this in, multiply it to 4, I get negative 2.8 rather. Plug in regular 3 pi over 2, I get 0. And when I plug in 7 pi over 2, I get 2.8. Gross. All right. Let's graph these. And as I graph them, I'm going to say where my t was. So 0, 4 lives around here. T was 0 for this one. 3.5 lives here-ish. 2.8 lives here-ish. And t was pi over 4 for that one. Okay, the next point is 5, 0. And that was t is pi over 2. The next point is 3.5, negative 2.8. So like right around there. That's when t was 3 pi over 4. What's the next one? 0, negative 4. That's when t was pi. Negative 3.5, negative 3.5 right around there, negative 2.8 right around there. That's when t was 5 pi over 4. Negative 5, 0, negative 5, 0. That's when t was 3 pi over 2. And negative 3.5 lives right around there. Up 2.8 lives right around there. That's when t was 7 pi over 4. So we got ourselves kind of like an oval-looking thing, an ellipse. Okay? So I'm going to try my best to draw this the best that I can. After I draw it, I'll get an oval ellipsy looking thing. And of course, we always include the directions that we go in. And again, if you're like, well, why did you stop at this number and not go to 2 pi? Because 0 is 2 pi, and why repeat myself? And as you can see, it kind of goes around in a circle. Circular, circle. What's a movie? I forget which one. I think it's Billy Madison. Like and subscribe. A soccer ball is kicked across a field at an angle of 30 degrees with an initial speed of 16 meters per second. Write a set of parametric equations for the motion of the soccer ball. All right, generally speaking, parametric equations are x equals stuff, y equals stuff. There's a rule that says if you're dealing with initial speed problems, the x equation is going to be the initial speed times cosine theta times t, and y is going to be completely based off of like the gravity function, which is negative 16t squared plus the initial speed sine theta t. If I started at a specific height, I would add h, but I'm not doing that here. My x value is going to be the initial speed, which is 16, cos theta, which is 30 degrees. All of that times t. I'm going to take this guy, figure out what this is. So let me see. Cos theta is root 3 over 2. I have to think about that for a second. 16 over 2 is going to be 8. So 8 root 3 t is going to be my guy. Some people might want you to say 8t root 3, but I'm not going to lose sleep over that. This guy, a little more involved, but not the end of the world. Y is going to equal negative 16t squared plus my initial speed, which is 16 again, sine theta, which is going to be sine 30 degrees. Again, t is attached. Sine 30 degrees is a half. So y is going to equal negative 16t squared plus 16 times a half times t, which ends up simplifying out to negative 16 t squared plus 8t. Those are my parametric equations. Fun. Graph each polar coordinate. When you graph a polar coordinate, the first number that you see tells you the length, like a radius. And the second one tells you where around your polar plane, try saying that fast, you're going to end up putting your point. So this guy is basically saying my point is going to be 3 units away from the center, and I'm going to place that at 150. So where's 150? There you is, 1, 2, 3. That's going to be my first point that I'm going to make in blue. The second guy that I'm going to make in green is going to be 2 units away, but it's going to happen at negative 255. Well, what's negative 255? I don't know. So let's add 360 to it to spin it around. When I add 360 to it, that changes this to 105 degrees. So I look for 105 degrees. That's halfway in between 90 and 20. I'm going to put a dot that's 2 units away, and that's going to be that point right there. All right, so that's how you graph polar coordinates when given degrees. Not so bad. Let's graph polar coordinates in radians. Oh, I can barely contain myself. Polar bear. So the first number in a polar coordinate tells you how far away from the origin your point is going to go. This tells you where on the polar axis you're going to put your polar coordinate. 11 pi over 6, you might be looking at this and saying, oh, there you are. 3 is going to be, what, 1, 2, 3 units away. So right there, yep, it's as simple as that. So that's your first one. And I'll make you red. Now, negative 3. Kind of weird. You're like, you can't make something -3 away. Sure you can. That's just going to mean backwards. Yeah, backwards. All right, so first let's find out where 23 over pi, or 23 pi over 12 is. Well, there's no 23 pi over 12. But if you think logically, 23 pi over 12 would be right here, if you think logically. So if it's going to be 1, 2, 3, that's where I would put my dot. But since this is going to be negative, it's going to be 1, 2, 3, which is going to live right there. Okay? So that's how you graph polar coordinates in radians. Super cool. Because it's polar. Polar means cold. Like and subscribe. Find the distance between these two polar coordinates right here. All right, before we do too much, let's try to draw these out in a very, 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 very basic way. So I'm drawing myself a polar plane, not pretty at all. There's pi, there's 0, yada, 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 yada. Pi over 3 would be somewhere around here. So let's just say that, this is 2. They're both 2, so that makes life a little easy. But you're going to be 2 pi over 3. So this measurement is pi over 3 degrees away, in radians rather, radians away from 0. Not too hard to understand. This guy is going to exist at 11 pi over 6, which is somewhere over here. Now, 11 pi over 6, if this is 11 pi over 6, implies that this is 1 pi over 6 units away from 0. So if I want to find this distance, what I'm looking at is I'm looking at a triangle where I need to find out what this angle is right here. So pi over 3 plus pi over 6 means I could change that into 2 pi over 6, 2 pi over 6 plus 1 pi over 6 plus is a cool 3 pi over 6 or pi over 2. So you are pi over 2. I know that you're 2, and I know that you're 2. So what I'm going to do is I'm going to bring back an old friend, and that old friend says, how can you find an opposite side if I give you an angle and I give you 2 sides? Well, that would be the law of cosines, of course. Law of cosines, c squared equals a squared plus b squared minus 2ab cos c. What do I know? I know that I need to find c. C squared equals 2 squared plus 2 squared minus 2 times 2 times 2 times cos pi over 2. Here's a nice thing. Cos pi over 2 is 0. You go away. So c squared is equal to 4 plus 4, which is 8. Square root both sides. And c is going to equal 2 times 2 times 2, 2 root 2. So some of you might have noticed right off the bat, isn't pi over 2 90 degrees? Yeah. So isn't this a right triangle? Yeah. So couldn't have used Pythagorean theorem? Yeah. But I didn't because I just wanted to show you law of cosines anyway because it's fun. All these 2's, 2 2's, where am I, at a ballet recital? Graph r equals 6 sine 3 theta, where theta is in between 0 and pi. Polar graphs are gorgeous. They're the most beautiful graphs that you see in math. They're also a nightmare to create. And the reason why they're a nightmare to create is because you have to put all these points all over the place, but when you finally connect things together, it just looks so very good. So what I'm going to do is I'm going to use these bounds right here between 0 and pi, whatever that is. I'm going to use every single one of these numbers right here so I can get myself as complete of a graph as possible. Now, just a heads up, I am going to use a calculator to get my numbers. You could do this without a calculator. It's possible, but I don't have a death wish, and so I'm not going to do it. Now, what I'm going to do is plug in all these thetas. What I'm not going to do is plug that right into a graphing calculator and try to trace this out, whatever it is. I'm going to be accurate but cheat a little bit, just a little bit. So I'm going to use all of these values from between 0 and pi and see what happens. So I'm going to plug in. I actually might need 2 rows of this. I actually might need 2 graphs. So let me make another one. All right. So I'm going to plug in 0. I'm going to plug in pi over 12. I'm going to plug in pi over 6. I'm going to plug in pi over 4. I'm going to plug in pi over 3. I'm going to plug in 5 pi over 12 and pi over 2. Like that. And then when I'm done that, I'm going to also plug in 7 pi over 12. I'm going to plug in 12. I did that right. I'm going to plug in 2 pi over 3. I'm going to plug in 3 pi over 4. I'm going to plug in pi over 11 pi over 12, and just to have some fun, I'm going to plug in pi, even though I'm not supposed to. I'm doing it anyway. You can't stop me. So when I plug these into a graphing calculator or a scientific calculator or whatever, I'm not going to worry too much about the square roots and the blahs. I'm just going to do it. All right. Sine of 0 is 0, so this becomes 0. This becomes 4.2 when I plug all that into my calculator. U becomes 6. Oh, look, 4.2 again. How about that? I wonder if that's going to continue being a pattern. I don't know. I guess we'll find out. U becomes 0. And you become, oh, weird, negative 4.2. How strange how all of this repeats. U become negative 6. Let me switch my color. U becomes 7 pi over 2, negative 4.2. U becomes 0, U become 4.2, U become 6, U become 4.2, and U, even though you don't really matter, becomes 0. Now, the fun part about this is graphing all those points and making sure you don't screw up. So let's do that. 0, 0 means I start at 0 and I haven't moved anywhere. Okay, I can handle that. Pi over 12 is this guy. 4.2 is going to be like here, so I'll put a dot like right there. Pi over 6, 6 is going to be that guy right there. The next one up, pi over 4, is going to be 4.2. What's next? Pi over 3 is going to be 0 again. Okay. 5 pi over 12 is going to be negative 4.2. So if regular 4.2 would be here, then I'm going to follow the line and make sure it's at negative 4.2, which is that guy right there. Half a pi is going to be negative 6, so negative 6 is that dot. Here we are on this one. 7 pi over 2 is going to be negative 4.2, so that guy right there. 3/4 of a pi over 4 is, oh, I forgot one. 2 pi over 3 is going to be 0, so that one right there. 2 pi over 3 is going to be 0, so again, I'm repeating myself. 5 pi, or no, I missed one. 3/4 of pi is going to be 4.2 in the positive range. And so where was 4? There was 4, 3/4 of a pi, 4.2. Then 5 pi over 6 is going to be 6, so u. And then 11 pi over 12 is going to be 4.2. And back to 0, not that it even matters. So now I need to find a way to draw this, and this is where I'm afraid I'm going to fail, but we'll see what happens. Okay, this is a pretty looking thing. Now you see that I'm trying to make the motions of it. Okay, this is a polar graph that's going to start at 0, 0, make this pretty little loop there. Okay, keep coming down. Keep dumbing down. Oh, Dr. Freud. That actually looks really good. And then come over here. And there you go. This creates what's called a rose, or as Rick Ross would say, rosé, because he's a rapper. I don't know what it means, but he said it, so that's how you graph a polar graph. Pretty cool stuff. Pretty fun stuff. Pretty beautiful stuff. I like it. Convert from polar to rectangular form. We know what polar is. Polar turns these things into pretty little roses and hearts and stuff like that. Well, rectangular form is just the regular y equals blah, blah, blah. In order to do that, what we have to do is we have to use these three things. We have to say that x equals r cos theta. That's thing number one. We have to say that y equals r sine theta. It's supposed to be an n. That's thing number two. And we have to say that r squared equals x squared plus y squared. So in order for us to make this look like stuff with x's and y's, first thing we need to do is why don't we turn that r into r squared? Let's multiply it by r. If I multiply the left by r, I have to multiply the right by r. So the left is now r squared, and we'll change that in a little bit. Distributive property puts that r right after the 4. So 4, oh, look at that, r cos theta. Minus r times 4. Oh, r sine theta. Now we have enough information where we can start swapping things around. R squared is now x squared plus y squared. R cos theta is now x. R sine theta is now y. Now, maybe we could leave it like this, and maybe some teachers would be happy with this, but I'm not really happy with this. I'm not happy at all. What I want to do is I want to make it look a lot prettier. So I'm going to move everything to the left. I'm going to subtract 4x from both sides, minus 4x, and I'm going to add 4y to both sides, plus 4y. Let me get some colors out here. That gets me x squared minus 4x, leave some space, y squared plus 4y, leave some space, equals 0. Now, what I want to do is I want to make this look like something squared, x something squared. And I want to do the same thing with that. My goodness gracious. I want to do the same thing with that, but with a y squared. How do I do that? Well, difference of squares, of course. Take half of this number, square it, and add it to both sides. So half of 4 is negative 2. Square that is positive 4. So let's add 4 to both sides. Same thing over here. This is supposed to have a y attached to it, and I simply forgot. Same thing over here. Take half of 4, 2. Square that 4, and add 4 to both sides. What we have here is we have a perfect square trinomial that factors out to x minus 2 squared. Oh, what do we have here? A perfect square trinomial that factors out to y plus 2 squared. And what do we have over here? 8. So now it's in rectangular form, and it's a pretty version of rectangular form. That's what I like. That's what I want. And that's what I'm sticking with. Let's graph this point on the imaginary plane. So I is a real number. 3 has the imaginary number complex. So go right 1, go up 3. Thanks for watching. Like and subscribe. Simplify 4 plus 4i, 5 minus 3i, FOIL, and imaginary numbers. I love imaginary numbers. You know that imaginary number is the square root of -1, but there's also some repetition going on here. I squared means I would be allowed to square a square root, which just gets me -1. I to the third, if I ever come to that, would be -1 times I, so negative I. And I to the fourth would be this guy to the fourth power, which is 1. And then everything just repeats itself. So what I'm going to do is I'm going to FOIL. So 4 times 5 is 20. 4 times -3i is -12i. 4i times 5 is 20i. And 4i times -3i is -12i squared. Let's turn any of these I squareds, I cubes, or I to the fourths into something different. And while we're at it, let's combine these guys. So you become 20 still. You simplify to 8i. And -12i squared becomes -12 times -1. -12 times -1 is 12. 12 plus 20 is 32. 32 plus 8i is my simplified version of that FOILed problem. Now it's a complex number, and it's a pretty complex number. All right, my job is to simplify 6 minus 2i, 2 plus 4i. And you might be looking at this and thinking, well, okay, there's a 2 in common, so let's take care of that. So let's bring out a 2. That's 3 minus I over 2. That's 1 plus 2i. Cross you out, and you now have 3 minus I over 1 plus 2i. And you might look at that and be like, done. We're not done. There's an issue here. I is the square root of -1. And last time I checked, you can't have square roots in the denominator of a fraction. So the way we're going to handle this is we're going to multiply the top and the bottom by what's called the conjugate. This is basically a difference of squares problem that eliminates all possibilities of having square roots or i's on the bottom. So the conjugate is whatever the bottom is, but flip the middle symbol. So 1 minus 2i, 1 minus 2i, multiply the top and the bottom by that. So we have a FOIL problem upstairs. We have a FOIL problem downstairs. But the FOIL problem downstairs is going to make us happy. Upstairs we have 3 times 1. We have 3 times -2i, so minus 6i. We have -1 times I, so -I. And we have -1 or -i times -2i, which is positive 2i squared. That's going to be all over. 1 times 1, which is 1. Minus 2i plus 2i disappears. That's supposed to happen. Minus 4i squared. So let's combine the two like terms upstairs in the numerator. So 3 doesn't change yet. This becomes -7i. And 2i squared, remember, I squared is the same thing as -1. So 2i squared is the same thing as 2 times -1, which is the same thing as -2. So that'll simplify. Similarly, on the bottom, we have 4i squared, which is the same thing as 4 times -1. So that becomes plus 4. On the top, these combine to 1. So 1 plus 7i. On the bottom, this just turns into a 5. And some teachers want you to split this up and say this is 1/5 plus 7 over 5i. So now it's in the appropriate imaginary complex form. But that's our guy. Now I, or a square root, is no longer in the denominator. Everything's the way it should be, and that's my answer. -1 minus 6i cubed. All right, let's write this all out. -1 minus 6i, -1 minus 6i, -1 minus 6i. Let's remind ourselves that I is just I, this -1 inside of a square root. I squared turns into -1. I cubed turns into -I. I don't think we're going to have to deal with any more than that. Let's FOIL. I know some of you might be like, well, can't we use some kind of shortcut? We can, but I won't because I don't have everything memorized. -1 times -1 is going to be +1. -1 times -6i is going to be +6i. +6i again. +36i squared. I'll change that in a little bit. That's going to be multiplied to -1 minus 6i. These two combine to make 12i. While I'm at it, 1 plus 36i squared combines because I squared is -1. So I squared becomes -1, which makes this -36. 1 minus 36 is -35. So -35 plus 12i times -1 minus 6i. Let's FOIL again. 35 plus 210i minus 12i minus 72i squared? Yes, 72i squared. Let's combine these. That becomes 208i. Nope, just kidding. 198i. That becomes plus 72 and 75. Oh my gosh, 35 plus 72 is 107. Now it's in complex form. Now it's completely simplified. Now it's beautiful. The end. Write in component form. This is a vector, like from Minions or Despicable Me or whatever train wreck that was. A vector is basically an arrow that's defined by the direction that it's going and how long that arrow is. The length of the arrow is called magnitude. Okay. Component form looks like this. It looks like a point, and in a way it kind of is. This basically says, let's just pretend we don't care where this arrow started from, but it goes x units to the right and y units up. If x is left, then it's negative, and if y is negative, then it goes down. So if we have an arrow that goes like this, we can expect to have an xy of positive negative because it goes right and down. Now, the way we find this is r is my starting point for this vector. So we are going to call r, that's a p, so we're going to call r x sub 1, y sub 1. And we're going to call s, which is the arrow, x sub 2, y sub 2. So in order to make this look like this, we are going to use this formula right here. In this case, we're looking for rs in component form. This is not like a formula that you'll find like on the internet, although I'm sure many websites would have it. This is just how I decided to do it. Okay, the x value comes first, x sub 2 minus x sub 1, comma, y sub 2 minus y sub 1. In this case, x sub 2 is 8 minus x sub 1 is -3, so we have a double negative. Deal with that in a moment. Y sub 2 is -1 minus y sub 1 is 9. Do a little bit of simplifying. Double negative makes that a positive. You have 11. -1 minus 9 is 10. -10. And that's my guy. And you can kind of see it here. This goes right 11 spaces, down 10 spaces. That's my vector in component form. The end. I am to write this vector in component form. Remember, component form looks like this. It looks like a point, and this point tells you how many units to the right my arrow is going and how many units up my arrow is going, and negative means the opposite direction. Now, this gives me something that looks like polar coordinates. It gives me a magnitude, which means a length of 52, and a direction of 174. So if I'm looking at this as if this is something written in polar coordinates, I would have that. Okay, I would have a vector that looks like that. So we should expect a pretty big x value and a not so big y value. So how do we do this? How do we find x and y? Well, we kind of remind ourselves about polar stuff, and we use the fact that x equals r cos theta. That's my theta. Nope, that's my theta. That's my r. And y is going to equal r sine theta. So x is going to equal 52 cos 174 degrees. Y is going to equal 52 sine 174 degrees. This is definitely a calculator exercise. I'm not going to pretend like I'm even going to do this in my head. When you type this all into a calculator, the x value that you get is negative 51.7151. And the y value that you get is 5.435. Again, these numbers kind of make sense. This line is 52, and it's pretty low. It's pretty close to the x-axis. So it's going to go 51-ish to the left and only about 5 up, and that's going to be how I get to the end of that vector. But there you have it. Draw a diagram and find the magnitude of this guy right here. All right. I don't know why I have to find the magnitude. I already have the magnitude. That's my magnitude. Maybe I'm just supposed to draw the diagram. I don't know, but let's go above and beyond. This is me drawing a diagram. Okay, here's 0, here's 90 degrees, here's 180 degrees, 180 degrees. 230 degrees is 50 more than 180. 50 degrees more than 180. And we could say that the length here is 15. So that's my magnitude. Let's double check that, though, using some knowledge that we have based off of components. I know r squared, okay, is going to equal x squared plus y squared, which means r is going to equal the square root. X is the same as r cos theta, not rose theta. That would be a prickly mistake. Squared. Plus r sine theta squared. R is 15. Cosine 230 squared plus 15 sine 230. Close it, squared, move that over. This ends up being 92.965. This ends up being 132.035 gross. Okay, those two numbers coincidentally add up to 225, and the square root of 225 is 15. So, the magnitude is the distance of my radius. That's what the R stands for. So the fact that it gave it to us like that and asked me to find the magnitude, I'm not sure. Sometimes I wonder when I make these problems, I copy and paste them off of other things, and I wonder if I copy and pasted it wrong. But at the very least, we kind of did a nice little proof to find out that I was right. And we drew a diagram, which is part one of what we had to do. So, everybody wins. Unless you hate square roots, in which case you lose. Find the magnitude and the direction angle of this vertex in component form. All right, I need to find the magnitude and I need to find the direction angle. Let's draw ourselves a very basic diagram of what we're dealing with. Okay, I'm doing Q3, quadrant 3, because this is basically saying if I were to start at the origin, go left 8 and down 41, that's going to be what I have. So this right here is the magnitude. Okay, in order to get to the end here, I go left 8 and I go down 41. Now, what I tried to make there, and I did poorly, so I'm going to do it again. What I tried to make there was a triangle. That's much better. I need to find this missing side. Not only do I need to find this side, I need to find this angle here, and of course do a little bit extra with that, but let's focus on the magnitude first. Okay, if I were to take that right triangle and pull it off to the side and say that you're 8 and you're 41, I'll call you C and do Pythagorean theorem to find the length of that hypotenuse-looking thing. So I have 8 squared plus 41 squared is equal to C squared. Square root everything, and that gives me C equals 41.773. So that's my magnitude. My magnitude, R, is 41.773. Now what I have to do is I have to find that blue angle right there. If I were to look at this blue angle and compare 8 and 41 to it, 8 is adjacent to the blue angle and 41 is opposite. So we need TOA, which means the tangent of that blue angle is going to equal the opposite side, 41, over the adjacent side, 8. So let me actually give myself a little bit more space. You'll see why. 41 over 8. To get that theta all by itself, we inverse tangent. So inverse tan. Theta is going to end up equaling 78.96 degrees. However, I'm not done. That angle is 78.96. I want all of this, which means I have to add 180 to it. And when I add 180 to it, the resulting angle is going to be 258.96 degrees. Ooh, close to 98.6 degrees, which is average body heat. Like and subscribe. Sketch a graph and find the magnitude and the direction angle of 5i minus 12j. Is that I the same as the imaginary number I? Nope, not at all. I basically means that this many units in the x-axis direction, and j means that many units in the j direction. So, or the y-axis direction. So, I don't have near enough space. So why don't I go by 5s for these 5, 10, 15, 20. You'll be -5. You'll be -10. You'll be -15. If this is going 5 in the positive direction, I'm going to go over here. 12 in the negative direction has me ending up somewhere around here. So the picture that I get is going to, boy, that's awful, 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 awful. The picture that I'm going to get is going to end up looking something like that. Now, what does all this mean? What does all this mean? Well, first off, went right 5, went down 12, gives me a picture where I can imagine a triangle that goes right 5, down 12. I have to find the magnitude, so let's do that first. Let's call you C. Okay, so this is Pythagorean theorem. 12 squared plus 5 squared equals C squared. 144 plus 25 equals C squared. 169 equals C squared, square root it, and C equals 13. So the magnitude is going to be 13. What I don't have is the direction angle. Now what I'm going to do is I'm going to find that angle in blue right there. Now, let's just say that I get 50, which I don't, but let's just say that I get 50. Does that mean my answer is 50? No, not at all. That means my answer is going to be 50 plus 90 plus 90 plus 90 plus 270 total, because my direction angle is going to have to be like 200 or 300 something, because it's going in that direction. So what I need to do now is I have theta. 12 and 5 compared to theta are my adjacent sides and my opposite sides. So I'm thinking SOHCAHTOA thoughts, which means that the tangent of my theta is going to equal the opposite, which is 5, over the adjacent, which is 12. Didn't leave myself enough space at all. So let's just inverse tangent both sides. I know that looks very sloppy, but I'm not going to rewrite it. Inverse tangent both sides, so that crosses out. Theta equals the inverse tangent of 5 over 12, which is 22.62. So this guy right here is 22.62. I have to add 270 degrees because 90, 90, 90. And when I add 270 degrees, that gives me a direction angle of 292.62 degrees. And that, ladies and gentlemen, is my magnitude and my direction angle. Cool! Write the component form of the resultant vector. What this is basically saying is U is going to look something like this. Let's multiply -3 to it, which means you flip it, do it again, and do it again. How long is this? Now 3 times because it's 3, and flip it because it's opposite. So the way that I answer this is I multiply -3 to the regular component form of the vector, and that gives me -60, +63. And if you're like, that's it? That's all we have to do? Yeah, that's it. Yeah, that's all you have to do. And that's kind of a picture of what we got. Pretty easy. Find the component form of the resultant vector. If I give you tx, they're points, yz, they're also points, and I need to multiply 4 to tx and add yz to that. Well, first off, we need to find the vector tx in component form. Okay, the quick way of doing this is you take 3, you subtract -3, so 3 minus -3 is 6. Okay, this gives us the fact that I'm going from -3 to +3, so that's 6 units total. 10 minus 8 is 2. YZ is going to be -8 minus -4. That would change things. -8 minus -4 is -8 plus 4, so -4. And -10 minus -7, which is -3. Okay, I have a video on turning points into component form. If you're like, he went way too fast for that, I understand. But, I offer no apology. Now, what we're doing here by adding these two up is Tx is 6, 2, which means looks something like this. So if I take 4 of them, 1, 2, 3, 4, and then if I were to go from there, so this is 4Tx, if I were to go from there and go in the direction of YZ, which is -4, -3, go here, so this is YZ. Again, my picture is not going to be perfect. What's the resultant vector if I just went from the very beginning to the very end? Okay, what's this going to be? Well, what you do is you take 4, you multiply Tx to it in component form, which is 6, 2, and then you add Yz to it. 4 times 6, 2 is going to be 24, 8, plus -4, -3, ends up being 20 and 5. So if I were to be like, Tx is this way, but you need 4 of them, then go Yz. And if someone's like, I'm just going to go from the very start to the very end, the very start from the very end is right 20 up 5. Dunzo. Find the magnitude and direction angle of the resultant vector. Resultant vector means you're going to take, a vector or two or more and add, subtract, multiply, do stuff to it to get an answer. Resultant vector. In this case, we're taking A and B, and we're multiplying -3 to A, and we're subtracting 7 times B. Let's find out what that is first. So -3A is going to look like this, and then we're going to do -7 times B, which is going to look like this. Okay, multiply. Whenever you have component form, just multiply. That becomes 9. That becomes 36. Same thing again, multiply positive. That becomes, I'll throw negatives in there, -28, -63. And then when you add these guys up together, you get -19, I think, and -27. All right. Let's get a nice little visual going. Okay, -19, -27 means in order to draw this picture out, you go left 19, you go down 27, and then you have something that looks like this. Now, fig number 1 is you went left 19, you went down 27, so I have myself a Pythagorean theorem-ish type problem, which that's how I'm going to do this first part. But I'm going to use more of this formula now. I'm going to move away from a squared plus b squared equals c squared and move more towards the radius version of it, which it's the same thing. In fact, it's not going to be by saying it's the same thing, I actually started writing out the same thing, which is the opposite of what I wanted to do. R equals the square root of x squared plus y squared. You've seen that. So in order to find the magnitude R is going to equal the square root of 19. Actually, we'll put -19 just to prove the point that this becomes positive. We're going to be consistent. And -27 squared. I'm going to do this mentally and not use a calculator and find out that this becomes 33.015. Big brain. Now, what I have to do is I have to find also the direction angle. Now, if this is a coordinate plane, I've got 90 up here, I've got another 90 here, and I care about that theta. I need to find theta and then add 180 degrees to it. So I do know that tangent theta equals the opposite over the adjacent. So 27 over 19. In order to get theta all by itself, we're going to inverse tan, which means you stay in the shadows. Get it? And that gives me a theta of 54.865. Did that in my head too. Now that's just this part here. In order to get the direction angle, I have to include the fact that it starts over on the right side of the x-axis and winds its way around counterclockwise. So 180 plus this is going to give me 234.865 degrees. So that's my direction angle. This is my magnitude. And that's the problem. Dunzo. Find the dot product of the given vectors. So I have u and v. So dot product looks like this. U times v is found by doing the x value in u times the x value in v plus the y value in u times the y value in v. So the x value in u is 3. The x value in v is 6. Plus the y value in u is 9. And the y value in v is 5. 18, 45, 63. It's my dot product, baby. Find the dot product of the given vectors. All right, we have a picture, which is unnecessary because when you find the dot product, what you do is you multiply the x values, so 8 times negative 7, add the product of the y values, so 4 times negative 9. This gives me negative 56. This gives me negative 36. This gives me negative 92. And that's that. State if the two vectors are parallel, orthogonal, which means perpendicular, or neither. So basically what I'm looking at, if I were to look at a picture of this, okay, if I were to look at a picture of this, whenever I'm given the form where I have i's and j's, this basically just means left 5, down 2, so I would have something that looks like this. This guy means left 10, up 25, so I would have something that's going to go way off the rails but looks like that. Okay. Now it looks, based off of the picture that I created, that it looks pretty orthogonal to me. Okay, but that's not good enough. Let's use a little bit of common sense here. Okay, u, vector u, is given to us by the fact that we go left 5 units, down j 2 units for j. I'm going to find the slope. I'm going to call it m sub u. Okay, the slope is the change in the y values over the change in the x values. Okay, if I'm going left 5, then my change in the x value is left 5. And if I'm going down 2, then my change in the y values is down 2, and that gives me a slope of 2 over 5. So the slope of this guy right here is 2 over 5, up 2 over 5, up 2 over 5, yada, yada, yada. Now, if I were to do the same thing with v, and I'm not going to write it out, there's v right there. If I were to say mv is the change in y values over the change in x values, the change in y values is positive 25. The change in x values is negative 10. That simplifies to negative 5 over 2. So when you look at the two slopes, 2 over 5 and negative 5 over 2, they're negative reciprocals of each other. Flip them, make one of them positive, make the other one negative. They're negative reciprocals, which tells me that these two lines are perpendicular, or in vector terms, orthogonal. Not to be confused with orthodontist, who fixes your teeth. Like and subscribe. Find the measure of the angle between these two vectors, 3, 6, 3, negative 8. The way to do this is you use dot product and use this formula right here. Cosine theta is going to equal the dot product of A and B, A being one of these guys, B being the other one, and then you find the magnitude of A and multiply that to the magnitude of B. Okay, so let's do everything one step at a time. The dot product of A and B means you multiply the x values, 9, add, multiply the y values, so 6 times negative 8 is negative 48. And so the dot product ends up being negative 39. The magnitude of A and B, we're going to use this formula right here, which is basically, something somebody stole, and I keep doing this, I always do this, but somebody stole the Pythagorean theorem. I should have used x and y, but, too late. But if I'm doing the magnitude of A, and I believe I called this one A, not that it matters, it's going to be positive 3 squared plus 6 squared. Type all that into a calculator and you get 6.708. To find B, which I'm calling that B, I'm going to use this formula again, square root of 3 squared plus negative 8 in parentheses squared. Type that into a calculator and get 8.544. Now that I know all this, I can plug it into that formula. So cos theta is going to equal negative 39 over 6.708 times 8.544. That terrible, terrible, terrible number ends up being negative 0.680472. How did you do that, sir? I did it in my head. No, I didn't. I have it written down. Let's inverse cosine. Let's inverse cosine. And my final guy is going to be 132.881 degrees. Fantastic. Find the projection of U onto V. I'm not even going to attempt drawing what projection means, but it kind of is like draw this guy and draw that guy and have it extend, and it's just terrible. So I'm not even going to attempt it. But we do have a formula for projection, and the formula for projection is this. Projection of U onto V is going to be the dot product of U and V over the magnitude of V, square that, and then multiply the whole thing by V. Okay, so first things first, let's find out what the dot product of U and V is. So 8 times negative 7 plus 2 times negative 3 ends up being negative 56, negative 62. So there's the top part. There's my dot product. Magnitude is going to be found by using this guy. Use this a lot. So I care about V, and I care about squaring it. So the magnitude of V squared is going to be the same as this guy squared, which is going to end up canceling each other out. We'll deal with that in a moment. But this is negative 7 squared plus negative 3 squared. So 49 plus 9 is 58. Square and square root cancel each other out. 58 it is. All right. So now what I have is I have a fraction, and I'm going to multiply it to this vector right here. I'm going to multiply it to that vector right there. So I have negative 62 over 58 multiplied to the vector v, which is negative 7, negative 3. Negative 62 over 58 actually simplifies to negative 31 over 29. How about that? Who'd have known? And just multiply that fraction to both of these numbers, and you end up with a terrible, terrible, terrible fraction. 217 over 29. And 93 over 29. All right. Write the vector in component form. 3 dimensions. Ooh. Well, if it was 2 of these, it was simple. We just kind of, it started at A, it ended at B, negative 2 minus 0, negative 3 minus negative 2. Well, now we're adding 7 minus negative 1, so this is not going to change in the slightest. Okay, so component form is going to be negative 2 minus 0, negative 3 minus negative 2, and 7 minus negative 1. Double negative makes a positive, double negative makes a positive. Negative 2 minus 0 is negative 2. Negative 3 plus 2 is negative 1. 7 plus 1 is 8. And there is my 3D vector in component form. Awesome. Find the magnitude of each vector. Well, we're used to seeing the magnitude found by using this formula right here. Okay, x squared plus y squared. But we're going to add a z squared because this is 3 dimensions now. So this is going to end up being 2 squared plus 7 squared plus 5 squared, which ends up being the square root of 4 plus 49 plus 25, which ends up being the square root of 78, which ends up being 8.832. So if you were to imagine a 3D arrow pointing somewhere in space, this guy is 8.832 units long. In space. Find the component of the resultant vector. All right, well, we have 3D stuff going on here, and all I'm doing is doing u minus g. So 0, 9, negative 4, minus 9, 7, negative 7. 0 minus 9 is negative 9. 9 minus 7 is 2. Negative 4 minus negative 7, double negative is 3. And we're done. Find the magnitude of the resultant vector. All right, so the magnitude of the resultant vector is basically I have P, I have Q. We're going to take the opposite of P. We're going to take the opposite of P, Q rather. We're going to take the opposite of RS, and then we're going to combine those somehow and then find the distance from the beginning to the end. Gross. Well, this is what we need to do first. What we need to do first is we need to take PQ and put that in component form. Okay? PQ in component form is going to be 1 minus negative 7, which is 8, negative 8 minus 7, which is negative 15, and negative 9 minus negative 7, which is negative 2. Lots of double negatives going on in there. RS is going to be negative 3 minus negative 7, so a double negative makes that a 4. 0 minus negative 3, double negative makes that a 3, and 0 minus 5 makes that regular negative 5. So that's PQ and that's RS. They want me to take the opposite of PQ, so the opposite of PQ, and then subtract away RS, so the opposite of RS. So let me write that all out. Negative 8, 15, 2 plus negative 4, negative 3, 5 is going to give me in component form negative 12, because negative 8 plus negative 4 is negative 12. 15 minus 3 is regular 12. 2 and 5 makes 7. Now, in order to find the magnitude of that, we use this formula right here for 3D vectors, x squared plus y squared plus z squared. And so I'm going to use, I'll just say the magnitude, r is going to equal the square root of negative 12 squared plus 12 squared plus 7 squared. Let's type that away into a calculator, and you end up with 18.358. Find the cross product of the given vectors. Well, ladies and gentlemen, I have news for you. The cross product of a vector is not fun at all. Let's write out the formula and then go from there. We have, it's in component form, by the way, a sub y, and by the way, that's an a, so that would be the sub y, a sub y, b sub z minus a sub z, b sub y. Okay, that would be your first in the component form. Then you have a sub z, b sub x minus a sub x, b sub z. And then part 3 is a sub x, b sub y minus a sub y, b sub x. Close. Okay, so there's my a, x, y, z. There's my b, x, y, z. Let's have some fun, shall we? A times b in vector form is going to be 5 times 2 AYBZ, AYBZ minus AZBY, which is negative 3 times 9. Okay, AZBY, so you should get the idea now. AZBX is negative 3 times 2 minus AXBZ is negative 9 times 2. And then we've got AXBY, which is negative 9 times 9 minus 5 times 2. I typed this into a calculator ahead of time. These numbers multiplied out to 90 or 73, 37. Ugh. These numbers multiplied and subtracted out to 12. And these numbers multiplied and subtracted out to negative, not 19, but 91. The year I was born. It's not true. All right. Find the cross product of the given vectors. All right, what I need to do is I need to find what these guys are in component form. So AB in component form is going to be -5 minus -6, which is +1, double negatives there, -5 minus -2, which is -3, and -3 minus 6, which is -9. CD, compact disk, is going to be -5 minus 8, which is -13, -4 minus 7, which is -11, and -1 minus -6, double negative makes that 5. Now, the formula for this guy is an abomination, okay? So I'm going to call you A, I'm going to call you B, and I'm going to label these X, Y, Z, and X, Y, Z. Now, if you know anything about matrices, which I'm going to have videos on matrices, this has a very matricey feel to it. And you'll see what I mean as we start putting things together, but I'm not going to do that quite yet. I don't want to make it all matrixy stuff yet because I didn't get to the matrix section in Precalculus, so I don't know, maybe I can connect the dots when I get there, but I ain't there yet. Here's the formula. You ready? The formula is A sub Y, so that would be U, times B Z minus A sub Z B Y. So like A sub Z, BY, what's that? A sub Z would be -9, BY would be -11. Okay, that's the first part. Then I have AZ, BX, minus AX, BZ. Then I have AX, BY, minus AY, BX. And now it's a matter of plugging things in. A sub Y is -3. B sub Z is 5. Minus A sub Z, which is -9. B sub Y, which is -11. Okay, so you get the idea. We now have -9. B sub X is -13 minus A sub X, which is just 1. B sub Z, which is 5. And then we have A sub X, which is 1. B sub Y, which is -11. Minus A sub Y, which is -3, and B sub X, which is -13. Multiply and subtract. These guys end up being -114. Multiply and subtract. These guys end up being 112. Multiply and subtract. These guys end up being -50 cent. Candy shop. Remember him? Shot like 5 times or something. Rest in peace. He's not dead, but, you know, someday. Like and subscribe. Simplify -4W multiplied to this matrix right here. This is called scalar multiplication. Whenever you multiply a number or a variable, in this case both, to an entire matrix, scalar multiplication. This matrix is a 2-row, 3-column matrix, so it's a 2 by 3. Not that it matters, but when you multiply something by a 2 by 3, you get a 2 by 3. And essentially what you do with scalar multiplication is you distribute that -4W to all 6 of these elements. So -4W times -W is positive 4W squared. And then you do it again. This is going to involve, more distributed property kind of stuff. So that will be 16W, and then what is that? Minus 4WU. U becomes 0. U become negative 4VW. Oh, Volkswagen. Remember that? It's a movie, Billy Madison. Negative 20VW again, and negative 12VW squared. So I know that looks kind of sloppy, but if we were to make sure that we have this all split, we have 6 elements right there. 2 rows, 3 columns. That's our resultant matrix. Fun, fun. Simplify a matrix minus a matrix. This is a 3-row, 3-column matrix minus a 3-row, 3-column matrix. You can only add or subtract matrices if the dimensions are exactly the same, and in this case the dimensions are exactly the same. And what we get is a matrix that is also exactly the same. And what we do is we subtract element by element, one by one, that correspond with each other. So negative 4 minus negative 6 is the same thing as negative 4 plus 6, which is 2. Okay, and then we do it again. Negative 5, silly me, minus negative 1 is the same thing as negative 5 plus 1, which is negative 4. And then we do it again. 5 minus negative 6 is the same thing as 5 plus 6, 11. And then we just keep the process. 1 minus 6 is negative 5. 6 minus negative 3 is the same thing as 6 plus 3, which is 9. 3 minus negative 2 is the same thing as 3 plus 2, which is 5. Negative 2 minus 4, negative 6. 2 minus negative 1, 3. 1 minus negative 3, 4. And there you have it. That's our answer. That's our resultant matrix. Okay, so if you add or subtract matrices, make sure that the dimensions are exactly the same, and what you get is the thing that's the same dimension. And it's basically just a subtraction problem a bunch of times. Okay? Matrices. The Matrix. Neo. Like and subscribe. Simplify negative 5 times, parentheses, a matrix plus a matrix. All right, so this is basically PEMDAS. And in PEMDAS, we do everything inside the parentheses first, then we can multiply negative 5 to all of this. Well, what do we do first, you ask? Well, we need to add these matrices up. In order for us to add them up, we have to make sure that they're exactly the same dimension. So we've got 1, 2, 3 rows, 1, 2 columns, so 3 by 2. Plus 1, 2, 3 rows, 1, 2 columns, 3 by 2. It's legal to add these. So let's keep negative 5 living out there. And what I need to do is I need to add these matrices together. And when you add matrices, okay, you go with the element that corresponds with the other element in the other matrix. So 1 plus negative 5. 1 plus negative 5 is negative 4. 0 plus 4 is 4. Negative 2 plus negative 6 is negative 8. Negative 3 plus 0 is negative 3. And then you just keep going and get my last color. 6 plus 4 is 10. Negative 6 plus 4 is negative 2. So I have my matrix inside my parentheses, and I multiply negative 5 to it. Now it becomes a scalar multiplication problem. Scalar multiplication is when you take the number or term living outside in front of a matrix and multiply that number to every element in the matrix, like distributed property a ton of times. So what we get is a matrix of the same exact dimension, same exact size, with negative 5 multiplied to each of these. So negative 5 times negative 4 is positive 20, and negative 5 times positive 4 is negative 20. You see? Negative 5 times negative 8 is positive 40. Negative 5 times negative 3 is positive 15. Negative 5 times 10 is negative 50. And negative 5 times negative 2 is positive 10. So PEMDAS, adding matrices, scalar multiplication, lots of matrices stuff going on here, but, not too bad once you get the hang of it. I know Kung Fu. It's a line from a movie called The Matrix. Like and subscribe. Matrix multiplication. We have to simplify that matrix times that matrix. Well, matrix multiplication has rules. Whereas you may remember from addition and subtraction, you just had to make sure that the dimensions are exactly the same and then you can add or subtract them. Well, this is different. The dimensions here are not exactly the same. You see, what we have is a 2-row by 2-column matrix. And here we have a 1-2-row and a 3-column matrix. What you do in order to make sure that you could do this problem is whatever the columns are for the first matrix and whatever the rows are for the second matrix, you have to make sure that they match. And if they do match, then your resultant matrix is going to be what the rows for the first one are and the columns for the second one. So we get a 2 by 3. All right. So let me draw hopefully what I think a 2 by 3 is going to look like. Now what you do from here, and let me actually scooch this over. I'm going to need the space. What you're going to get is you're going to get a 2 by 3. So let me outline this out. I think that should be plenty of space. I might be cutting myself short, but we'll see. What you do is in order to get the first row, first column of this guy, you are going to multiply the first element of the first row to the first element of the first column of this guy. Notice how I split this up by rows and I split this up by columns. Well, you multiply these two together. 3 times 2 is 6. And then you multiply these two together. Negative 3 times 6 is negative 18. And you add them up. Okay? And then we repeat ourselves. So let me get rid of these red guys. Look at that. Look at that very abstract art looking thing that I just did. First row, second column. You're going to take the first row, second column. Multiply the first two elements of each. 3 times 6 is 18. And if you're like, didn't we already do the 3? Yep, a lot of repetition with these. First element in each. And then you do negative 3, the second element, times negative 15, the second element. I'm sorry, negative 5, that becomes positive 15. That's where my brain went. And then you add those up. And then you just repeat that process one more time as I continue building this abstract art creation over here. Wow, so pretty. Picasso ain't got nothing on me. Pretty sure Will Smith said that in a movie. 3 times 1 is 3. Negative 5 times a regular 4 is negative 12. Add them up. And then we're done with the first row up here. In order to get to the second row, first column, a very similar process is going to take place. You go to the second row in the first matrix now, and the first element in the first column over here and multiply those together. 6 times 2 is 12. Then you do the same thing. 3 times 6 is 18. Add them up. So a little bit of repetition is going on. All right, a little bit of repetition. 6 times 6 is 36. We're now in the second row, second column. 6 times 6 is 36. 3 times negative 5 is negative 15. So I could put plus negative 15, but maybe I will for consistency's sake. And then I'm going to have to repeat a color. 6 times 1 is 6, plus 3 times 4 is positive 12. And then now it's just an exercise in simplifying. So we end up with our 2 by 3 6 plus negative 18 is negative 12. 18 plus 15 is 33. 3 plus negative 12 is negative 9. 12 plus 18 is 30. 36 minus 15 is 21. That was it. And 6 plus 12 is 18. So there you have it. This is matrix multiplication. And again, what you have to remember is the only way that you're allowed to do this is if you set up 2 by 2, 2 by 3. Oh, the inner numbers match, which means I'm going to get the outer numbers 2 by 3. And then it's just a process of multiplying stuff and adding stuff and simplifying. So kind of complicated, but Avril Lavigne once asked us why would we have to go and do that? And sometimes the answer is because. Avril Lavigne, she rocks hard. Like and subscribe. Ooh, we have to simplify a matrix times parentheses a matrix times a matrix. Well, according to PEMDAS, we need to multiply these two matrices first. So in order to multiply matrices, what you do is you take matrix number 1 and matrix number 2, and you figure out the dimensions. We have 1, 2 rows, 1, 2, 3, 4 columns. And we're going to multiply that to 1, 2 rows, 2 columns. Now, in order for you to multiply two matrices, the first two or the inner two numbers, okay, of these have to be the same. And they're not. So the answer to this guy is undefined. And if you're like, whoa, 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 whoa. So what do we do? Nothing. We can't do it. You can't do this problem. You can't multiply two matrices if when you're doing matrix A times matrix B, if the number of columns in the first matrix don't match up with the number of rows in the second matrix. It can't be done. So don't worry about all this other stuff. You can't do it. Undefined is my answer. The end. Simplify a matrix times another matrix. All right. Whenever you're multiplying two matrices together, you need to make sure that you kind of figure out the dimensions and make sure you can even do it in the first place. So this guy has 2 rows, 1, 2, 3 columns, 2 by 3. This guy has 1, 2, 3 rows and 2 columns like so. So whenever the amount of columns for the first matrix is the exact same as the amount of rows for the second matrix, you're good to go. And what you end up with is whatever these outer numbers are, which is a 2 by 2. So we are going to end up with a 2 by 2, just like I did the other day when I went to Lowe's. Yes. 2 by 2 is a type of piece of wood. All right. Now, I'm going to need a whole lot of space, so there we go. We're going to end up with a 2 by 2, so let me get my dashes. When you multiply two matrices together, you split the first matrix by their rows and the second matrix by their columns. In order for me to find the result of the first row, first column here, I need to start multiplying corresponding elements and adding everything in between. So what I do is I take the first element in the first row and the first element of the first column and multiply them together. 6u times -3u is -18u squared, and then I add. Okay, then we do it again. 2u times 6u is going to be 12u squared. And then we add, and what color didn't I use? Blue. U squared times -6u is going to be -6u cubed. Now, I know this kind of looks sloppy with the plus negative thing. I'll clean all that up because, as you can see, we're going to end up combining like terms anyway. Okay, let's get rid of these colors. Let's get rid of them so we can do the next row column combination thing. Oh, it's like almost the Olympics thing. Remember the Olympics? Of course you do. Okay. So now I want to do the first row, second column. So multiply the first element in each. 6u times 1 is going to be 6u. Okay. 2u times 3v, adding an extra letter, is going to be 6uv. And u squared times v is going to be u squared v, again, plus signs in between. All right, so that completes the complete first row. Now we move on to the second row, and we'll do second row, first column, second row, first column. All right, I'm going to stop drawing all over my picture so I don't make it sloppy. uv times negative 3u is going to be negative 3u squared v. V squared and 6u is going to be positive 6uv squared in no particular order. Negative 2v squared, negative 6u is going to be positive 12uv squared. Okay, let's finish this thing out. Again, I know I have to combine like terms. We're not there quite yet. uv times 1, uv. V squared times 3v is positive 3v cubed, and negative 2v and v is going to be positive negative 2v cubed. All right, let's combine some like terms. Let's make this a little bit bigger so it doesn't look so sloppy and jumbled up. Hopefully I left myself enough space. Let me scooch it over just in case I didn't. Why the heck not? All right, negative 18u squared, 12u squared is going to give me negative 6u squared. This is supposed to be a u cubed. I know it looks like squared, but that's a u cubed. So this is going to be plus a negative minus 6u cubed. That's the top left. Negative 6u squared minus 6u cubed. The top right, which we'll do in a different color, nothing combined. So it's just going to be 6u plus 6uv plus u squared v. Bottom left, do we have any? Yep, we have some combinations. We have this one right here. These two combine. So negative 3u squared v, nothing happens there. But this becomes 18uv squared. And on the bottom right, let's go to blue. On the bottom right, I have two v cubes that are going to combine. So I'm going to have uv. 3v cubed minus 2v cubed is 1v cubed. And there you have it. There's our 2x2 matrix with lots of u's and lots of v's. It sounds like I need some sunscreen because of the UV rays. Like and subscribe. Find the determinant of this 2x2 matrix. Whenever I'm being asked to define the determinant, okay, when you see, by the way, what looks like absolute values, it's not absolute values, it means determinant. I'm going to just replace these with A, B, C, and D. This is just the definition in general. The determinant of a 2x2 is you take the top left and the bottom right and multiply them together. Then you subtract the top right and the bottom left and multiplied together. So in this case, U would be my A, U would be my C, B, U would be my C, U would be my D. The alphabet's really hard. So this is going to end up being negative 2 times 5 minus 3 times 0. Negative 10 minus 0 is negative 10. And that's the determinant of this 2x2 matrix. Find the determinant of a 3x3 matrix. Now, 2x2s, pretty easy. 3x3, not so much. So I'm going to show you the definition of what a 3 by 3 matrix looks like. I'm just rewriting a 3 by 3 using letters. And let's get some colors involved here. Get some colors and get some lines. And you might be thinking, what's he doing? Well, if I want to find the determinant of a 3 by 3, I'm going to kind of work my way left to right and cover things up. What I did here is I'm going to say it's going to be A, this is the determinant, A times the determinant of the EFHI matrix. So -2 times the determinant of this guy right here. Okay, then you always subtract in the middle. This is going to look kind of weird. I probably should have got different colors, but you're going to cover that, and we're going to pretend that A and C are covered. All right, so you're going to do B times a determinant of the DFGI matrix, DFGI. I'm going to swap back to a plus sign. We're going to swap back to a plus sign. Let's get rid of these, bring this back up here and scooch that over. And now we're going to take this C and multiply it to the determinant of the DEGH matrix. Kind of sloppy looking, I know, but you get the idea. All right. So what this is going to look like is we're going to take A, which is -2, and multiply that to the determinant of 5, -5 to -5. So I will write that out, 5, -5 to -5. Then I'm going to minus 1, which is not technically necessary, but I'll put the 1 there anyway. The determinant of the DFGI, which is 0, -5, 0, -5. Okay, 0, -5, 0, -5. Then I'm going to add C, which is technically plus -2, so I'll put -2 times the determinant of 0, 5, 0, 2. Okay? -2, remember the determinant is found by doing cross multiplication and subtracting. So 5 times -5 is going to be -25 minus 2 times -5, which is -10. Minus 1, 0, minus 0, I can handle that. Minus 2, 0, minus 0, I can handle that. U becomes 0, which means you go away. U becomes 0, which means you go away. And this just ends up being -2. Double negative makes a positive. -2 times -25 plus 10. -25 plus 10 is -15. And my determinant is my age in a couple years, 30. Just kidding. I'm not 30 in a couple years. Much older than that. Like and subscribe. Find the inverse. Well, the way you find the inverse of a 2 by 2 matrix is, let's just say that we have an A, B, C, D. All right? The inverse is going to be 1 over the determinant. So we'll call this A. So we'll say the determinant of A. And then we multiply whatever fraction we get here to D. So we swap these two, D and A swap. You take the opposite of this one and the opposite of this one. So another way of writing it out is if this is A inverse is going to be 1 over the determinant of A, which is going to be 10 times 0, minus 0 times 1, times, swap the A and the D, so U becomes 0, U become 10, make U its opposite, so positive 1, and the opposite of 0 is 0. So this becomes 1 over, wait a minute. You can't do 1 over 0. I forgot, if the determinant is 0, the inverse is undefined and you can't do it. Oh, I should have just done that first. Silly me. If the determinant is 0, you can't do it. You can't find the inverse. So the inverse is undefined. Some people might say the inverse does not exist. Either way, can't do it. So there you go. For what values of x does the matrix M have an inverse? Well, a 2 by 2 matrix has an inverse as long as its determinant is 0. So the way you find the determinant of a 2 by 2 matrix is you multiply the top left and the bottom right, x times x plus 1, and then you subtract the top right and the bottom left multiplied together. So if we do a little bit of distributive property, this is x squared plus 1 minus 2. Now, the determinant cannot be 0. The determinant cannot be 0. By the way, this was supposed to be x, not 1, so I apologize. That looks sloppy. But what we have is we have x squared plus x minus 2 cannot be 0. Oh, you know what? I can factor that, can I? I can turn that into x minus 1, x plus 2 cannot equal 0. And this uses the zero product property. You set each one not equal to 0. So if you add 1, x cannot equal positive 1, and x cannot equal positive 2. So the question is for what values of x does the matrix M have an inverse? For all real numbers, except x cannot equal 1 and x cannot equal 2. Okay? There you go. My job is to solve this matrix equation. Now, if you're looking at this and saying, oh, this is the absolute worst, I'm here to tell you that solving something that looks like this is not too different than something that looks like, I don't know, that. And you might be thinking, no, this doesn't look like that at all. Well, I would add a number and then divide everything by 2 and I'd be fine. Well, very similar stuff going on here. First things first is I have to get B all by itself. I have 2 multiplied to B, and I'm also subtracting this matrix here. Let's get rid of the matrix by adding the matrix to both sides. So I'm going to add -4, -8, -9, 0 to both sides. -4, -8, -9, 0. Cross U out. That gets me 2b equals. Now I can add these together because they're the same exact dimensions. So when I do that, I get -2 because 2 plus -4 is -2. 4 plus -8 is 6. 7 plus -9 is -2. And 16 plus 0 is 16. I have 2 being multiplied to b. I'm not a big fan of dividing a matrix by anything, so what I'm going to do is I'm going to multiply both sides on the left by a half. When you're dealing with matrices, whatever you do to one side, you should do it on the same exact side. So I'm multiplying both sides by a half on the left. This is scalar multiplication here, so I just multiply 1/2 to every element inside this matrix. 1/2 times -2 is -1. 1/2 times 6 is 3. 1/2 times -2 is -1. And 1/2 times 16 is 8. That's my answer. B is a matrix right there. Cool. All right, I'm going to have to write small on this one because I have to solve this matrix equation. So in order for me to solve a matrix equation, I have to get B all by itself. So I'm multiplying a matrix to B, and I'm also have a matrix floating around. So let's subtract this matrix from both sides. So I'm going to subtract -3, 7 from both sides. -3, 7, this crosses out. So let's write it over here. We have negative 3, 0, 5, 1. Don't forget that negative, by the way. It's so easy to do. Equals 21 minus negative 3 is the same thing as 21 plus 3, which is 24. And 21 minus, I'm sorry, my fault, negative 39 minus 7 is negative 46. I forgot my b. So here I was talking about, don't forget that negative when I forgot the b. That would actually be very, 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 very important. Let's distribute that negative real quick. So now I have this. And that's going to equal 24 negative 46. All right. Now, this is very important. You can't divide by a matrix. It's impossible. But what you can do is you can multiply both sides of its inverse, and that essentially does the same thing. So what I need to do is I need to find the inverse of that guy and multiply it to both sides. The way you find the inverse of a 2 by 2 matrix is thing number one. You set up a fraction 1 over its determinant. That's thing number one. So the determinant of a 2 by 2 matrix has you multiplying these two guys together. So 3 times negative 1 is 3, and 0 times 5 is 0. So I end up with just negative 1 over 3. 1 over negative 3, negative 1 over 3, same thing. Then you take that and you multiply it to this matrix where you flip the 3 and the negative 1. So you flip the top left and the bottom right to make it negative 1 and 3. Make this its opposite, so the opposite of 0 is 0, and make that bottom left its opposite, which becomes 5. Now it's scalar multiplication. Multiply it out, and you end up with positive 1/3, 0, negative 5/3, negative 1. So we take this guy, which is the inverse of this guy right here, we multiply it to both sides. So what that's going to look like, if I rewrote this one out, I'm worried that I don't have enough space, but I think I'll be okay. If I rewrite out 3, 0, negative 5, negative 1, b equals, leave myself some space, 24 times negative 46. I have to multiply them both on the left side. I can't just, go back and forth. So this ends up being 1/3, 0, negative 5/3, negative 1, 1/3, 0, negative 5/3, negative 1. This becomes the identity matrix, which goes away, and now B is going to be all by itself, and I have matrix multiplication. So with matrix multiplication, you split that up in by rows, and it's already one column, and this shouldn't be too bad. Hopefully. 1/3 times 24 is 8, plus 0 times negative 46 goes away. Negative 5/3 times 24 is negative 40. And then negative 1 times negative 46 is plus 46. So at the end of the day, I end up with 8, 6. And that's my B. Which is what I would say if I have a honey company and I lost my queen bee. Oh, my God. Use reduced row echelon form. Friends, this is gross. But let's set it up. what you do is you write out your own version of a matrix using the coefficients in order. So for -2, there's no z, so 0, 2. I like to put a little line there. You're allowed to do that. 5, -2, 1, 7, 3, 4, -1, 3. Now, what you're allowed to do is you're allowed to manipulate, okay, any of these rows, any two rows, and add things together in order to make something that ends up looking like this. What this will do is give us our answers. So I'm just making this up. If I end up with this tells me that my answer is 369. I use that because it reminds me of a Little John song. Get low. All right, now what I need to do is I need to end up getting that identity looking thing on the left. And what I want to do is I want to kind of find ways to puzzle things together to make stuff go away. So I'm going to manipulate rows, add or subtract, usually add, and replace one of those rows with what I get as a result. So the first thing that I want to do is I'm going to add the second row to the third row. And when I do that, when I add the second row to the third row, that eliminates this guy right here. And I'm going to replace the second row with my result. So the first row doesn't change. 4, -2, 0, 2. I'm adding the second and third row in an effort to make that 1 disappear. So it does. I'm replacing the second row. So the third row won't change. I'll deal with that in a second. This becomes 2, you become 8, and you become 10. The third row, I'm keeping the exact same for now. Now, I started out this way because I'm thinking, all right, what I can do now is I can make the first row become a 0 right here, and that kind of almost gives me that 1, 0, 0. It's not 1, 0, 0, it's 4, 0, 0, but that helps me out. So what I'm going to do now is I'm going to add the first row and the second row and replace that first row. So I'm going to add the first row and the second row and replace the first row. So first row plus second row, 4 plus 8 is 12. -2 and 2 becomes 0. 0 and 0 becomes 0. And 2 and 10 become 12. Keep everything else exactly the same. Now you might be thinking, oh man, if only that 12 was a 1, life would be good. Well, let's make it a 1. Let's divide the top row by 12, and then that wraps up our first row. So if we divide the top row by 12, we get 1, 0, 0, and 12 divided by 12 is 1. So now we have 8, 2, 0, 10 still. We have 3, 4, -1, 3. And we can kind of see things, forming out the way we want it to. We have that top right of zeros forming out. We just need to make you zeros and make you a 1 and make you a 1. So what I want to do now is I want to take, I want to make this 8 become a 0. So what I'll do is I'll multiply the top row by -8 in my head, add it to the second row, and replace the second row with what I get. So in my head, I'm multiplying the top row by -8. So you become -8 and 8, and I'm going to replace the second row. All right, so actually, well, why don't I do this? I can rewrite that first row. Nothing changes with the first row. So if I multiply the top row by -8, and I add it to the second row, replacing the second row, -8 plus 8 is 0. Good. -8 times 0 becomes nothing, nothing changes. -8 times 0 becomes nothing, nothing changes. -8 times 1 is -8, plus 10 is 2. So if you're thinking, oh, I see what I'm going to do. I'm going to do the same exact thing that I did up here to down here and divide this guy by 2. Sure am. Sure am. So I'm going to divide everything here by 2. So I get 1, 0, 0, 1. Divide u by 2, 0, 1, 0, 1. And now I have 3, 4, negative 1, 3. Okay, almost done. Almost home free. What I'm going to do next is I'm going to, let's get rid of u. And I can get rid of u. Multiplying this row won't do anything, but if I multiply the top row by negative 3 and add it to the bottom one, that negative 3 goes away. So let me write a little bit smaller just in case I need the space. Multiply the top row by negative 3 and add it to the bottom row. Negative 3 times 1. So actually, why don't I do this? Just rewrite the top 2 rows. All right, multiply the top row by negative 3 and add it to the bottom row. Negative 3 plus 3 is 0. 0, 0, so these two won't change, so you're 4 and negative 1 still. If I multiply the top row by negative 3 and add it to the bottom row, that becomes 0. That means nothing. Now let's do the same thing to the second row, where if I multiply the second row by negative 4, that allows me to get rid of u. So the top 2 rows, once again, will not change. But if I multiply the middle row by negative 4, 0, 0, nothing. Negative 4 plus 4 becomes 0, 0, nothing. And if I multiply u to negative 4 and add it to 0, you become negative 4. So last but not least, I'm almost there. If I have 1, 0, 0, 1, 0, 1, 0, 1, and if all I could do is multiply this bottom row by negative 1, which I will, that happens, you become positive 4, and I am finished. So the answer to this huge system of equations using row reduced, echelon row form of the rows is 114. And that ding means that I'm done. Ding, fries are done. Thanks for watching. Bye. Identify the vertex, focus, axis of symmetry, and directrix of this guy right here. Then I have to sketch the graph. All right, I have a y that's not squared and an x inside of a parentheses that is squared, which tells me it is a parabola. Now, what is all this other stuff? Well, if I were to draw just some random parabola right there, focus lives inside the curved part of the parabola. That's the focus. The vertex is the minimum or maximum, and then equally distant is going to be a flat line called the directrix. Okay? Now I'm going to have to draw all this stuff out at some point. Not quite yet. Let's just focus on one thing at a time and finding stuff out. The x part is squared. There are parabolas where the y part is squared, so make sure when you're looking for the formula that you compare this to, you use the right one. This is the standard form of a parabola where the x part is the one that's squared. X minus h in parentheses squared is going to equal 4p, and if you're like, p, what does that stand for? You'll find out. Y minus k. I need to make that look like that. So what I'm going to do first is I am going to flip things. Let's just completely flip everything. We've got negative x plus 3 squared. I'm actually going to keep, now I'm going to still flip it. Minus 1 is going to equal to y. Okay, now what I need to do is I need to get all the y stuff on the right side. So let's add 1, So negative x plus 3 squared. Let's add 1 to both sides. So now I have y plus 1. Let's throw a parentheses around that just for funsies. And let's multiply both sides by a negative. So what we have is x plus 3 squared equals negative. And I'll put negative 1 even though I don't need to. I'm multiplying everything by a negative. There you have it. Now I can compare that to that. It's important to know that I have to find what? The vertex, the focus, and the axis of symmetry, and the directrix. Okay, well, the vertex is going to be HK. So the vertex in this case is going to be H. Now, negative H is positive 3 here, which means positive H is negative 3. So H is negative 3. K, similarly, positive 1 is negative K. So positive K is going to be negative 1. Okay, that's my vertex. Let's get a different color. My focus is found by taking H and then K plus P. You might be thinking, what's P? I still have to figure that out. In front of the parentheses here, I have 4P, and this is negative 1. So comparing this to this, I'm going to let 4P equal negative 1. So if I divide both sides by 4, P is negative 1/4. So my focus is H, and I already know that my H is negative 3. K plus P is going to be negative 1 plus negative 1/4, so negative 1 1/4. All right, so what I have so far, let's circle things out, is my vertex is there. My focus is there. My axis of symmetry is going to be a vertical line that cuts through the vertex. So my axis of symmetry, since it's going to be a vertical line, is going to be x equals. Well, if it cuts through the vertex, then x equals right there, negative 3. So that is my axis of symmetry. Last but not least, my directrix is going to be a horizontal equation given to us by y equals k minus p. K was negative 1. P is negative 1/4. So to round things out, y equals negative 1 minus negative 1/4 is the same as negative 1 plus 1/4, which is going to be negative 3/4. Now I know I'm going to do a terrible job drawing this out. Okay, I'm going to do a terrible job. So what I'm going to do is I'm going to paste the picture that I'm supposed to have. Did it work? Did it work? I don't think it worked. I don't think it worked. Let's try it again. Copy, paste, and it didn't work. All right, let's try it this way. Let's try copying it like this. This makes for very good podcasting. All right, I captured it. Let's go back over here. There we go. All right. So, why is it upside down? Because this is negative. That's thing number 1. Okay, let's label this picture a little bit. My vertex is negative 3, negative 1. So my vertex, my vertex does live right there. Okay, my directrix right here is y equals negative 3/4. So it's like a little dashed line, like kind of like right there, whereas my focus is negative 3, negative 1 1/4 lives right there. Okay, so we can kind of see everything falling into place. My axis of symmetry is x equals negative 3. So there's my vertical line that goes through negative 3. So we can see everything there. Directrix, axis of symmetry, focus right there, vertex right there. So everything lives where it should be. And if you're wondering, well, how can I get points to make a graph? Just plug random points in. If you know what your vertex is and it's -3, -1, then plug in -2 and see what y value you get. Plug in -1 and see what y value you get. And whatever you start graphing over here, the same exact thing is going to happen over here because this acts as a mirror image. So graphing parabolas when they're in this standard form is never fun, but we did it, and I had a great time. Parabolas. Identify the vertex, focus, axis of symmetry, and directrix, then sketch the graph. First things first, we need to realize that this is a parabola because one of my x thingies is squared and one of my x thingies is not. Okay. But this is different because it's the y thingy that's squared and the x thingy that's not. So this is going to open sideways, and we have to figure out which ways that sideways is going to go. So I'm going to compare this to y minus k. This is the standard form for a sideways opening parabola. That's going to equal 4p times the quantity x minus h. So I need to make this look like that. Okay, so first thing I want to do is swap this. So I have y plus 5 squared equals -1/3 x minus 3 not squared, and now it's exactly the way I need it to look like. Okay, all is well. Let's compare the two. Okay, y plus 5 squared, y minus k squared. Negative k is positive 5, so k is -5. Okay, x minus 3, x minus h. Negative h is -3, so h is positive 3. And if -1/3 is the same as 4p, then what I do is I say 4p equals -1/3. Divide both sides by 4, and p is -1/12. Now I have all the information that I need. Okay, we find our vertex by doing hk. In this case, hk is 3, -5. That's our vertex. That's thing number one. We find our focus, in this case, by doing h plus p k. So h is 3 plus 1/12 is going to be 2 11/12. My k doesn't change. K is -5. My directrix is x equals h minus p. Now, x equals means it's a up and down line, which is what tells me it's sideways. So what do I have? H is 3 minus -1/12, so 3 plus 12, x is equal to 3 1/12. Okay, that's my directrix. And my axis of symmetry in this case is y equals a vertical line that goes through my axis of symmetry. My axis of symmetry is 3, -5. If it's y equals, then y is that -5. Okay, so there's my axis of symmetry. There is my directrix. There is my focus. And there is my vertex. So a quick look at this. All right, now I'm not even going to pretend like I can sketch this. I'm not going to sketch this. This opens sideways and to the left. How do I know that? Well, my directrix, and this is just going to be a rough draft, since my directrix lives to the right of my vertex, that has to open to the left, and my focus is always going to live inside. Okay, so let me actually pull up a picture that I stole from Desmos of what it should look like. There you have it. And we can see everything kind of falling into place. Okay, even though things are kind of close to each other, we can see that our vertex is 3, -5. So right 3, down 5, there's our vertex. And so where you can barely see it, our directrix is going to be just to the right of it as a dashed line just to the right of it. And then our focus is just to the left of it. And you can see that our axis of symmetry is y = -5, which goes through it. So the picture is good. And if you're like, well, how do I graph it completely? Well, then you take points, knowing what your vertex is, you take possible y values, plug them in, and see what x value you get, and then that gives you more points to draw. But this gives me a sketch. This is what it ends up looking like, and yeah, not so bad. Not so good, but not so bad. Use the information provided to write the transformational form equation. All right, so what do we have here? We have a vertex, we have a focus. This is a parabola. Okay, this is a parabola, and what we see here is that the focus lives to the left of the vertex. So we have an equation that looks like this. An equation of a parabola that looks like that in standard form is going to be y minus k squared equals 4p times the quantity x minus h. Now let's label some things. The vertex is hk. The focus is going to be h plus pk. So I have an h, not bad. I have a k, not bad. I don't have a p, so let's find out what that is. H plus p is going to equal -17/16. H is -1. So let's replace that. H is -1. Add 1, and P is now going to be -1/16. So let's put all this together. Let's rewrite this equation and substitute what we just found out. Y minus k is y double negative k squared equals 4 times p. P is -1/16 times x minus h, which is -1, another double negative. So let's clean this up and put our answer down here. Y minus -k. Why did I say k when I know that it's -3? What a rascal I can be sometimes. Y minus -3 is y plus 3 squared equals 4 times -1/6 is -1/4. And then x double -1 is x plus 1. So there you have it. There you have it. Parabola, baby. Identify the center, radius, and sketch. All right, so this is a circle because it mentions radius. Radii only live with circles, so that is the circle formula. This is the circle formula right here, actually. X minus h squared plus y minus k squared is going to equal r squared. This is actually pretty easy. Now my center, I'm jumping ahead. My center is hk. Negative h is +3, which means positive h is -3, so that's the x value of my center. -6 is +4, so +6 is -4. There's my center. Now I need a radius. My radius squared is equal to 5. So if I square root both sides, my radius is going to be whatever the square root of 5 is, and that's 2.2, blah, 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 blah. Now, I'm not even going to try to draw this out, except that I am going to try to draw this out. Let's place my center at -3, -4. And then I try to draw out and around 2.2 units. So this is what the outside would look like. And then I would draw that picture around. Oh my gosh, I'm actually doing it. That's not bad. That's not bad. Here's what it's supposed to look like. Oh my gosh. Well, I mean, it's not perfect, but that's probably the best circle that I can whip up. But there you have it. So given all the information that we have, you could see, where my center is at -3, -4, and then a circle that's a little more than 2 around it. So yeah, I'll give myself a pat on the back. Do you hear that sound? That's me patting myself on the back. All right, we graphed a circle, boys and girls. Fun. Identify the center, radius, and then we're going to sketch this out. Now, if you're looking at this and thinking, what the heck is this? Well, it mentioned radius, which tells us it's a circle. Now, a circle is supposed to look like something with an x in its squared plus something with a y in its squared equals some number. I need to make this look like that. So let's group all the x's together, x squared and 4x, and let's purposely leave ourselves some space. And then let's group the y's together. So y squared, 2y, let's leave some space. And while we're at it, why don't we add 4 to both sides? Now what I'm going to do is I'm going to use completing the square twice to make this look like that. In order to complete the square for this part right here, I take half of the number in front of x, 2, square that, 4, and add that to both sides, like so. I'm going to do the same thing right here. Take half of 2, 1, square that, 1, and add that to both sides. Now, what this leaves me with is this guy right here ends up being x plus 2 squared because now it's a perfect square trinomial. This guy right here ends up being y plus 1 squared because that's a perfect square trinomial. And this guy ends up being 9 because 4 plus 1 is 9. Now I compare this to the equation of a circle, which is x minus h squared plus y minus k squared equals r squared. My center is hk. So if negative h is positive 2, then positive h is negative 2. And if negative k is positive 1, then positive k is negative 1. There's my center. My radius is r squared equals 9. So if I square root that, r equals 3. I'm going to try to draw this out. So my center is going to be at -2, -1. Since that's a pretty number, drawing this out shouldn't be too bad. So a radius going to the right gets me an outside right there. A radius going up 1, 2, 3 gets me right there. A radius going to the left 1, 2, 3 gets me right there. And a radius going down, down gets me right there. And then we try to draw a circle which looks like that, and I'm extremely pleased. I don't think I can do a better job if I was paid to do a better job, which I'm barely paid at all because I'm a math teacher. But that's our guy. We just graphed a circle of something that's not even close to resembling standard form. Good work, everybody. Use the information provided to write the standard form equation of a circle. Well, the standard form equation of a circle is x minus h squared plus y minus k squared equals r squared. My center is HK. Well, that's nice. There's my H, there's my K. My R is, I don't know. But you know what I do know? That the area of a circle is pi r squared. So the area of my circle is 16 pi. So 16 pi is equal to pi r squared. And those pi's are useless because we can divide both sides by pi. If I take the square root of that, r is going to equal 4. Oh, so let's put all of this together, shall we? X minus h is x minus 15 squared, plus sign. Y minus k is y minus negative 8, a double negative. We'll deal with that in a second. And r squared is 4 squared, which is a fun game. By the way, we already found out that r squared was 16 a minute ago. Maybe I could have kept it like that, but who cares? X minus 15 squared plus y double negative is a positive 8 squared equals 16. That is a radius in standard form with a center of 15, negative 8, and an area of 16 pi, baby. Fun. Identify the center, vertices, co-vertices, and foci, and then sketch the graph. All right, what do we have? We have an ellipse. I know it's an ellipse because the x part's squared, the y part is squared. That's a plus sign and it's equal to 1. If it's a minus sign, then it's not an ellipse. You'll learn that in a future video. But what I also see is the part underneath x squared is larger than the denominator underneath y squared, which tells me that the ellipse is going to have a major axis that's wider and is also horizontal. So I need to compare this guy to this guy. X minus h squared over a plus y minus k squared over b. And that's going to equal 1. Actually, a is squared and b is squared, silly me. Now, if you're looking at this and saying, what if 16 was under y squared? That's a different equation. And that's a different animal all in itself. So, the center is found by doing hk. If h is negative here and negative h is positive 3, then my center is going to be negative 3 because positive h is negative 3. Similarly, but opposite literally, if negative k is negative 1, then k is positive 1. That's my center. My vertices are given by h plus or minus a and k. Now, 16 is a squared, which means a is the square root of that, 4. So I have two vertices here, h plus 4 or negative 3 plus 4, which is 1. K doesn't change. And my other vertex is going to be h minus 4 or negative 3 minus 4, which is negative 7, and then k is 1 still. So these are my vertices. My co-vertices are found by using negative h and k plus or minus b. All right, did I say negative h? Regular h. Oh, man. Let's try to get rid of that. Sorry, everybody. Regular h. All right. H is negative 3. I can handle that. So let's write them both out. Negative 3. K is 1. If b squared is 4, then the square root of 4 is going to be b, so 2. So I have 1 minus 2, which is negative 1, and 1 plus 2, which is regular 3. Those are my covertices. Now, the way I find my focus is I need to come up with a C, and the way you find a C, and I'm looking at what color I didn't use, red. The way you find a C for your focus is going to be c squared minus or equals a squared minus b squared. Now I know that a squared is 16. So c squared equals 16 minus b squared, which is 4. 16 minus 4 is 12. And the square root of 12 is going to be somewhere along the lines of 3.5. My focus is going to be h plus or minus c and k. So that's going to become negative 3 plus 3.5-ish is going to be 0.5-ish. K is 1. And then my other focus is going to be what was it? Was it negative 3 minus 3.5, which was negative 6.5-ish 1. So drawing this out, probably not going to go well for me, but I'm going to give it a shot. I'm going to give it a shot using the colors that I have. So let's start out with the best part, which is the center, negative 3, 1. Negative 3, 1. There's my center. My vertices are 1, 1. So 1, 1. And negative 7, 1 right there. So that represents the sides of it. My covertices are negative 3, negative 1, and negative 3, positive 3. And then my foci just kind of are invisible dots that live on the inside, which is going to happen at here-ish and here-ish. They don't do anything or have anything to do with the drawing of my picture. And yes, I said drawing. So let's try to connect these dots the best I can. So there's an ellipse, there's an ellipse, there's an ellipse, there's an ellipse. I started out strong, ended up weak. This is what it's supposed to look like. So I'll give myself a little bit of credit on that one. I'll give myself a little bit of credit. We have our circle where it needs to be. So if I were to take this and cover this up and go like, pew, looks pretty good. Pew, pew. So that's my ellipse. Identify the center, vertices, and covertices of this guy here. All right, well, first things first, it's not a parabola. It's not a circle. Why isn't it a circle? Because there's a number in front of y squared and not a number in front of x squared. So is this an ellipse? Yes. Why? Because both of these are positive. If one of these were negative, then it's something else. You'll find out in the near future of what that something else could be. Now, when I did a problem like this with a circle, the thing that I did first is I grouped everything up by variable, and then I ended up completing the squared, and I'm going to do the same exact thing here. So I'm grouping the x's, leaving some space, grouping the y's, leaving some space, and that's going to, while I'm at it, by the way, let's subtract 225. There you go. Okay. Before I go any further, before I tarry further, let's do this. In order for me to do completing the square, I really want nothing in front of y squared. So let's rewrite this out, and let's factor out a 9 so we can, for the moment, pretend that there's nothing in front of y squared. So this becomes negative 10y, leave some space, set that equal to negative 225. Okay, the part here in purple, not so bad. I'm going to add 9. Y, half of 6 is 3. 3 squared is 9. Got to do the same thing over here. I'm going to take half of negative 10, which is negative 5, square that and make it 25. Now this is where you have to be careful. I'm not going to add 25 to both sides. Technically on the left here, 25 lives inside of a parentheses that's being multiplied to 9. So if I'm going to add something to both sides, I'm adding 9 groups of 25, which is 225. Okay? Tricky. Tricky. But what that leaves me with is x plus 3 squared plus 9 parentheses y minus 5 squared equals 9. Now, if it's an ellipse, I have to make this equal to 1. So let's divide everything by 9. And ooh, God is good. Look at that. Over 9. And my standard form is now coming together. X plus 3 squared over 9 plus y minus 5 squared. I'll put over 1 even though it's not necessary is going to equal 1. Now for an ellipse where the number underneath the x is bigger than the number underneath the y, I have this form right here that I'm going to write up. It's going to be x minus h squared over a squared plus y minus k squared over b squared equals 1. My center is going to be hk. So if negative h is equal to negative 3, then h is going to equal positive 3. And if negative k is equal to negative 5, negative h is equal to positive 3, so h is negative 3. That changes a whole lot if I don't do that. Negative k is equal to negative 5, which means k is 5. There's my center. My vertices are given to me by the formula h plus or minus a k. A is the square root of 9, which is 3. So my vertices are going to be h plus 3 or negative 3 plus 3. K doesn't change. And my other vertex is going to be h minus 3 or negative 3 minus 3, which is negative 6, 5. Those are my vertices. My co-vertices are given by the formula h, k plus or minus b. We already know what h and k are. B is going to be the square root of 1, which is 1. So my vertices are going to be h, which is, what was it? Negative 3. My k is 5, so 5 plus 1 is 6. And negative 3, 5 minus 1 is 4. Not graphing this one, kind of ran out of space. But if we had to graph it, we'd be able to, and you can watch a video on how to do so if you're dying to know. Use the information provided to write the standard form equation of an ellipse where I have 2 vertices and 2 foci. This is what I notice. In my vertices, the y values don't change, which means I have a horizontal major axis which has an equation that looks like this. These are the ones that are wider than they are taller. Okay, so I'm going to write that out. Y minus k squared over b squared equals 1. My center is hk. I don't have a center here, so I can't really start with that. So let's go to vertices. Vertices are given to us by h plus or minus a and k. So that at least gives me a k of 9. Okay, do I have an a? No, but this is what I also know. Foci are given by the equation h plus or minus c k. So if my foci here are going to be 5 plus stuff and 5 minus stuff, well, then that 5 is going to be my h. Also, plus 2 root 7 minus 2 root 7 tells me that c is 2 root 7. With that information, if my vertices were given to me by h plus or minus a, then since this has a difference of 16 between each other, that tells me that a is 8. Okay, so then that's because my horizontal major axis is going to be 16, and your half of that is going to be divided by 2. And so that right here tells me that a is 8. Now, do I have all the information that I need? I do not, because I don't know what B is yet. I have A, I have C. Well, what we do know is I can find B, and it's not too bad. So C squared equals A squared minus B squared. C is 2 root 7, so 2 root 7 squared equals A, which is 8, so 8 squared minus B squared, which is, I don't know. 2 root 7 times 2 root 7 is going to be 4 times regular 7, which is 28. This becomes 64. That equals B minus B squared. Move that up here. Subtract 64 from both sides, and that gives us negative 36 is going to equal to negative B squared. Make them both positive. 36 equals B squared implies that if I square root everything, B is 6. So now I have everything that I need to plug this in here and make myself happy. So just to save some space, do I have any negatives that I have to deal with? No. So x minus h is going to be x minus 5 squared over a squared, which is going to be 64, plus y minus k is 9 squared over b squared, which is going to be 36, equals 1. And that is my ellipse, total ellipse of the heart. It's a song. It's great. I believe that's a journey, but I could be wrong. Identify the vertices, foci, and asymptotes, and then sketch the graph. This is a hyperbola because we have a y something squared, we have an x something squared, we have a minus in between, and it equals 1. Usually hyperbola look like that, and that's no hyperbole. English humor. Since the y squared is positive and the x squared is negative, we're going to compare it to this function right here because it's a vertical transverse axis. So we're going to compare it to y minus k squared over a squared minus x minus h squared over b squared equals 1. The center is HK as usual, but oh friends, be careful. H is over here, not over here. So negative H is in this case negative 3, which means H is regular 3. Tricky, tricky, tricky. And negative K is positive 4, so regular K is negative 4. All right, be careful. It's very easy to flip those guys around and get it backwards. Let's do the focus next. So in order to do the focus, you need a C, and we don't have a C. But the way you would find C for hyperbola is you would do C squared equals A squared plus B squared. So if you remember ellipses, it was minus, now it's plus. So what do I know? I know that C squared is 1 plus 1, which means C is the square root of 2. So the foci is found by doing h, which I already know, k plus or minus c, which is what I just found. The h is 3. The k is negative 4 plus or minus root 2, so I'll do negative 4 plus root 2, and then 3, negative 4 minus root 2. Okay, that's my foci. My vertices are going to be h, k, plus or minus a. So 3, once again, k is negative 4. If a squared is 1, then a is 1. So negative 4 plus or minus 1, which I'll do negative 5, because that's negative 4 minus 1. And negative 4 plus 1 is a negative 3. Now the asymptotes, and I'm kind of running out of space, so let me, I don't need this information. I don't think I need this information that much anymore. Maybe I will regret this, but I don't think I will. The asymptotes are found in this case by using, basically we're going to use the old traditional slope or point slope form, right? Because an asymptote is a line, and in this case we're going to have two asymptotes. All right, y minus y sub 1 in our case is the same thing as saying y, like y minus k. M in our case with this type of hyperbola is going to be positive a over b, which I know them are both them. I know they are both 1. And then I have x minus h. Okay. So my asymptotes are going to be two functions. And let me do this. Let me do y minus k is going to be the same as double negative y plus 4 from that equals negative or positive or negative plus or minus 1 x minus 3, which makes this y plus 4 equals a positive x plus minus 3. And a negative x minus 3. And just because time is an issue, if I were to simplify that, subtract 4, do a little distributive property, I have two equations, y equals negative x minus 1, and y equals regular x minus 7. So this is all the information I need. I'm not even going to try to graph this. So let me just pull it off the internet, pull it off Desmos when I graphed it myself on Desmos, and that's what you're going to end up with. Okay, you could see, like, for example, one of the horizontal asymptotes is going to cut through here. The other one's going to cut through here. My vertices are where they need to be: 3, negative 5, 3, negative 3. It's hard to see the foci. The center is 3, negative 4. So, everything is where it needs to be. And again, if you're looking at the asymptote as positive x going through 7, you can kind of see the asymptote take place. All right? Graphing these guys aren't fun. Not at all. But we did it, and I'm proud of us. Use the information provided to write the standard form equation of the hyperbola. Well, looking at these guys, my y values are the same, so we're going to use this formula right here. X minus h squared over a squared minus y minus k squared over b squared. That's going to equal 1. Okay, what do I know? Well, what I know is vertices are usually given to us by the equation h plus or minus a, and then k, which tells us that k is negative 2. Okay, I have 7 and 5. Those are 2 apart. So if I were to take 6 and add 1 and take 6 and subtract 1, that tells me that 6 is h and A is 1. So H is going to be 6, A is going to be 1, bada bing. Now I need B. I know that like in an equation like this and a hyperbola like that, my slope is going to be in the form plus or minus B over A. My slope for these guys are 11 and negative 11. So my slope, B over A, is the same as 11. Well, I know that A is 1. So if A is 1, B is 11. So I have all the information that I need to plug this guy in here. X minus H is X minus 6 squared over A squared. A is 1, so over 1. So technically I don't need the over 1, but I committed too late. Y minus K is going to be Y minus negative 2, so we'll put Y plus 2 squared over B squared. B is 11, so 11 squared is 121, and that's going to equal 1. And that's my guy, baby. That's my guy, baby. Dunzo. How many possible outcomes exist in the example? A math quiz has 5 multiple choice questions. Each question has 4 options, A, B, C, or D. Ooh, let's do a little fundamental counting principle. And of course, you can't spell fundamental counting principle without fun and prince and count and ting. But what you do when you have several things going on is you use the fundamental counting principle, which means you multiply. So problem number 1, question number 1, how many options do I have? 4. Question number 2, how many options do I have? 4. Question number 3, 4. Question number 4, 4. Question number 5, let me get 4. And you multiply everything in between, and 4 times 4 times 4 times 4 is 1,024. So that's how many options there are. So one option is A, and A, B, and A. And if you were to do that, you would have to do that 1,024 times. So that's the fundamental counting principle. See, I told you it was fun. List all the possible permutations. You got yourself a smiley face, a sun, and a heart. Well, permutations is how many ways can I reorganize this thing? Well, thing number 1 is I got smiley face, I've got the sun, I've got the heart. So that's way number 1. If I were to start out with the smiley face again, my other option is smiley face, heart, sun. So let's start out with the sun. If I start out with the sun, I could do sun, heart, smiley face, or I could do sun, smiley face, heart. As you can see, I'm not much of an artist, especially when I start to get lazy. What didn't I start out with? Heart. You should always lead with that, am I right? Then smiley face, and then the sun. And then last but not least, heart, sun, smiley face. So 6 of them. And those are all my possible permutations, which means how many ways can I rearrange this to create something unique? Well, there they are. Evaluate 8 permutations taken 5 at a time. There's 2 ways to look at this, okay? This is the lazy way to look at it. 8 times 7, 2 times 6, 3 times 5, 4 times 4, 5. So what you do is you write out what 8 factorial is until you do 5 numbers, but I don't want to use that. That's just a lazy way. That's a lazy way. Don't want to do it. Don't want to do it that way. The permutation formula is if you're given, and let me actually write it all out. If you have NPR, National Public Radio, NPR is n factorial over n minus r in parentheses factorial. So this is my n, this is my r. So I have 8 factorial over 8 minus 5 factorial. Remember, factorial means you start out with that number and you multiply one integer less until you hit 1. So 8 times 7 times 6 times 5 times 4 times 3 times 2 times an unnecessary 1. Now this is the same as 3 factorial. So 3 times 2 times 1. Now, I know that when I'm multiplying straight across the numerator and straight across the denominator, that anything that's the same up here that's also the same down there, I can just cross out. So this happens, which means I end up with 8 times 7 times 6 times 5 times 4, just like I did up here 2 minutes ago. Now, the reason why I'm showing this step is if the numbers are nice, then I can just multiply these guys together. Well, the numbers aren't nice, and I can't do that in my head, so I did it in the calculator ahead of time, and I got 6,720. Perms, not just for hair anymore, they're also for mutations. Permutate. Like and subscribe. Find the number of unique permutations of the letters in every word, every. I don't know why I said every before every word. It should be the word, but whatever. Every. Well, there's 5 letters here, but the thing that's very important is 2 of those letters repeat. If none of the letters repeated, it would just be 5 factorial. Then I'd call it a day and everybody would be happy, but that's not what I have at all. I have 5 numbers where 2 numbers repeat. If you are asked to take a permutation, okay, and that's what we have when you're rearranging things, and it says permutation, you do NPR. Okay, the total number of objects you have, you're taking r of them at a time, and depending on how many repeats you have, you just take that many factorial, do it again if you have to, do it again if you have to, so on and so forth. Okay, so if I was asked to do like Mississippi, for example, I have a bunch of P's repeating, I have a bunch of I's repeating, I have a bunch of S's repeating, and I might do like 2 factorial. For like the P's, and I don't know, I could take 4 factorial for the S's, M-I-S-S-I-S-S. So yeah, whatever. Here, I'm being given 5 total letters, and I'm taking all 5 of them at a time. And that's going to be over the fact that 2 of my letters repeat, and that's the only things that repeat. So 5p5 is the same as 5 factorial over 2 factorial. Let me write it down here. 5 factorial is 5 times 4 times 3 times 2 times 1. And 2 factorial is 2 times 1. Now, if you have something across the top that's same as the bottom and all you're doing is multiplying straight across, you can get rid of them. And now I don't really need a calculator. 5 times 4 is 20 and 20 times 3 is 60. So there's 60 ways that I can rewrite every to create a different thing. And again, since 2's repeat, I'm not going to be like, let's do EEVRY and then switch these E's to make EEVRY. No, in this case, these guys are the same, so we're not going to repeat ourselves. And that's why I divide everything by 2 factorial, so I can get rid of all those repeats. That's it. List all the possible combinations if I give you 3 letters T, V, and W taken 2 at a time. All right, so with a combination, the order doesn't really make it any different. So TV and VT are the same thing. So I have T and V can match up, I have T and W can match up, and I have W and V, or VW, Volkswagen, can match up. And that's it. And if you're wondering, well, what about WT? What about WV? Nope. Combinations, we don't care about the order. So I only have 3 of these guys. That's it. I'm done. Evaluate 18 total combinations, but only taking 5 at a time. I have NCR, and the formula for NCR is n factorial over n minus r factorial. And before you yell at me and say, this is the same as permutations. No, it's not, because this guy adds an r factorial also on the bottom. So what I have here is I have, you're my n, you're my r. I have 18c5, which is 18 factorial over n minus r factorial. So let me see, 18 minus 5, 13 factorial times r factorial, which is 5 factorial. Now, this might be overkill, but I'm going to write this all out and then all of a sudden start using common sense. I have 18 factorial. Let's write that out like I said I would, and then I decided I wouldn't do it. 18 times 17 times 16 times 15 times 14 times, ouch, my hand hurts. So I'm just going to write 13 factorial. I could write 13, 12, 11, 10, but wait a minute. 13 factorial is already on the bottom. Oh, let's just get rid of those. And then I have 5 times 4 times 3 times 2 times 1 from that 5 factorial right there. Now, I'm going to make life a little easy. 15 is the same as 5 times 3, so we can cross those out. But unfortunately, there's not much more I can cross out. So if the numbers were a little bit more pleasant, maybe I can pull that off and get some numbers that I can multiply together in my head and be okay. That doesn't really happen here. So I ran to a calculator ahead of time and found out that this whole thing ends up being 8,568. Okay? So that's combinations. With combinations, something like VT and TV are the same exact thing. We don't worry about order. Order doesn't really matter like it does in permutations. That's why that extra r factorial is there, because order doesn't matter. If I were to give you something like TV and VT, I'm just going to say, well, those are the same thing, so let's kind of get rid of all those repeats. But that's what I have here. Those are combinations. Baby. You're going to hate this one. State of the scenario involves a permutation or a combination. A permutation means that something like ABC and CBA are two completely different things, whereas a combination tells you that CBA and ABC are the same thing. So I have to find out the number of possibilities once I figure out what is this, a permutation or a combination. So you might be thinking, well, you said I'm going to hate this. Why am I going to hate it? That's not so bad. You are setting the combination on a 5-digit lock. The answer seems kind of obvious. You want to use the numbers 62413, but you don't care what order they're in. You're automatically thinking, I don't care about order. And it says the word combination, it's going to be a combination. Wrong. It's not a combination. Because if you don't care what the order is in, then I can give you 6, 2, 4, 1, 3, and that doesn't matter. And you're like, that's fine. And then I'll be like, well, how about 6, 2, 4, 3, 1? And you'll be like, that's fine. Or how about 2, 6, 4, 3, 1? And you could be like, that's fine. And I can go all the way down the list and tell you all these different permutations, and you don't care which one, just list all the possibilities. So after all of that, and seeing that word and seeing the phrase don't care what order, you would think combinations, but it's not. Tricky, 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 tricky. Permutations. Now, I have 1, 2, 3, 4, 5 numbers. So I have 5 total permutations. And I'm going to take, are any of them different? Nope, they're all unique. So I'm going to take all 5 of them at a time. No repeats, so I don't have to worry about repeats and dividing stuff. So it's just going to literally be 5p5. And whenever you have 5p5, it's just that number factorial. So this is 5 times 4, 20, times 3, 60, times 2, 120, times 1, still 120. 120 different permutations, even though it says combinations in it. I hated it. I hated it. Tricky. But don't be fooled by the rocks that I got. Jennifer Lopez. Jennifer Lopez. She's from the Bronx. Like and subscribe. Cody is carrying 7 pages of math homework and 3 pages of English. Oh, that's the way it should be, Cody. Math is more important. A gust of wind blows the pages off of his hands, and he is only able to recover seven random pages. What is the probability that he recovers all of the math homework? Well, we have 7 maths, and we have 3 Englishes, giving us a grand total of 10 pieces of paper. All 10 of them are laying on the ground. He picks up one of them. The probability that he picks up a math one is 10. Then he picks up another, but there's only 9 left. Also, there's only 6 math ones left. Then he picks up another one when there's only 8 total papers left, and there's 5 total math ones left. Oh, pretend that I didn't put that dot there. That means nothing. I'm trying to lead to something. All right, 7 total pieces of paper left. 4 of them are math. 6 total pieces of paper left. 3 of them are math. 5 total pieces of paper left. 2 of them are math. 4 total pieces of paper left. The last one is math. Whenever you're doing probabilities and you're doing different probabilities, different events at the same time, you multiply. Multiply, multiply, multiply. That's the fundamental counting principle. And I'm not going to pretend like I did this all on my own. I didn't. I used the internet and I got 1 over 120. So you're thinking, oh, 7 out of 10 pieces of paper. I'm probably going to pick up all math. No, you're probably not going to pick up all math. Probably not at all. And the probability of me getting only 7 pages of math, even though there's more maths than English, is not high at all. It's 1 out of 20. That's less than 1%. That's how you do it. A class has 6 girls and 5 boys. If the teacher randomly picks 6 students, what is the probability that she or he will pick exactly 3 boys? 3 boys. All right, so we've got 6 girls, 6 G, and 5 boys, giving us a total of 11 children. Okay, so me closing my eyes and picking, what am I doing? A boy is right now 5 out of 11. Me picking a boy again, well, there's 10 students left, is going to be 4 out of 10. And me picking a boy again, if there's 9 students left, is going to be 3. Now I have to pick only girls. So there's 8 students left, 6 girls, 6 out of 8. 7 students left, 5 of them are girls. 6 students left, 4 of them are girls. When I multiply all of this together, I end up with 5 out of 231. So not very likely. Not very likely at all. But this is me closing my eyes with a room that's nearly half boys, half girls, and saying, I only want the guys. Probably not going to happen. You're probably going to pick a girl. But it's possible. It's not likely. Find the first 4 terms in the sequence given to us by a sub n. A sub n means the nth term, equals a sub n minus 1, which means previous term times 3. My first term is 3, so the first 4 terms, well, I already have the first term. It's 3. The way I find the second term is I use this formula and I say the second term is going to be a sub 2 minus 1 times 3. A sub 2 minus 1 is the same as a sub 1. And a sub 1 is 3, so 3 times 3 is 9. Didn't do myself a good job giving myself space there. I regret it. Let me move to the left a little bit. So the third term is going to be a sub 3 minus 1 times 3. A sub 3 minus 1 is the second term. And the second term we found out was 9, so 9 times 3 is 27. So you kind of are figuring out the pattern, I hope. 3, 9, 27, I wonder what happens next. A sub 4 is the same as, that's the fourth term, A sub 4 minus 1, which is the same as the previous term, A sub 3, and A sub 3 is 27, and 27 times 3 is 81. So my four terms are going to be 3, 9, 27, 81. I am one of these ages. 81. Just kidding. I'm 73. Find the 10th term in this sequence. Ugh, I'm going to need all the space I can get. Well, this is saying the nth term is going to equal a previous term plus the number term that you're dealing with. So we're not dealing with any specific pattern. It's not like you add 3 each time or multiply by a half each time. It's not simple like that. It's a little more complicated, so I'm going to write this all out, which requires a little bit of space. My first term, I already know, it's negative 8. It says it right there. My second term is going to be a sub n minus 1. So a sub 2 minus 1 plus 2, which is the same as the first term plus 2. So negative 8 plus 2 is negative 6. Okay, the third term is going to equal the previous term, because 2 minus 1 is 2, and then I'm going to add 3 to that. The previous term, a sub 2, was negative 6, so negative 6 plus 3 is negative 3. Okay, I think I see the pattern here. A sub 4 is going to be the previous term, so negative 3 plus 4 is 1. A sub 5 is the previous term, 1 plus 5 is 6. The sixth term is going to be the fifth term plus 6, which is 12. The seventh term is going to be the previous term plus 7, which is 19. The eighth term is going to be the previous term plus 8, which is 27. The ninth term is going to equal the previous term plus 9, which is 36. And the 10th term is going to be the previous term plus 10, which is 46. So once you kind of get the hang of it, you don't need to make everything look like we did for the second term. So we kind of whittled things down one step at a time, ended up with 46 in the end. That's my guy, and I'm sticking with 46. 46, my age in about 25 years. Just kidding. Much older than that. Not older than 46. I'm much older than 20. Like and subscribe. Determine if the sequence converges or diverges. If something converges, it's approaching a number. Like, for example, if I were to give you a pattern where I have, like, I don't know, 4. And then I divide by 2, and then I divide 2 again, and then I divide 2 again, and then I divide 2 again. You can see that this guy is getting smaller and smaller and smaller. And as I keep doing this, it's going to end up being like, you know, that's 4, that's 2, that's 0.5, that's 0.25, that's point something else, point, what is that, 125, and then smaller and then smaller. Eventually, this is going to get so small, so close to 0, that that's something that converges. Something that diverges is it's either hitting infinity or it's going all over the place. So if I were to reverse it and have something like, I don't know, like 2, 4, 6, 8. That's going to keep going and get bigger and bigger and bigger and never really approach a number except for infinity. Or if I were to complicate it and make this negative, positive, that's not going towards a number either. That's diverging. So what I want to do is let me see if I can find the first couple terms, figure this out, and see what I can do. A sub first term is going to be negative 4 times negative 4 times 1 minus 1. All right, let me get rid of this mess over here because I'm going to need the space. Okay. Negative 4 times negative 4, to the 0. That's going to become 1, and negative 4 times 1 is negative 4. Okay, so I start out with negative 4. I can handle this. The second term is going to be negative 4 times negative 4 to the 2 minus 1. So I'll just put 1 there. And so this is going to be negative 4 times negative 4, which is 16. So I went down from negative 4 and I jumped from negative 4 to 16. So it doesn't look really promising, but let's just do maybe 1 or 2 more, see what happens. So the third term is going to be negative 4 times negative 4 to the 3 minus 1, which is 2. So negative 4 times positive 16 is going to be negative 64. So there's a pattern, and that pattern is negative, positive, negative. The digit's getting larger, and we're going from positive to negative to positive to negative. This isn't going anywhere except for all over the place. This guy is diverging. Evaluate the series given to you by sigma, where it starts out at 1, goes to 5, and I have that polynomial. A series is when you take terms and add them up. Sigma is telling you sum. This is called summation notation. This tells you start out with 1, you plug in 1, then 2, then 3, then 4, then 5, end at 5, and add everything in between. So let's do that. Let's do 200 minus 1 squared, which is 1, plus 200 minus 2 squared, which is 4, plus 200 minus 3 squared, which is 9, plus 200 minus 4 squared, which is a fun game, 16, plus, last but not least, 200 minus 5 squared, which is 25. All right, let's simplify all of these guys. We got 199, which is 100 more problems than Jay-Z had. We have 196. We have 191. We have 184. And we have 175. Oh, let me just add these up in my head. 945. So that's it. We evaluated the series and we ended up with that big number right there. Bam! Evaluate the series 1 over n, where we start out at 3 and we end at 9. So again, we have our sigma right there. This says plug in 3, and then plug in 4, and then plug in 5, then add up all of those and keep going until you hit 9. So we're going to have 1 over 3 plus 1 over 4 plus 1 over 5 plus 1 over 6 plus 1 over 7 plus 1 over 8 plus 1 over 9. Stop. Let me figure out what this is in my head. 3,349 over 2,520. Yeah, that's what it becomes. Let me just quick type it into a calculator and make sure I'm right. Yep, just did. Yeah, I'm right. Of course I'm right. I did it in my head. Determine if the sequence is arithmetic. If it is, find the 52nd term. Arithmetic means is, do I have a pattern where every time I add the same exact number to get from one number to the next? So to get from 34 to 28, I subtract 6. Do I subtract 6 here? Yup. Do I subtract 6 here again? Yup. So what I have is an arithmetic sequence where my first term is 34. My common difference is, since I subtract 6, is negative 6, and what I need to do is find out the 52nd term. Now, what we're going to do is write out the explicit formula for an arithmetic sequence. Now, the explicit formula for an arithmetic sequence is a sequence that involves a lot of cursing. Ha ha ha! I'm just kidding. No cursing. We keep this kid friendly here. Although, if you want a cursing version, I'll make a Patreon or something like that. My parents would be very disappointed. Anyway, that's my formula. So if I need to find the 52nd term, what I'm going to do is I'm going to replace n with 52. I'm going to replace a sub 1, which is 34. I know that from here. I'm going to add n minus 1 in the parentheses. N, once again, is 52. 52 minus 1 times d, which is negative 6. So a little bit of PEMDAS is 51 times negative 6. I'm going to not pretend like I can do all this in my head. I typed it out ahead of time. Negative 272. So this is me asking for the 52nd term. Don't confuse this with series. I'm not adding anything up. I'm just, if I were to keep this process going, or I subtract 6 like 40 some more times, the 52nd term is going to be negative 272. Okay? Arithmetic. Not arithmetic. Arithmetic. Evaluate the arithmetic series. Now, series means you take all these numbers in a pattern and you add them all up. Now, there's a formula for that. The formula for an arithmetic series is the sum of the first n digits is going to equal n, so in this case 12, times the average of the first term and the last term. Okay, so writing out what we know, this means what am I doing? The 12th term. So the sum of the first 12 terms, where I have a first term of negative 22, so the opposite of the Taylor Swift special. My last term is, I don't know. Oh, that's a shame. So what I have to do is I have to go off to the side here. And I have to use the explicit formula for the arithmetic sequence, which is a sub n equals a sub 1 plus n minus 1 in parentheses times the common difference. I need to find the 12th term in this sequence or series. So negative 22 plus n minus 1 is going to be 12 minus 1 times the common difference is, thank goodness for that, negative 3. Type all of that into your calculator, and you end up with negative 55. So I now know that the 12th term of this sequence is going to be negative 55. Looks sloppy, not the end of the world. So that ends up being negative 462. So if I have a series that starts out at negative 22, and then I subtract 3, negative 25, and then I subtract 3 again, negative 28, and I do that a total of 12 times where I have 12 numbers and then add them all up, that's the number that I get, negative 462. That is an arithmetic sequence in action. Evaluate the arithmetic series. So arithmetic series means I'm going to have a bunch of numbers and then add them all up. If I wanted to, there's two ways that I can handle this. I can plug in 2 and then plug in 3 and then plug in 4 all the way up through 10 and then add that up. But that is not what I'm going to do here. That's not what I'm going to do here. What I'm going to do is I'm going to say, all right, well, let's find my first term. My first term has me, oh, be careful, be careful, be careful, plugging in 2. And by the way, this is not imaginary number I. This is just saying I'm starting out with variable I and is 2. So that has the potential of being confusing. Don't let it. And of course, the first term, you would think that I'd plug in 1, but actually I started 2 here. So my first term is going to be 0.8 times 2 minus 6.3, and my first term is going to end up being negative 4.7. Now my last term is actually the 9th term, because if I start out at 2 and go all the way to 10, that's 9 terms. And so to find my last term, I'm going to do 0.8. I'm going to plug in 10 minus 6.3. So that's going to be 8 minus 6.3. I can handle that one in my head. There you go. Now I'm going to use the arithmetic sums formula, which says that the sum of the first n terms is going to equal the number of terms times the average of the first term and the last term. Bada bing. So the sum of these 9 terms is going to be 9 times the first term, which I found to be negative 4.7, plus the last term, which I found to be 1.7, all over 2. You run to your calculator, you type all that in, you get negative 13.5. So there's 2 ways I could have done it, and it wouldn't have been the end of the world if I started out with 2 and then made my way all the way up to 10 and then added them up. But I have a feeling this is the way they'd want us to do this if this was on a test and they asked you to show work. I think this is the way you would impress your teacher. I know since I am a teacher, I'm impressing myself so much right now by doing this. Determine if the sequence is geometric. If it is, find the 8th term. Geometric means, am I multiplying the same number from this guy to get to that guy, the same number to get to that guy, the same number to get to that guy? Well, in order to get from 0.75, multiply something and get to 3, I multiply 4. And then 3 times 4 is 12, and then 12 times 4 is 48. Is this geometric? Yes. Now, if it is, find the 8th term. Well, the explicit formula for a geometric sequence is a sub n equals the first term times the common ratio, which is, in this case, 4, to the n minus 1 power. So let's again list what I know. Okay, I know that my first term is 0.75. I know that my common ratio is 4, and n in this case is going to be 8. So a sub 8, the 8th term, is going to be 0.75 times my common ratio 4 to the, what was it, 8 minus 1 power. So, I guess showing one step is 0.75 times 4 to the 7th. I don't know what 4 to the 7th is. So 4 to the 7th is blah, blah, blah. You multiply that to 0.75 and you get 12,288. So if you were to keep this process going, if you were to keep multiplying this by 4 a couple more times, which wouldn't be the end of the world, you'd end up with 12,288. So there you go, geometric sequences. Evaluate the geometric series. So first off, it's geometric, which means you multiply a number every time to get to the next guy. It's a series, which means you add everything up, and I want 8 terms. So this is the equation for the sum of the first n terms in a geometric sequence. You take the first term, you multiply it to a fraction. In the numerator, it's 1 minus r to the n over 1 minus r in the denominator, close parentheses. I know my first term. It looks like I'm multiplying 4 every time, so my common ratio is 4. And it looks like I'm already have 8. So if you're like, oh, I need to find the 8th term, no, I don't. If it was an arithmetic series, yes, I would. But with geometric, I don't need to find the 8th term. So that makes life a little bit easier. So the sum of the first 8 terms in this geometric sequence or series is going to be the first term, which was 2, times 1 minus r, which is 4, to the 8th power over 1 minus 4. Just showing a little bit of work. That ended up being 1 minus 4 to the 8th is negative 6,500, or negative 65,535 over negative 3. And when you multiply all that together, you get 43,690. So if I were to keep multiplying this by 8, do it a couple more times, I would have 8 numbers, and when you add them all up, you get that number right there. That's how I evaluate a geometric series without doing too much work, although the work here isn't the worst. I mean, if you had to double check your work and just go, okay, fine, times 4, times 4, times 4, times 4, plus, 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 it would be all right. But this wasn't so bad either. Evaluate the geometric series that starts out with 1, ends at 8. We have a sigma here, which means you add stuff up. Oh, this is going to be a mess. Now, what I could do is I could plug in 1 and plug in 2 and plug in 3 and do some math and add some stuff up. But that's not the way that we really should be doing it. What we should do is we should first things first find out, well, let's write out the geometric series formula. Okay? It's the first term, which I don't know yet, times 1 minus r, which I can figure out pretty easily, to the n, which is going to be 8, over 1 minus r. All right, so you are my n. My common ratio is always the guy inside the parentheses, so you're my r. Now, what I need to do is I need to find the first term. And the way I can find the first term is I just plug in 1 into that guy, which won't be so bad, and you'll see why. 32 times 1/2 to the 1 minus 1 is 1/2 to the 0th power. Anything to the 0th power is 1, so 32 times 1 is 32. There's my first term. So the sum of the first 8 terms in this geometric series is going to be 32 times 1 minus r, which is 1/2, gross, to the n. So let me put parentheses around that to make that look better. N was 8 over 1 minus 1/2. So let's show a little bit of work. 32 doesn't change yet. Let's make that bigger. 1/2 to the 8th power is an awful number. 1 minus that is going to be 255 over 256. Now that's going to be over 1 minus 1/2, which is 1/2. Now, in order to do a fraction over a fraction, you multiply the top and the bottom by its reciprocal, so the bottom, the numerator, can completely go away. So now what I have is 32 times this fraction times 2, which ends up changing it to 255 over 128. 32 times 255 over 128 is 255 over 4. So if I were to take these, plug in 1, plug in 2, plug in 3, plug in 4, all the way up to 8, then add them up, I get that guy right there. All right, so that's geometric series. Pretty exciting stuff. Calculate the limit as x approaches infinity of negative 3x squared over 4x plus 4. Normally when I calculate the limit algebraically, all I have to do is just plug in whatever number that is to x and hope for the best. Well, I can't do that. Not here. Not here because I have an infinity, and if I plug infinity, I get infinity over infinity, And that doesn't make sense. You're not allowed to do that. So what you're going to do, this little trick, is find out what the highest degree variable is on the bottom here. It's x. Take that x, put it over 1, like this, yeah, and put it over 1 again for the numerator. I'm going to multiply the numerator and the denominator by 1 over the highest degree variable. Why does this do that? Well, there's a little trick that says if you have, some number over x, and x is approaching infinity, x is going to get larger, and eventually that'll turn into 0. Okay, so I can't have infinity over infinity, but I can have something different. So let's see what happens when I do that. I have the limit as x approaches infinity, right, of negative. I'm going to multiply 3x squared to 1 over x, which cancels out an x, so I get negative 3x over distributed property, 4x times 1 over x, the x's cancel out, giving me just 4, plus 4 times 1 over x, which is 4 over x. Now what I have is I can plug in infinity now. I have negative 3 times infinity over 4 plus 4 over infinity. 4 over infinity becomes 0. So this becomes negative infinity divided by 4, which is negative infinity. And so my answer, and if you wanted to double check this on a graphing calculator, you will see a type of line that kind of just dips down like that. This will head towards negative infinity. So when you get infinity over infinity, your decision is, well, which infinity is it going to? Where is it going first? Negative infinity is going to be my answer here. Tricky. Calculate the limit as x approaches 1 of stuff. Whenever you're trying to find the limit algebraically, you just take that number, substitute it in for every x, and hope that nothing crazy happens. Now, I'll tell you what I mean by something crazy happening. That's not going to happen here. Okay, we can plug in 1 for x squared, so this will look like negative 1 squared over 2 plus, plug it in again, 2 times 1 plus 4. And then use the order of operations to simplify stuff. So negative 1 squared is 1, so we get a half, plus 2 times 1 is 2, plus 4. Negative 1/2 plus 2 is negative, just kidding, 1.5 plus 4, which is 5.5. Now, this is just a normal number, which means this is my answer. Now, if I were to have something like infinity over infinity or 0 over 0, that would be a problem for a later day, which I know you will see if you continue to watch my videos. But all we have to do is take care of that. That's it. Compute the limit as x approaches 1 from the right side of this whole thing right here. Now, there is an algebraic method that you can do this. If I were to plug in 1, that would give me my answer as long as this whole thing isn't undefined when I plug in 1. Well, I'll tell you what right now. If I plug in 1, I get 0 on top. I get 1 minus 2 plus 1, which is 0 on the bottom. I can't plug in 1. This is undefined at 1. So what I need to do is I need to graph this. Now I'm going to use a graphing calculator and paste the graph of the picture right here now. Now, as you can see from the picture, the limit at 1 actually doesn't exist because the left side and the right side don't meet up. But what this plus sign is saying is, where is my limit headed as it approaches 1 from the right side? As you can see from the picture, once I hit 1, it kind of dips down to negative infinity and keeps going to negative infinity, which would make my answer negative infinity. Now, if this was a minus sign, that would mean from the left, that would be positive infinity. And if I were to put just regular 1 here, since the left and the right side don't meet up, the limit does not exist. But in this case, I only care about where my number is going, where this graph is going as it approaches 1 from the right, and it dips down, which means negative infinity is going to be my answer. Find the derivative using the limit definition. Oh, this one's going to be fun. The limit definition of the derivative is this. The limit as h, you might be thinking, what's h? You'll see. The limit as h approaches 0 of f of x plus h minus f of x all over h. This will give you the derivative. It's a mess, and there are shortcuts, but this is the problem that I created, so this is the problem that we're going to do. What I like to do is I like to take turns writing out what this is going to be, f of x plus h, and then kind of like plugging everything in, and magic will happen. But the first thing I need to do is find out what f of x plus h is. So to find f of x plus h, you need to rewrite this original equation. And remember, y and f of x, same exact thing. You're going to rewrite this equation, and you're going to replace every x value with x plus h. So f of x plus h is negative x plus h in parentheses squared plus 2 times x plus h in parentheses plus 1. So what I'm going to do is I'm going to write out that x plus h squared is a perfect square trinomial. I can FOIL this, split this and FOIL it, but I'm going to be a little lazy and just say that becomes x squared plus 2xh plus h squared. This is distributive property, so plus 2x plus 2h, and then plus 1. Distribute this negative, negative x squared minus 2xh minus h squared plus 2x plus 2h plus 1. Now, you might be thinking, oh, please let one of these guys cancel out. It won't, but don't you worry. It will, something eventually will cancel out. Now, what I'm going to do is I'm going to, over here, rewrite this guy, right? I already know that f of x plus h is this. So I'm going to write out the limit as h approaches 0 of f of x plus h, which is blah, 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 blah. So negative x squared minus 2xh minus h squared plus 2x plus 2h plus 1. Now I'm going to subtract f of x. I know what f of x is. It's that guy. So remember, when you subtract, and I'm going to skip a step, when you subtract a polynomial, you are distributing a negative. So when I subtract this green parentheses, flip the sign. So you become plus x squared, that's good news, minus 2x, that's good news, and minus 1, that's good news. Now you might be thinking, why? Remember how I mentioned magic before? Well, things are going to disappear. First, I need to put this all over h. Negative x squared and x squared cancel out. You should expect this to happen when you do problems like this. What else cancels out? 2x, negative 2x, positive 1, negative 1. So I now drop down the limit as h approaches 0 of negative 2xh minus h squared plus 2h. Now you might know from limits and computing limits algebraically that if I were to plug in 0 for h, and h, I would get 0 over 0, which is indeterminate, which is against the rules. But if I have an h in common with all of them, can I just factor out an h? I'll tell you, you can. So the limit as h approaches 0 of, let's pull out an h, negative 2x minus h plus 2 over h allows me to cancel out these h's. I missed. So the limit as h approaches 0 of negative 2x minus h plus 2 is going to turn that minus h into a 0, negative 2x minus 0 plus 2. And since I'm running out of room, I'm going to skip the minus 0 part and leave it at that. That is my answer. It's a mess. There are shortcuts for this, and I will have videos showing you the shortcuts, but this is using the derivative definition, the huge limit crazy thing right there. Always expect things to disappear. Always expect to factor out an h, and then your answer will be a whole lot friendlier once this whole mess is taken care of. Find the average rate of change over the given interval. So we have an equation, y equals x squared plus 2. We have an interval. I'm going to change that y into f of x just because it's the same thing, but I'm going to change it because I'm going to write out this formula right here. The average rate of change is the same thing as f of b minus f of a over b minus a if b and a are the endpoints of your interval. And you might look at that and say, well, that's a lot like slope. Yeah. Yes, it is, because rate of change is slope. So what I have to do before I even start this is I need to find out what f of b, or f of negative 3/2 is, and what f of a is. So f of b is going to be f of negative 3 over 2. And that's going to become negative 3 over 2 squared plus 2. Negative 3 over 2 times itself is 9 over 4 plus 2, which is, what is 9 over 4? 2 1/4. So 2 1/4 plus 2 is 4 1/4. 4.25. All right, so that's f of b. Let's get a different color and do f of a, which is negative 2. So f of negative 2 is equal to negative 2 squared plus 2. Negative 2 times itself is positive 4. Positive 4 plus 2. This math is a little bit easier, 6. So now that I know that information, f of b is f of negative 3 over 2. And f of negative 3 over 2 is 4.5. So f of b is 4.5. 4.25, apologies. Minus f of a is negative 2. F of negative 2 is 6. So 4.25 minus 6, all these colors, over b minus a is going to be negative 3 over 2 minus 2. So I'll just write that down in black. Negative 3 over 2 minus negative 2. 4.25 minus 6 is negative 1.75 over negative 3 over 2, double negative. So negative 3 over 2 plus 2 is 0.5, and that's positive. And negative 1.75 over 0.5 is negative 3.5, I think. Yeah. Negative. We got a negative 1. So negative rate of change is decreasing, which makes sense because that's a parabola going down in this area. So I like it. I like it a lot. Find the value of a that makes the function continuous everywhere. So we have ourselves a piecewise function. That's a mess, but it's over t squared. It tells you that t can't be 0. Well, it makes sense because if you were to throw in 0 for this guy, you would get 0 squared on the bottom, which is 0, which means you get an undefined function, which is impossible. So what's going to happen is you're going to get a graph of this, and you're going to have a hole or an asymptote of some kind or a breakage at 0. But I need to fill that 0 in. Now, I'm like, okay, well then find where things fall apart. Well, I can't just plug in 0 because it won't work. So what I need to do is I need to run to Desmos and make a graph. So I'm going to go to Desmos and do a graphing calculator. You could also do a regular graphing calculator, run to your own graphing calculator, but I'm going to graph this guy right here and see where my equation exists at 0. And then I'm going to paste that graph right there. All right, so if you take a look at my graph, and I zoomed in quite a bit, I typed this exact same thing into Desmos on my phone. I had to use X's instead of T's because that's all it gave me for the phone edition of Desmos. If I were to try to take my thumb, or if you're on a computer, take your mouse and hover over where X or T is 0, it'll say undefined. But if I get awfully close to 0, it'll tell me that t, or the y value, is 0.25. So in order to fill that hole in, a has to be 0.25. Right now, I see this weird image that looks like that, but there's a hole there at 0.25. By allowing a to be 0.25, it fills that hole in. Now it's continuous everywhere. That's my answer. Find the derivative of y equals 5/4 x to the 2/3. If you're just finding the derivative of a polynomial and you have a bunch of, exponents, variables, coefficients here and there, that requires only the power rule. Now, this is what the power rule says. I'll just write out the definition. d dx means you take the derivative of, some constant I'll call a, x to the n power. This is what I have here. A would be 5/4, x is x, n is that exponent right there. What you do is you take that n, you drop it down, you multiply it to the coefficient, keep x, and subtract 1 from n. That is the power rule. Again, bring the exponent down, multiply it to that, subtract 1 from there. So let's get rid of this. Okay, let's get rid of this now that I know that. What I'm going to do is y prime, or I could call it dy dx if I wanted to. I'm going to take that 2/3, I'm going to bring it down, multiply it to the 5/4 that's already there. X is x, and 2/3 I'm going to subtract 1 from. All right, so a lot of cleanup on this problem, but, that's fine. It's part of the job. 2 times 5 is 10. 3 times 4 is 12. I can simplify that. X to the 2/3 minus 1. That's the same thing as saying 2/3 minus 3/3 for those of you who hate fractions. All right, so let me clean all this stuff up a little bit. That gives me 10 over 12 is 5/6. X is x. 2/3 minus 3/3 is negative 1/3. So the way I will wrap this problem up, and I'll actually take 2 steps to wrap it up, is a negative exponent drops x to the other side of a fraction bar. Right now, it's on the invisible top of a fraction bar, even though, there's no fraction bar. I could put over 1 if I wanted to. Now I have it on the bottom. So 5 remains in the numerator, 6 in the denominator, x to the drop it down and make it positive 1/3. Now, you can leave it like that if you want to, but an exponent of 1/3 also gives you the cubed root, so this is the other way that we could write this out. Either of these is perfectly fine, either of these is simplified, and that's my guy. y equals negative x squared. Find, this means the second derivative. So I'm going to take the derivative once. I'm going to take the derivative a second time and see what I get. So the first derivative, d regular y, d regular x, forces me to use the power rule. So the power rule is you take the exponent, you drop it in front of the x, or multiply it to whatever coefficient is there. My coefficient's -1, invisible 1, but -1. So I would I'll keep the negative there, drop the 2 down, the 2 in front, keep x the way it is, and subtract 1 from the exponent. So 2 minus 1 is 1. That's sloppy, so -2x. Now I have to take the second derivative, which means I take the derivative of that guy right there. So the way you write out the second derivative is d squared y dx squared. You could put, that would also mean second derivative, y double prime, but, whatever. Whenever I'm taking the derivative of a coefficient, forgot my word there, times x, just an x to the invisible 1, you just have the constant now. So if you're wondering, well, why? Well, pretend that's an invisible 1, multiply the 1 out in front, nothing changes, subtract 1 from 1, so x to the 0 is nothing, the x goes away. This is my answer right here. So the second derivative of negative, that's the worst looking circle I've ever made in my entire life. The second derivative of negative x squared is -2. That's it.